All right, are we ready? Okay, welcome everybody to Punch 5. I can't believe it, Punch 5, right? We've been doing this for a while. We're really happy you're here. We're looking forward to an excellent meeting. We have lots of great talks. I'm going to start out by just giving you a few logistical things. Then Barbara is going to walk us through how we're going to use the Slido to ask questions. And then we'll get going on the schedule. So first logistical thing, bathrooms. Bathrooms are over here. Oh, actually, let me introduce Carrie Don, because I'm going to be mentioning her more than once. Carrie Don is our wonderful runner of shower. So if you have any questions, please go and ask her at the front desk. Also want to introduce Kelvin at the back. Kelvin, wave your hand, and his colleagues out there. Let me just mention to you up front that if you have a talk and you've loaded it on the Google Drive, if you end up doing a change to it and you reload it on the Google Drive, it'll sit merrily on the Google Drive and won't be changed unless you make sure that you've closed the loop with Kelvin and he's downloaded it, because that's where it's being presented from. So make sure you've double-checked that if you do make a change to your talk. And please do that during the breaks, because during the talks, they're quite busy running the talks. Secondly, the bathrooms. In that corner there, we have bathrooms. We have bathrooms on all the floors. At the front of the building, in the third floor, we have gender-neutral bathrooms. We also have a lactation room if anybody needs it. And you can ask Carrie Don, there's a key for it, and she can help you get that. We have lunch talks both days. So we have at 12 o'clock, we're gonna break. We have a line for lunch. You can come back in here and eat at these tables. Today we have an amazing open data science talk by Barbara Thompson. It's actually more of a kind of showing you how to do stuff with the web. So it's gonna be quite interactive and fun. Tomorrow we have the head of NASA heliophysics giving a presentation. He's going to be virtual, so it'll be on these screens. It'll also be on the large screen in the lobby if you wanted to watch it from there, so that's also fine. We have an hour for poster after each of those lunch presentations, so you have an hour to walk around, go see the posters, interact, etc. This evening we have a reception. Looking forward to talking with y'all then as well. And I think those are the logistical things I wanted to mention up front. So I want to turn it over to Barbara now, and she's going to basically walk us through the Slido. Oh, one last thing. The Slido, you can access through a slido.com that she's going to tell you. There's also a QR code. I want to point out that on the back of your badges, there are 2 QR codes. One of them is the Slido for asking questions, and the other is the agenda. All right, Barbara, take it away. Do you want to do it down there or up here? You have a mic. Oh, I meant because I thought you were using the computer.
Oh, hello. Hi, everyone. Yeah, so thanks, Kelvin and what's your name? Kelvin and Joey, thank you guys. You guys do such a good job on this. All right, so if you haven't used Slido before, it is a web-based interface to ask questions and also interact about the questions. So Slido, you can join it 2 ways. If you want to ask questions, interact on a phone, you can use the QR code. If you want to use it on a laptop or a computer, you go to slido.com or slide.do and enter that access code. Now, the reason we use Slido is a couple of things. I think everyone's been in a meeting where it was the speaker gives a wonderful talk, and then the first question completely sidetracks the discussion, and the speaker isn't really doesn't get the interaction that really is beneficial to the speaker, and often sometimes not even to the audience. And so Slido has several benefits. One, you have to phrase your question in advance. You have plenty of time to phrase it. You can think of it. 2, people can upvote the question. So even if you don't have a question, please have a presence on Slido, because if you think there might not be enough time to answer questions for the speakers, and so you can help determine, oh, I think that's a great question. I'd like to upvote it. We will choose the questions in order of the audience vote and not in the order that they are asked. And so you guys to help determine what the interaction is. And yeah, so that's, and the third reason is because you know, that gives the audience also, you can interact. If somebody has a question and the speaker has an answer, but you have something to add, you can add it there. If you say it in the audience, that's fine. Whoever remembers it, remembers it. We have a record now of the discussion, and so please have an online presence. Now, there are some of you that aren't going to be having a phone or a computer. If that's the case, then I can either give you pieces of paper and you can write down your questions or something like that, or if we run out of time, we can also take questions from the audience. My intention is to have the person who asked the question to actually stand up and ask the question anyways. Or if they're online, online they can unmute it. Oh no, they can't. Okay. All right. So the person in the audience, if you're here, you can ask the question, because if you do have a question, it's good that people get a chance to know you. Please introduce yourself. If I call on you, if I say Velmir, you have a question, stand up and you say, "Hi, I'm Velmir Morai, and right, and I'm graduating soon, and I'm awesome, and so you'd be lucky to have me work for you." So, anyways, go ahead and do that. Introduce yourselves. Now, there are 3 rules. These are based on the science fiction author John Scalzi. Scalzi's rules for questions and answers. 1, it must be relevant to the presentation. It's about the speaker's talk, and that I know you guys have all done brilliant work and you're all interested. If you have something that is about your work or is peripheral to that, hey, you can talk about it during the break, or you can mention it during your, to the group. But it has to be relevant. It has to be fit in the space of a tweet, which is nice for Slido. It has to be compact, and it has to be a question, right? Okay, so those are the 3 rules. And again, we have plenty of discussion time, and we one of the most important things that comes out of these meetings isn't just the presentations, it's this discussion and interaction afterwards. So please, if you think a talk is fascinating, I really hope that you guys have a long, nice discussion out there. But yeah, try to keep the conversation in the room relevant to the talk itself. And then talk about what we're all going to do in the future there. So let's see. So how can I possibly pontificate for 10 minutes while pretending to ask a question? Well, you're the PI, so Craig, you're allowed. Everybody else, you can pontificate all you want. See those doors? Yeah, there you go. On the other side of the doors. Do the holes in a donut radiate calories? Oh, that's true. Okay, so if you're wearing a fitness tracker, then donut calories don't count. That's really important. So be careful. Don't forget your fitness tracker. All right. Why is Punch so awesome? Oh, well, that's what these 2 days are about. So does anybody have any questions? Yes.
On my phone, and I see a place to ask a question. I just ask a question, but for a second there I was like, but how do I upvote? Can you tell people? Oh, there's a little
Thank you. So you press on the Q&A. There's a little Q&A button, the upper right, and you're going to see, oh, look at that. Sarah has 7 upvotes. Can we please, everyone in the audience, upvote Sarah's question so I can see for sure that you guys, 8, 10, 12, nice. All right, you guys are doing a good job. Oh, that's right, and Sherry, thank you. Sherilyn Moreau says, yes. What a perfect day for a Punch meeting, right? We're going to get really good at this by about 4 o'clock tomorrow.
Thank you, Barbara. So it is my pleasure to introduce our first speaker, who will come up and pontificate. And he's going to tell us about how the future is so bright for Punch. And, oh, his name is Craig DeForest, and he's the PI of Punch.
Morning. So you may see I'm wearing sunglasses. I'm going to take them off, but these are the coolest sunglasses on the block, and we have a whole bunch of them for free out front. So if you don't have a set of polarizing Punch sunglasses, get some. They're really good. All right, so overview and status. I only have about 94 slides. We're going to go fast through the first ones because most of you have seen most of them, but some people haven't. So if you haven't seen these, try and keep up because everyone else is drumming their fingers waiting till we get to the second half. Next slide. Oh, right here. Boom. Is this working? Yes, okay. So what are we doing? Punch is the opposite of Parker Solar Probe in some ways. Solar physics has traditionally been a remote sensing field. Solar wind physics has traditionally been an in situ field. Parker Solar Probe famously has brought in situ sensing inward to the sun. We have a probe that's now flying through the corona and bringing us ground truth of the physics that are going on there. However, in situ probes don't capture the global and cross-scale phenomena that are so important to collective behaviors of the system. And so Punch goes the other way. We're bringing imaging technology outward into the solar wind and bringing to bear the kinds of techniques that we've seen on the sun out in the solar wind itself. So this is the overview. We are trying to understand how the corona gives rise to the solar wind and the heliosphere as a whole. We are doing 3D imaging. You'll hear more about that during the week, and you have heard over the last few years a lot about that. We're taking polarized visible light images. We have 4 small sats. Something that keeps coming up, despite the fact that we all in this room know better, is we are not doing stereoscopy. We have 4 satellites because there's a darn planet in the way, not because we're trying to view the sun from different angles. So the 4 small sats are essentially in the same place on the solar system scale. We are in phase D right now. We are hot and heavy in integration and test. We have one of our observatories, the NIFI observatory, is in thermal vac right now as we speak. Our next milestone is this fall, and that's our pre-ship review to get ready to go out to Vandenberg. This is our science. You're all familiar with this. These are the 6 science questions. The working group 1, A, B, and C are about solar wind flow and the background solar wind, trying to understand the physics of the place where all this is happening. Working groups 2, A, B, and C are about transients, CMEs, CIRs, and shocks that propagate through that, the bright, fancy stuff that makes space weather happen, or at least the most severe space weather. We have collaborative science with several other missions. Parker Solar Probe will get the global and local picture of coronal dynamics. That I'm very excited about that because we will have cross-scale studies with Parker Solar Probe that span over 9 orders of magnitude in scale, which I think is the broadest scale of any astronomical observation. So I'm pretty thrilled about that. Solar Orbiter, multi-vantage observations, SDO, and of course many future missions that are coming up, MUSE, Sunset, Vigil, Cubics, Proba 3, name your favorite here. We will be providing synoptic data of what the outer corona and inner heliosphere look like, so your favorite mission can collaborate with us. If anybody asks you, the answer is yes. We don't run campaigns, but we do provide data to anybody. There's additional science I've been thinking about this spring that I think we've all heard about, but I just want to highlight again because you'll start to see these people showing up at our meetings. Polarimetric astronomy. It turns out the star field is polarized. That there's a lot of important information there. That's not our prime science, but we will produce the best polarimetric astrometry measurements ever made over a wide part of the sky. Comet and asteroid inventory. People already want to use punch data to look for volcanoids and to investigate comets, things of that nature. We will see every comet. And I've just got out of a meeting with the Tracers team talking about magnetospheric jets. Tracers was selected at the same time we are. They are a magnetospheric mission. Bernie Jackson knows a lot about the High Altitude Aurora, which was, I think, discovered by SME. And we'll be flying under it and seeing it as well. But the Tracers people really want to exploit it. So sort of neat stuff on the horizon that's far afield from our main science. We've all seen this a million times. I know you're tired of it. This is what we do. We track things from the outer corona on the right to the inner heliosphere on the left. That mosaic behind you is from, or behind the yellow is from stereo. And it's just sort of giving a sense of where our field of view lies in polar coordinates here. So we'll have a continuous view from the inner part of the LASCO C3 field of view out to 45 degrees from the sun. What's new? Wide and continuous field of view all the way out to 180 RS. That's just direct angle. If you're using tan theta, it's different out there, and so it's 200 and more. High sensitivity. If you're used to legacy instruments where 30 times more sensitive, that has a lot of impacts, including better resolution, which is coupled to sensitivity. We'll be operating at 4-minute cadence throughout the mission, so we'll be able to see the time scales on which these structures evolve. And of course, we're the first wide field polarimetric imager. So we'll be able to extract polarization to find the 3D location of things. And I've been harping on this for a long time, so you're all familiar with it. These are the two instruments, or the two types of spacecraft. On the left, we have the NIFI spacecraft. That's the one in thermal vac right now. It has both the NIFI instrument, which is a coronagraph, narrow field imager, and the STEAM student instrument, which is an X-ray spectrometer. I'm pretty proud of that instrument and of the team that made it happen. You'll hear from Mary Hansen, who led that a little later in the morning. By the way, in case you haven't heard, Mary had some kind of a bug this morning, so she'll be presenting remotely rather than here in person. And then the Wide Field Observatory, we have 3 of them to look out in different directions. That is a true heliospheric imager. It's similar to a coronagraph, but in linear geometry. So we have at the front an artificial horizon made of a solar baffle, and we peek out over that to look out 45 degrees from the sun. This is how they work together. The fields of view all mesh, they overlap. Every field of view of each instrument overlaps with all the other ones so that we can cross-calibrate. As the spacecraft orbit the Earth over the dawn-dusk terminator, they paint a large field of view on the sky. Out to about 80 solar radii, we get an image every 4 minutes. And then all the way out to 45 degrees from the sun, we get an image at a little longer cadence, about every half an hour. Making these data work together has taken a tremendous amount of effort. I'm not going to spend a lot of time talking about the SOC, but I just want to highlight some of the things that we have done. We have advanced the state of polarimetric analysis, which really surprised me, given that it's been going on since 1611 or so. I'm confusing the two. 200 years for the polarization. And then over on the right, we developed a feasible PSF regularization scheme, which we're applying to every single image, which will remove coma from the images and produce images from a single ideal telescope. So we're pretty pleased about that. Lately, I just saw a SOC demo, which I think you may see from Marcus, showing that we can showing that we can stabilize the star field to better than 1/100th of a pixel on average. So I'm pretty thrilled about that too. Lots of groundbreaking going on in the ground processing. This is our schedule overview. You are here, that's in red, that's Punch 5, 20 June 24. A year from now, we will have Punch science data in hand. We are in the final approach to launch. I'm pretty darn excited about that. It's been a long road. We're launching on a Falcon 9 rideshare with SphereX. So we're flying on a Falcon 9 out of Vandenberg. We are right now scheduling the Punch 6 meeting. I can't announce a launch date for you, but I can tell you when the Punch 6 meeting will be, which is very likely the week of the 24th of February. So plan for that, and we'll be getting more info in the email soon. We have an outreach program I'm very proud of. Sherilyn Morrow is here. Where are you, Sherilyn? Right there. She's been sending out public engagement newsletters every month. If you're not getting them, please talk to either me or to Sherilyn and get on that list. They're really cool. And there are a lot of things going on. We've had a national impact. There was a huge flurry of activity around the eclipse. Sorry, I used the word impact. We're tied into many other missions and events, and we're expecting a couple of planetarium shows to come out soon. There's just a tremendous amount going on, and I won't steal your thunder. So just a couple of beauty pictures of things. The NIFI instrument is integrated. I just had to throw this up because you can sort of see the overall structure of the instrument. The observatory here is in a cage in San Antonio that is NFI or NIFI mounted on a spacecraft. The STEAM instrument is in the upper left there. It's integrated to it. Vibration and optical tests are complete, and we're in thermal vac now. Of course, we have one more set of optical tests at the end to make sure that we didn't break anything. The Wi-Fi instruments are fully integrated. You'll hear more about that from Glenn. They are, well, there are 2 of them pictured here, but there are 3. These are images of the optical checkout. You'll probably hear more about that from Glenn in a minute. On the left is an image of the team taken through the instrument itself in the clean room. So pretty neat to see everything come together to make images actually work from end to end. This is a vibration test of the Wi-Fi 1 observatory just a few weeks ago. That's the observatory sitting on the table there. I like this picture because it lets you see how small these instruments really are. They're a little too heavy to just hoist, but 2 people could lift one pretty easily. The particulars of the launch. We're going to be launching on a Falcon 9 from Vandenberg no later than the 1st of April and potentially earlier based on what we're seeing in schedules. This will be a late dusk launch. SphereX can't look at the sun, and so in order to avoid any risk of that, we'll be launching a little bit after sunset and then plane changing on orbit. This is what happens when you have a sports car of a rocket with lots of extra delta V. You just, no big deal, we'll change the plane. This type of launch has been spectacular. This is another Vandenberg launch that just happened a few days ago, as seen from either San Diego or northern Mexico. So these things are spectacular to see. We are planning Punch 6, and Phase E will be 90 days after launch. So sometime next spring, we'll be seeing data. Transition to Phase E. I'm not going to run through all this. Basically, right now we're starting the Phase E proposal. We're doing budgeting and scheduling so that we can get a proposal to NASA in good time for a smooth transition from development to operations next spring. So we are deep in Phase D. Lots of things are happening. It seems like every day something gets broken and something gets fixed. We're doing final integration and observatory level tests. The SOC pipeline is making huge strides, and I cannot stress enough how big of a deal this is. The SOC should be ready to turn the key on, I think I'm out of time. Oh, SOC, Science Operations Center, which has the reduction pipeline, has possibly the most sophisticated sequence of operations of any heliophysics mission, just to get the data to you. So we'll be delivering background subtracted, thoroughly massaged data. And you'll hear more about that from the SOC team a little later on. We're seeing major progress on the MOC. That's the Mission Operations Center, making sure we can get commands sent and raw data analyzed. And be ready, because you're going to be getting data and they're going to be awesome. That's it.
Thank you so much, Craig. And if you have questions, please put them into the Slido. We're going to have all 4 of our speakers come up and sit here at the end, and we're going to go through the questions then. Our next speaker is Robin Colanino, and she is going to be talking to us about the NIFI instrument, the Near Field Imager. Go ahead, Robin. I'll give you 2 minutes.
Hi, I am Robin Colanino from the Naval Research Laboratory, here to talk to you about the NIFI instrument and where we are. So, as you might have gathered from Craig's talk, NIFI is going to provide the interior part of the unified punch field of view from 6R sun to 30R sun, and we'll be delivering exceptionally high spatial and temporal resolution for that inner field of view. This is the NIFI, where the circle in the middle there, you can't tell from the circle that we are also spinning. just like the Wi-Fi field of view. So that'll be an interesting new take on coronagraph data. So here's the Wi-Fi instruments in all its glory. The top, we have a side of the outer view. Then here in the bottom left, we have a side view cutaway where you can see all of its parts with the occulter in the front inside the green baffle here. And then we have a silver heat rejecting mirror followed by the lens assembly. And then, of course, at the back, we have the camera. And then purple here, we have the radiator for the camera sitting on top. We also have a top cutaway view in the right, and so you can see we also have a polarizing filter wheel and motor that is snug against the lens. And I'll go through all of these components in the talk. So we go forward. So the thing about NIFI and Wi-Fi is, and you can see this very well illustrated here in the block diagram, is that they are very similar instruments, and that's on purpose to create this unified punch field of view. Here we have the block diagram of the NIFI on the top and then the Wi-Fi on the bottom, and we leverage this similarity by also having common subsystems to both of the instruments. These common subsystems are the polarizing filter wheel and the camera, and then we also have the same actuator for the door. And this actually presents the same electrical interface to the spacecraft for both instruments, and that means that we also have the same physical mounting points for both of the instruments too. So that allowed the spacecraft to be agnostic to which instrument was actually installed on it. So really trying to create this, even though we have two different instruments, trying to create one punch mission. In addition to the hardware being similar, the observing plans will also be similar. You can see the Wi-Fi and the NIFI observing plans down here. The orbit is divided up into these 8-minute observing blocks as we kind of tick-tock around in the orbit. And during those observing blocks, both the Wi-Fi and the NIFIs will be taking coordinated polarization images and clear unpolarized images, and then another set of polarized data. So those will all be synchronized to create, to give to the SOC to create these beautiful images. So let's get into the subsystem hardware. Here's some beautiful hardware photos for those of you who are into that kind of thing. Here is the front of the instrument, and we call it the stray light suppression assembly. That's where the magic happens. This is where we take out enough of the solar brightness and then the stray light from the solar brightness so that we can image the corona. In front, we have this occulter, which you can see here, and it is mounted onto the pylon at the front. Also, you can see it from the view over here. It is inside this A0 aperture, which is our entrance aperture to the instrument, to the front of the baffle assembly. Then we have our HRM, which then rejects any light that comes out that we don't want, and our A1 aperture, which is actually the entrance aperture to the telescope. The occulter actually vignettes the field of view, as if you're familiar with coronagraph data, that's how it works. So the vignetting function actually serves to flatten the gradient in the corona, and then here we also designed NIFI so that we actually had a region that overlaps with Wi-Fi where we don't have, this is only the optical vignetting, not the vignetting from the occulter, so that we have a good region to overlap and do calibration in that region. Moving on, we have the optical lens assembly. This is a 6 optical lens assembly. This is down here in the barrel, the lens assembly with all of the optics mounted. We designed this at NRL. This has high heritage from the Solo High and Whisper optics. And you can see over here, it's actually mounted into the instrument with its thermal hardware and a black lens cap on the back here. And so this lens is going to produce a superior spatial resolution, and it also has a bandpass that matches exactly with the Wi-Fi's, which is a novel if you've ever used the stereo instruments. Moving on. in between the optics and the occulter, we have what's called a heat rejection mirror. This is an off-centered parabolic mirror. You can see it here. Oops, make a dot. All right, oops. That's not what I wanted the clicker to do. Okay, up here in the top right, we have the mirror itself. It's a very high quality mirror, and then that is mounted inside of the baffle housing for NIFI, and then what that does is you can see from the rays here in the middle image, it makes a real image of the sun opposite the pylon and above the occulter, and then all of that light is rejected out of the baffle to reduce stray light inside of the baffle, and also to prevent heating of the rest of the telescope. So we want to keep the rest of the telescope much cooler than the sun wants the telescope to be, so we're rejecting both the heat and the light out of the front of the baffle assembly with that component. So the NIFI structure itself, to hold and align all of these various important optical components, is aluminum tube at the front. It has 3 major components. You can see them here in the bottom. We have the solar stray light suppression tube, then we have the optical housing, and then in the back we have, there is a clamshell that holds the filter wheel, which has these long legs. The legs were a little bit wide in the back so that we can match the Wi-Fi physical profile on the spacecraft. That's why we have these kind of wing-like legs. And then mounted to the back of that is the camera box, which you can see at the top right here, which also has all of its thermal hardware installed on it. That's why it has all these wires flying off of it. And then NIFI is mounted to the spacecraft with thermally isolating kinetic titanium mounts. And then we are aligned to the spacecraft with those mounts. The NIFI door is here at the front, and it's really there to provide protection from contamination during the integration, launch, and early operations. It is a one-time door with a wax paraffin pin puller. If somebody can click on that movie, that's actually a movie that will go. It's very slow. This is actually the door deploying in TVAC, so this is at temperature in vacuum, so just as it'll happen in space. Doesn't have sound. It's in a vacuum. There you go. People get scared when they hear your door open. So there it goes. So it deploys back and out of the way so that NIFI has this 180-degree field of regard, and so that we don't have anything in the front of the field of view. So, okay, and then one of the common subsystems, as I mentioned, is the polarizing filter wheel. This is the same subcomponent in both the NIFI and the Wi-Fi. It was provided by NRL. You can hear in the bottom, this is the motor and actuator, which includes a motor and a resolver. And then the top we have the 5-position wheel installed in the NIFI instrument. The wheel has the 3 polarizing positions at -60, 0, and 60 degrees. These are linear nanowire lithographic polarizers, which have excellent throughput and excellent contrast. And then we have a clear filter, which is the same glass as the polarizers. And then we have a blank, which is just a piece of metal, not really a good filter, so that we can block off the CCD and perform testing flat field, and there's also an LED in the camera, so we can illuminate the CCD with just the LED light. And then there's the common punch camera. If you're familiar with the stereo instruments, this will be very familiar to you. It was created by our friends at RAL, so it's very similar, except this, instead of, it's operated without a shutter, and it is a charge transfer CCD, so it's actually rectangular, and then the image is moved over to the blotted out, the covered area here and then read out. The camera and the camera electronics are this identical between the WIFIs and the NIFIs. And this here is our little friends of Nick Waltham at the top here, taken with the punch camera in their little masks. So, all right. So once we put all of those pieces together, we take the instrument into environmental testing. So Craig showed you some of the environmental testing at the spacecraft level. Before it goes to the spacecraft level, we do environmental testing at the instrument level. And the environmental testing that we did at NRL was vibration testing and thermal vacuum testing. First, we do the vibration testing, and that simulates the vibrations that we expect to see at launch in each one of the axes. So you can see the instrument on the shaker table in the different orientations here in the 3 pictures. And then once we're done with that, we move it into the thermal vacuum chamber, and this simulates the temperatures that we're going to see on orbit in vacuum. And of course, we can then operate the instrument and test it, such as the door deployment in vacuum at temperature. So this is the NIFI instrument actually coming out of the thermal vacuum chamber, and we were actually in thermal vacuum at this time last year. So now we're in thermal vacuum at the spacecraft level for this meeting, so seems very circular. Before and after we do all of this environmental testing, we do our optical testing. We call this Scotch testing because that's the name of the chamber that we use. The Scotch chamber is, you can see here, and so we do a full set of optical testing in vacuum and at operational temperatures to test the optical performance of the instrument with a solar simulator, which has a 10-meter collimator in front of it. And then we do that before and after our environmental testing, both to make sure that we're meeting our requirements and also to show that nothing changed when we subjected it to the environment that we're expecting to see in space. After we completed all of our work at NRL, we then delivered the instrument to SWIRI in San Antonio. You might wonder, how do you ship a space instrument across the United States? Well, you just call FedEx and you get a FedEx truck. We were the only thing in the FedEx truck. It was, but we just shipped it FedEx. You can see it arriving at San Antonio at the loading dock here in the top left instrument, and then top left, and then you can, the bottom left image is the unboxing of the instrument in San Antonio. So this is when we opened it up, and you can see how we shipped it in the shipping container. And then here on the right, we have the NIFI and Punch teams thumbs up at the delivery. I am the hobbit-sized person in the middle there, with the NIFI instrument in the background. So, and then as Craig already mentioned, we were integrated onto the Sponge spacecraft. And the Punch spacecraft with the NIFI instrument has successfully completed vibration, shock, and acoustics testing, and the Punch NIFI spacecraft is in thermal vacuum testing right now. So these are images of it integrated onto the spacecraft and testing the door operations once it's integrated onto the spacecraft as well. So in summary, NIFI meets the driving requirements and the science objectives for Punch. NIFI was successfully delivered to the Punch mission for spacecraft integration and has started environmental testing. And NIFI is currently in spacecraft TVAC, so knock on wood. Thank you.
Thank you so much, Robin. All right, moving on. Our next speaker is Glenn Laurent, and he is going to be talking about the wide field imagers, or WFI, instruments on the Punch mission.
While Glenn's getting up there, I forgot to mention one thing about LIDO. Since we're holding the question towards the end, if it's not obvious which talk we're asking a question about, please put that in your question.
All right, thank you, everybody. My name is Glenn Laurent, the instrument lead on the 3 wide field imagers, or WFIs, aboard Punch. My goal is to give you a very brief summary of the design of WIFI and then jump right into the performance and delivery of all three instruments. As Craig and Robin mentioned, WIFI complements NIFI by providing a complete view of the corona through the solar wind transition. The WIFI field of view is from 5 to 45 degrees, which has 3 degrees of overlap with the NIFI instrument, as well as the WIFI between the WIFI instruments. Both WIFI and NIFI provide polarized images using a rotating filter wheel. The 3 WIFI observatories are equally spaced 120 degrees around the Earth, and as they sweep over full coverage at 32 minutes cadence, with individual observations at 4 minutes. So here's a cutaway of the WIFI instrument. From the life of the photon, the first thing we see is the solar baffle, which attenuates the stray light from the 3 primary sources, namely the sun, the earth, and the moon. Light then goes through a conical baffle, goes through a polarizing filter wheel, which is a common element between WIFI and NIFI, then goes through a multi-element optical lens assembly, and then finally comes to a focus on a CCD. So this is the actual WIFI 3 instrument undergoing final inspection, fully packaged up, including our MLI installation. So the image on the left there, you can see these dark light traps. So if you are, say, the moon, that is where the photons go to die. Robin showed this, but this is the WIFI functional block diagram. NIFI's there is grayed out on the top with WIFI on the bottom. Number of common elements between the 2 instruments, namely in purple there, including the filter wheel, the camera, the back-end electronics, as well as multiple heater zones. So WIFI meets all of its level 2 requirements, which have essentially remained unchanged since CDR, and that defines our passband, field of view, and resolution. All of those are met. I won't dig into the level 3, 4, and 5 requirements, but we have met all of those as well. So WIFI ConOps, as Robin has mentioned, is common between WIFI and NIFI, with 2 sets of 3 polarized images with a clear filter in the middle. The only difference between WIFI and NIFI is that due to the extreme difference in dynamic range, NIFI takes 3 different images, whereas WIFI takes a single image at each of those polarized locations. So as far as the WIFI instrument status, all 3 WIFIs have undergone a suite of tests, including focus at a number of different times. Went through environmental testing, including VIBE and TVAC. Also, WIFI 1 went through Scotch testing in order to validate the design. And then all 3 WIFIs went through, again, optical performance checks at each level before VIBE, after VIBE, TVAC, Scotch, passed all of its requirements there. All 3 WIFIs have undergone their pre-ship review and submitted their end item data package and have all been delivered. That should be 124, not 123 for WIFI 1, but they've been delivered in January, March, and the last one in last month. So as far as the schedule here, I just wanted to show, yeah, we had juggling all 3 WIFIs here in various stages of development, and we're proud to say that we were able to successfully deliver all 3 of those. So we encountered 2 main design challenges. Really the only 2 changes between the original conception and the final delivery. 2 changes due to incidents in VIBE was the first one was the door latch assembly. The door didn't quite open after VIBE. And that some design changes were done there, including on the right there is a close-up of the latch where we introduced, transitioned from a cup-cone interface to a ball cup interface in order to minimize the stiction between those elements, as well as a kickoff spring in order to get everything moving. A second design change was the optical lens assembly, shown here on the left. Due to some shifting of the optical lenses themselves, we introduced radial holes in order to stake each of the individual elements. All of those went through individual component testing in order to verify focus, and then again at the instrument level as well. So environmental testing, after assembly, all 3 WIFIs went through vibration testing. Here it is at our in-house facility here in San Antonio, in all 3 axes, bagged and purged. in order to maintain cleanliness. And then was Vibe in 3 axes according to GEV's 14.1 Gs RMS, so a lot of shaking going on. And for those who are interested, this is kind of a snapshot of the frequency response of Wi-Fi post-Vibe. You can't see it, but there's actually, all the curves overlap both pre and post-Vibe, which is good, which means nothing shifted, and meeting our first mode requirement as well. After Vibe, we took Wi-Fi out, brought it back into the clean room, and did a door functional test, which went swimmingly well. I don't have a video like Robin, but the door opened, and the door's been tested multiple times, both in thermal vac as well as at atmosphere. So post-Vibe, and indeed many times, we want to check the focus of the instrument as well as other characteristics. What you see here on the left is we use a point source, and we put that in several places in the field of view. So these are just postage stamps of our focus, showing that the spots meet our requirements. The plot there in the middle shows in the green there that our point spread function fits all meet our 3 arc minute requirement. And then we also have several points even beyond that in our field of beyond our required field of view, which also meet requirements, which is a bonus area that we'll be using in flight. Near the edge of the field of view, as designed, is one of the characteristics of the optical lens assembly. We do suffer from some coma, but we've been working closely with Marcus Hughes in the SOC, who's done point source regularization in order to correct for this well-understood coma, and then we can effectively correct that to essentially Nyquist sampled spot, which is great. In addition to focus, we also check our vignetting, where we look at a blank screen in the lab and then perform fits on that, showing our vignetting function both at our inner field of view, which is defined by that front, we peek over the front of the baffle, so we are somewhat vignetted there in the front, and then as well as the optical lens assembly radially. So this just shows those vignetting curves and that we do meet our requirements. In addition to the vignetting, we also do onboard LED testing. We have 2 LEDs on board. We can run those simultaneously or one or the other. And then from multiple different pulses of those LEDs, we can build up a flat field, pixel by pixel flat field, which allows us to, in flight, monitor both obscured pixels as well as performance of degradation of the CCD in flight. And one of the bonuses of the LED tests is, again, the obscured pixels. Due to either dead pixels or any debris that's on the CCD. The histogram there on the left just shows a relatively small number of particulates. We meet our requirement by 2 orders of magnitude, which is good. And then finally, we validate the polarizing filter wheel, making sure that each of the 3 filters are indeed separated by 60 degrees within requirements, and they are, which is good. After Vibe and follow-up optical testing, then each Wi-Fi went into TVAC. Here is Wi-Fi inside the DS8 chamber in San Antonio. We test 7 of the 8 cycles horizontally for thermal vac, and then we go vertical for a final door test for a final cold cycle. And then we have a monitoring equipment which allows us to monitor all of our thermals, which is the strip chart plot there in the center. And then we're working with the mock to get similar the data strips real time in flight. And this is just our temperature profiles for TVAC, just showing each of the 8 cycles there where we go hot and cold. Nothing, no surprises here. Everything went quite well. We were able to validate our thermal models, which allows us to do our in-flight predicts to make sure we're within our thermal requirements. And again, as I mentioned, we test our focus many times throughout the test campaign, and this just shows both our pre-environmental, post-TVAC, and post-Vibe that our focus is not changing, which is a very good thing, and that we meet requirements across the board. And again, we are repeating these exact same tests at the observatory level to make sure that there's no changes. And for WIFI-1, in order to validate our stray light design, we brought the WIFI instrument to the Naval Research Laboratory, and as NIFI did, we put WIFI inside the Scotch chamber, which has a solar simulator on the end of it. It's a long vacuum chamber. Put the image of the sun onto the front of the baffle, and then look at the Fresnel scatter into our optics. While challenging and dominated by the stray light of the chamber, which is all the bright stuff in the right image, looking at our inner field of view, which is where in flight we expect to be the Fresnel scattering to be the worst, we meet the strict 10 to the minus 16 B sun requirement by 2 orders of magnitude, greater than 2 orders of magnitude, which is good, which validates our optical design. So coming out of the end of our test campaign, we had 133 level 3, 4, and 5 requirements for each of the WIFI instruments. All of those have been closed out and passed. We did have 2 waivers for some minor items, the reflectivity of the metering bracket and the solar shield position, but neither of those have any substantial impact on performance. So those waivers have been approved, and we were able to close out all of our level 3, 4, and 5 requirements. So moving on to the WIFI delivery, all 3 WIFIs have been successfully delivered to the observatory INT. Again, the year is wrong on that. WIFI 1 in January, WIFI 2 in March, and WIFI 3 in May. All 3 WIFIs are now bagged in Lumilloy and undergoing continuous gaseous nitrogen purge. You can see the roll cage, similar to what Craig mentioned. There's the WIFI instrument in the roll cage there on the bottom. And all of those are in various stages of observatory level INT. WIFI 1 has been integrated, undergone CPT testing, optical testing, vibe and door open testing. We are working through an issue with the solar array simulator and peak power tracker issue, so the observatory team is working on that, after which we will likely have to repeat a penalty vibe. And then after that, we'll be going into TVAC, hopefully shortly after NIFI comes out. WIFI 3, which piggybacked over WIFI 2 due to schedule issues, is currently in vibe. This meeting is important, otherwise I would be down in San Antonio supporting that. But from what I hear, everything is going well down there. So hopefully we'll be vibing the first axis either likely tomorrow. And then WIFI 2's final integration is underway. MLI is being installed, and that should be following into vibe within a few weeks. So with the delivery of the 3 WIFI instruments, our job is not done on the instrument team, so we are supporting the observatory team, including optical testing, ensuring our focus and vignetting is consistent with the instrument level results, and then supporting both vibe and TVAC, including the door open tests, and then looking at all of our functional and comprehensive performance test images, making sure those meet spec. We're also working closely with Marcus Hughes, who I think is giving the next talk, supporting the SOC instrument pipeline. In fact, one of our lead test support personnel on the instrument team has now joined the SOC, which allows us to have good synergy between both the instrument as well as the full observatory testing. And then we're also working with the MOC. I'm working with Jillian on that in order to ensure all of our real-time telemetry data is coming down so we can monitor things, our diagnostics and our housekeeping data. And then finally, if that's not enough, I'm trying to find time to write the instrument paper, so that is in development. Craig's looking at me because he knows that he wants to get that out. So that is being worked as well. So we hope to get that out within the next couple months. So again, I think that's it. Go punch. Craig stole my thunder, but again, that's first light from WIFI 1, showing the instrument team. And I think there was a question on the online, and that is on the clear filter and not a polarized image, although we do see some differences between each of the filters, even in the lab. So there are some polarized scatter coming from the lights and various stray lights coming. The exit signs are hard to cover up, so we try to block out everything. And the exit signs in the lab, which I'm always frustrated by, we cover those up, and it's a don't ask, don't tell kind of thing. So, and then just there on the right is the engineering WIFI. We did not take the flight WIFIs outside. The engineering WIFI just showing the Milky Way in the background, which was a fun shot while we were taking data with the engineering unit. So with that, thank you.
right, thank you, Glenn. Okay, and our final talk before we have our Q&A is going to be Marcus Hughes, who's going to be talking about the Punch Science Operations Center, or the SOC. I'll give you 2 minutes.
Hi everyone, so I'm Marcus Hughes, I'm the SOC lead, and it's really exciting to hear from the NIFI and the WIFI team about all the progress they're making. We're really almost there. Clicking the wrong button, there we go. So this is the SOC team. So we have 7 of us right now working in the SOC. Derek Lamb, Dan Seaton, Ritesh Patel, Matt West, Chris Lauder, Sarah Kovac, and myself. And if you ever see any of us or run into us at this meeting or other meetings, we're happy to talk about the SOC. We want your feedback. We want your questions. We want anything that you can help us with. One thing to note is that Dan Seaton was the SOC lead, but I've taken over his role, and he's now a senior advisor helping us figure out how to do this complicated thing. So you've heard about WIFI and NIFI now. And what our job in the SOC to do is to take these images and combine them to make a data product that includes both NIFI and WIFI seamlessly. So we don't want to see edges where we combine images. We want to see everything nice and fluid. So there's an animation here, or a picture on the right, that you can see the edges very clearly. So you see the NIFI in the center, and then the 3 WIFIs around the edge. And there you can see the overlap that we've talked about so far. So we're creating these mosaics that combine all the input images. And to do that, we have a lot of complicated steps. So we're going to walk through this diagram and talk about the updates that the SOC has made about some of them. So at the top, you see the level, I think I have a pointer. Maybe.
Yep, just click and drag to your right.
Okay, I see it now. I saw it briefly, but it's fine. There we go. So there's the level 0 starting at the top left, and we move all the way across with the level 1 processing. So we'll walk through that and talk about the updates there. And then on the second row, we have level 1 to level 2, and level 2 to level 3. And these level 3 products are the products that you might want to use first for your science. Among them, we have them listed at the bottom. We have a wind speed plot, some clear mosaics and polarized mosaics, a NIFI view every 4 minutes, and then we have low noise mosaics and a NIFI view. So let's just walk through some levels. Let's zoom in a little bit. And we're going to note the status of each of these steps as we go. When I say completed in these diagrams, I want to put a little caveat that when we say completed, we have something that works, but we're still improving. So by the time launch comes, these algorithms may change some, but we have something in place that we could use at the moment. So we start with these level 0 raw frames that we construct from CCSDS packets from the mock. So there's a whole step of level processing that we're not showing here that happens first. And then we do a quartic fit calibration where we fix the nonlinearity of the instruments. We remove cosmic rays using an algorithm called Spike-Jones. And then we do destreaking. So as mentioned, the cameras are shutterless. So we have a streak that occurs as we read out the instruments. And so we use some linear algebra to reverse that streak and remove it from our images. So after that, so you see the destreaking continue. This is the overlap. We have stray light subtraction, so we build a stray light model, and we have point spread function deconvolution. And finally, we'll talk about the alignment that Craig alluded to earlier. Let's summarize some of the point spread function correction. So we talked about this some, I believe, the last Punch meeting. We have this pretty well under control now. We have a paper published that describes this if you'd like to look into that. But the way it works is we have observations on the left where in the top left of an image, this is a sample image from WIFI, you can observe the star has a tail that goes toward the center. And that tail is different depending on where you're at in the image. And if you think about mosaicing this now, we have overlap. So an overlapping region, the tail would go one way and the tail would go the other way in the other image, and it would just be a mess of tails if we tried to combine them. So part of the rationale is that we want to correct these tails. So we use an algorithm that's implemented in this package called regular SPSF, which is public and available through our GitHub at the moment, to correct this point spread function. One of the highlights of things that we've finished since the last Punch meeting is this image alignment problem. So we have this package called Thuban, which is not yet released, but I was hoping to get it there by this time, but we don't want to rush things. But we have some performance results. So Thuban actually is a star that used to be the North Pole star during Egyptian times, so we're kind of going to play off things. It's a package to realign things. So we have a requirement that we know the pointing to 1/10 of a pixel. It's a hard requirement to meet, but we're meeting it. So I've constructed some synthetic data where we made star fields that would look like what we'd expect at the level of processing. And in those synthetic field images, we were getting 2/100ths of a pixel pointing knowledge, which is well beyond what we're required to do. But we were worried that maybe in real data there are details that would make that harder. Real data is always messier. So what we've done here is we've taken some High-2 images, and you can see in the bottom left where we're taking the High-2 images, figuring out the pointing to a high degree of accuracy and precision, and then we're reprojecting so that one star should stay in the center. So if we didn't know the WCS, the World Coordinate System, very well, that star would jump around. But since we do know it, you can see there's things that are happening in the image, and it's fuzzing a little bit, but the center of that star is not moving. So we have a good handle on the pointing now. At the same time that we have pointing, we can figure out the distortion. So the optical distortion of Wi-Fi will be considerable because it's a wide field imager. So stars won't be exactly where you might expect them to be. So this is a High-2 distortion that we've derived from these images. And it looks pretty realistic. We've also tested recovering the distortion with a known input. So let's move on to level 1 to level 2. So we start with these images that have been aligned and had those steps that are happening at the top. But now we have to resolve the polarization and identify where bright structures might be, so like aurora, so that we can flag them so we don't confuse you in your analysis. So you can see that there's an aurora here, or there's moon glow or something in our uncertainty layer that we're including with the data. And we also have to mosaic at this level. So we're taking that world coordinate system that we've refined in level 1 and combining and adding up the images to make this level 2 trefoil mosaic. So the polarization resolution we've talked about quite a bit. It's available through a package called SOPOLPy, Solar Polarization Resolution in Python. It takes an arbitrary input system, so we could take the MZP observations or the polarized observations we get from the Wi-Fi cameras, the NIFI camera, and convert them into polarized brightness or total brightness or Stokes vectors or whatever is useful for the science that you're processing. Along that processing, we realized that there's an issue where the Wi-Fi field of view is so large that the sampled polarization angle varies across the field of view. So we have to correct for that additional problem as well. So on the right here, you see a diagram of how the polarization angle varies across the field of view. And so we have a paper in prep that will describe this correction, and it'll be included in our software and included in the data products you receive. So finally, we go to the last step of processing, level 2 to level 3. So we have to subtract the F corona and subtract the star fields. So we've made progress on that as well. So when we improve the pointing, we get free progress on the star field removal. So if you were to look at this image, this movie that we had a month ago, you'd have seen a lot of artifacts. So what's going on here is we have a High-2 scene on the left, just a small movie. High-1, sorry. And on the right, we have a Starfield removed version. So we've used some code that Sam Ben-Kuten has prepared for Whisper. So we're having cross-mission development happening already. And so we model the star field, and then we subtract it off. And so you'll see that there are some artifacts that still remain. Like these bright stars have a little bit of bipolar subtraction where you're over-subtracting or under-subtracting. We think we have a handle on that's caused partially by an overly smooth distortion model and some other parameters that we can adjust. So by launch, we expect this to look much better, but it's already way better than it was a month ago. So that brings us to the conclusion of the pipeline. A lot of things are marked as completed here because we have in-place versions that'll work, but we're making progress to improve them even further. And there's a lot of things that aren't shown in this diagram, like how the pipeline works together and how it automates, and how we track uncertainty, for example. That's a challenge that we're working on right now to give you measurements of if you have a pixel value, what is it plus or minus in its uncertainty. The one thing that we've worked on is the automation system for the pipeline. So we use this package in Python called Prefect. So it's a general purpose data flow management package. So on the left, you can see a preview of, we ran a test where we created fake level 0 products. So you can see here, I don't know if you can read this in the back of the room, but it says create fake level 0. And then it ran through the pipeline to see if everything performed correctly. So there should be green dots here when a processing flow completes successfully. There's a couple red in there mixed in that we did intentionally, and a couple yellow, meaning that it's scheduled and hasn't run yet. But we have a comprehensive way of monitoring the pipeline to know if everything is running properly, and we can intervene otherwise. On the right, we realized that we didn't have tracking for the files themselves. So this left view tracks the processing flows, but we wanted to make sure the files themselves are being created properly. So we're improving this dashboard that tells you whether the file has been created and lets you have a quick view of what it looks like, so you can monitor, so we can monitor whether or not the files are being created properly. One thing I want to encourage you to do is to go to our GitHub. So you can scan this QR code right here, or you can go to the link at the top right. And this is where we're going to release all of our software. This is where we're releasing guides that help you use the data. This is where we're releasing example data that you can use right now. So if you go to the GitHub and you look at the top right, it says unfollow. But if you're new to the GitHub page for Punch, you'll have a follow button, and we encourage you to click that so that way you can see our updates and see our progress and see our code being released. Along the same lines, we have a discussions tab that we encourage you to use to discuss our products and discuss the software and ask questions. So you may have already heard we have some sample products that are available now. You can go to the Punch GitHub again to get them, or you can go to the Punch 5 repo in the GitHub. So this QR code will link you there. We have a lot of things left to do, but we're making great progress. So we need to improve the synthetic data, go all the way down to level 0. Our server that we're going to run all this code on is on its way here right now. Not here, but to the Sweary office. And so we will deploy that. We need to finish improving our Starfield model, complete our uncertainty propagation, include Starflow tracking algorithms, complete the development of Quick Punch products, so you'll hear about later, work on SunPy affiliation so the community is aware of our packages, and then create a great user guide so the community knows what we're doing and how to use it. So everything is coming along nicely. We're on track to finish. We have some synthetic data available. There'll be a couple more talks in this 2-day meeting about how to work with punch data and what the quick punch data will be. So to finish, I just want to say we want to work with you. We want to hear your feedback. And so please get in touch. You can use GitHub as a discussion board or an issue tracker. And if you have a private inquiry, we encourage you to also use punch_sock@swear.org, and we'll answer it. But we would like you to use GitHub because everything is public there, and so other people can benefit from the questions and answers that are created there. So thank you. That is all I had to share about the SOC today.
Great, thank you, Marcus. That was really, really impressive what you guys have been doing. So could I have all of the speakers from the first session come up here? The Slido questions, I'll run the mic so you don't all have to jump up all the time. And let's take it from there.
Can you guys put up the questions? Wonderful. So the top question that I see up there is from Nikki Vile, and I believe that question is for Sarah, but
Oh, well, no, I think punch 6, it's punch, or I think it's Craig question.
oh, okay, good. All right.
There we go. You see, push to talk. Sarah and I are working on where it will be. It'll be in Southern California. We're going to try and hold it at Vandenberg, but we want to see if the logistics will work out. If we do go to Vandenberg, we'll be close to the vehicle, which is pretty cool. But on the other hand, there are some restrictions involving getting people onto Vandenberg. I do intend for the meeting to be open to everyone who can come to a regular punch meeting.
And the intention is to have it coincide with the launch date, which is sometime in the spring. We don't have more specific right now, so it'll be earlier. It'll be a little less than a year from now. It won't be a summer meeting, right, Craig?
I am not able to announce a launch date for Punch at this time.
Okay, like you said. Stay tuned.
Great. Next question is from Dave Webb. And over there.
So I just ask it again. For Wi-Fi, how does the lunar baffle work? I see a couple replies. I wonder, it says there's no pointing on these experiments. The moon moves around, you know, does the baffle move around? Seems a little bit hard to understand geometrically.
Yeah, the Wi-Fi lunar baffle is a two-stage, think of a double doggy cone of shame, and it is fixed and will reject, and the knife edges define both the field of view and field of regard, and between, say, the first and third quarter of the lunar phases, we'll be able to reject lunar light. There will be times during just before and after new moon where we will have some spoiled images.
Thanks.
That was well done. Sarah asked, was the team polarized? Glenn answered that. You guys get along great. I don't know why she would even think that.
We have a unified team that is unpolarized.
Yeah. And I think you answered the real question there, which was how you test for the polarized. This was a clear image, but
yeah, that's right. So this was a clear image, but we do test all of the polarized filters, both with the point sources. We do lab imaging, and then the filter wheel. When we're doing the filter wheel polarization tests themselves, we use a polarized source using an integrating sphere, and then rotate the filter wheel, looking at the maximum, fit that curve, and that we know the orientation of each of the filters.
Great. Alberto, next question.
Hi, thanks for the presentations. I guess my question was then addressed also by Marcus and Glenn. So when you show us this beautiful composed image with the roll and all the processing you guys will be doing, what will be the cadence for those full composed images? Is that 4 minutes or 8 minutes? Because you mentioned 2 different cadences.
So you'll produce a trefoil image every 4 minutes, but you don't get full coverage all the way out to plus or minus 45 degrees more frequently than once every 30 minutes.
And there's also an 8-minute cadence for the clear products that happen, because the clear filter, as you saw in the ConOps, it happens in the middle of the sequence. And so you'll have another way to measure total brightness through the clear.
Great. Next question. I think this has been answered, but Michael, why don't you go ahead and ask it anyways for the audience?
Yes, thanks. Yeah, I think, Craig, you answered in the chat, but Craig, Robin, I see the inner field of view for NIFI stated as both 5 degrees, 5-hour sun, 6-hour sun. Can you clarify these numbers and exactly where it stands?
Well, it's not 5 degrees. The geometric cutoff of the occulter is at 5.75, so that just means 0 light. We are meeting the requirement at 6. And if you're used to using the, around the occulter, you should have some signal inside of 6-hour sun, but we're not promising the field of view until you get to 6-hour sun.
Okay, so in one of the presentations it said 5.4.
I think that was an error.
There's some nomenclature issues to think about, which is within the project, as Robin knows, we've defined our sun to be 15 arc minutes, but a more common number that people use is 16. And so sometimes you see inconsistencies related to that.
Right, so because the Earth's orbit is not perfectly circular, and because our sun is a ratio, you have actually your our sun changes over the course of the orbit, so.
Nicely done, Michael. All right, our next question is from Sam.
Hi, I think Craig also kind of answered in the chat, but maybe just to expand, to confirm, is the NFI spacecraft in the same orbit and just at a different phase? And then is it kind of just drifting relative to the 3 WIFIs that are 120 degrees apart?
So yes, we are in the same orbit. We don't have any, the WIFIs are orbit kept. They have to be spaced in the orbit to keep their field of view. We don't have any, don't have to be aligned with respect to the other spacecraft in the orbit. So we are in the same orbit, but we don't have any orbit keeping that we are required to do because we're looking at the sun center the entire time. So it's a matter of more of how we're deployed when we initially launch, where it will be.
Great, thank you. All right, Nikki.
And I was just going to comment that for people online, you can also ask questions if you go to the Slido, and also people can upvote questions.
Yeah, Marcus, can you say more, please, about the high altitude aurora processing? Are you just saying, yep, that image has aurora in it, and putting that image off to the side, or are you actually going to pick out the piece of the image that has auroral pixels in it and isolate those?
Yeah, so we have a voting algorithm that is developed originally by Craig that will look at pixel by pixel and see how the pixel values change over time. So if there's a sudden spike because of a high altitude aurora, it gets flagged as a transient bright structure. And so then that gets input into our uncertainty layer as a high uncertainty. It's known that it's not what we want to observe necessarily with punch. So as we move in the processing levels, high uncertainty features are weighted less when we're making mosaics. So we flag them first on a pixel by pixel level, and then when we make mosaics, those aurora contributions are less because of that flagging. Does that answer everything, or? Yeah.
Nikki's asking, I mean, if it's one person's noise is another person's data, right? And so if you are trying to do this, how would someone query and collect specifically the aurora images?
Right, so this is a level 1 to level 2 processing step. So you would have to look at those. Level 1 products would still have the aurora included. And you could run a version of the pipeline, I guess, to get just that flagging or somehow work backward. We're not planning to create an aurora product at the moment. It is great to note that like one person's discard is a great treasure. So like the star field, for example, we're creating a star field map. That would be helpful. But the aurora will not be tracked in a separate product, but you could run a version of the pipeline to recover that.
Right, great. Next question is from Bernie.
No, I think he wanted to comment.
I just had a comment. The aurora doesn't have to be spiky. It's pretty much a general place in the sky that's bright, and it may last for several hours. So
I'll comment on that, which is
deal with that.
Because we're in orbit, it's spiky in time because of the perspective effects. So when we did the I guess a long time ago now in the CSR, we did an analysis where we talked about we'll never see aurora in the same place in 2 4-minute sequences.
Great. All right. Next question. Next question is from Michael Kirk again.
Hey, me again. For the SOC, did you consider running a cloud solution? I mean, it sounds like you could containerize the process pretty easily, run it in AWS or something like that. What made you decide to run it on a rack-mounted server instead?
So I will say that decision was made before I started working on the SOC, but I want to point out, so Dan is going to make a comment, but I want to point out that because we're using Prefect and the way we have things set up, we could actually transition in the future, I believe, without too much trouble to a cloud system. So there's opportunity, but I'll let Dan speak to the original question.
Yeah, we didn't consider running it in the cloud. Egress is a big question. We have a huge amount of data. We didn't have a really clear solution to get the data out of the cloud and serve it to the community. I think having been through this whole process now, if I were going to go back in time and do things differently, I would probably say we think we know how to do it in the cloud, and the cloud offers a lot of benefits that we don't have with local hardware. So maybe for a future mission, that's something we'd talk about. But between security requirements and figuring out egress and just, having spec'd this stuff a long time ago when the cloud was not as robust a solution, it wasn't something that was in the mix. But it's a good question, and I think Marcus' point is well taken, that this thing could move to any hardware and you wouldn't know the difference anymore. And I think that's an argument for being able to go to the cloud. So.
The PI is also jumpy about running things on other people's computers.
Great. Our next question is from John Keller. Nice to see you, John.
You, Barb. It's been a long time since Hawthorne House. So, naive question, but the mirror that's rejecting the solar light back out the baffle, is there ever any chances that would ever not be pointing the right direction and cause issues? I don't actually know much about occulters. I apologize.
Actually, so we did look into this. There are very non-operational angles that the spacecraft could get themselves into, and that would put the image of the sun onto the baffles. That is something, a failure case that we did investigate, and it would heat the baffles. Presumably, we would also, be in it would be a very bad situation if that were the case, and the spacecraft recovery would start at that point, and we would be spinning, so it wouldn't be a consistent input of heat. But that is something that we did investigate, is sunlight going to places we don't want it or expect it to be in the spacecraft.
From a CCD perspective, the CCD itself can handle direct solar imaging without any damage.
Great. And now we got a good question from Don Kolinsky. Why does NIFI have a monster mouth, right? Yeah, there's Don.
Well, if you look at any other if you look at all the other coronagraphs, this is actually consistent across all coronagraphs. Anytime you have a edge that gets light onto it, you have diffraction. Unfortunately, that's just the way photons work. So when we have that toothed mouth, the angle of those teeth are highly in such a way that we are deflecting the light out of the image. So we are My optical engineer tells me that it's very, very good. So we're reducing the scatter into the field of view by having those teeth in that front aperture.
Strategy. Let's see. The next question, Shahida. Let's see. Shahida's over here.
I was just curious. I'm not sure whether it's the right question or not. So for testing, is it possible or advisable to take images from the ground before the launch? Not directly on the sun, but off from the sun. Is it possible? I know the aperture will be much smaller.
We did something like that just to prove that we could take images from below the Van Allen belts and still see the heliosphere. But it turns out it's really challenging to do that from the ground. Air glow and lots of other effects get in the way.
All right, great. Now we have a question from Joan. Oh.
Thank you. Is the spacecraft jitter, is that controlled to 1/10 of a pixel or less? Because I know the polarization requirement is that 1/10 of a pixel.
Jitter is controlled at that level.
Cool. Oh, and here's Bill. Sarah's getting her exercise this morning.
Yeah, I was noticing that one of the presentations talked about the 2K by 2K CCDs, and then there was a mention of a 2K by 4K part of the CCD, and I was wondering, first of all, what's that about? What's the other half of the CCD for? And also, after all of these massagings that you do with the data, I guess at the SOC, ultimately, what's the resolution of the final product images?
I think I can take the first half of that at least. Because the punch cameras are shutterless, we operate in something called a pseudo-frame transfer mode, where half of that 2K by 4K chip has a aluminum store shield that effectively blocks all light. And so we image using half of that 2K by 2K, and then very quickly, in I think about 80 milliseconds, we can move the image from the imaging side to the store shield side, and then take our sweet time reading it out, which takes about 1.5 seconds, I think, in order to get the actual image downlinked. Yes, that's right. That's right.
So is that transfer done digitally, I guess?
Yes, that's correct.
It's analog. It's a latent virtual image that's just an amount of charge in each pixel.
Standard bucket brigade of a charge transfer. And then on the second half of your question, the native resolution of Wi-Fi is 90 arc seconds per pixel, but I think Marcus can speak to the final resolution of the combined data product.
I'm trying to remember the actual number. Do you remember it, Craig?
Let's see, excuse me, we want 3 pixels per resolution element. So something like 4.5 arc minutes. $270 arc seconds. What are you asking? Got it. About, what is that,
Can you
about
repeat the
750? The question is how many pieces of information across the image? And it's 1/3 of the pixel count, so about 700.
But then the trefoil, the full trefoil image from the science operate data product is that much larger, right? Because it has 3 Wi-Fis and a
Yeah, the product that you'll get for will be 4K by 4K because we combine everything and yeah.
Right, and Joan, would you mind also combining your question with Deepankar's? Oh, okay. The last one. Yes.
I'm sorry, where? I'm sorry about that. Well, his is pointing. I was wondering if you're also going to be removing solar energetic particle hits. You're removing cosmic rays, which is very cool.
Joan had 2 questions. She asked the other one. So
we can't tell the difference, so they all get hit by the same filter.
Same filter. Okay. I'll ask Deepankar's. So Deepankar's online, I believe. Don't see him in the room. And he's asking, what is the pointing accuracies of each spacecraft if the three WFIs have different pointing stabilities? How do you take care of that?
So in the pipeline, we have that alignment step. It doesn't impact the pointing of the satellites, but allows us to know very confidently where we're looking, so we can combine that in the software, and we don't have a problem then.
Great. All right. Next question is from Chris.
Hi. I don't know if I missed this in the talk, but how long will it actually take Punch to complete a full orbit? And is it different depending on each spacecraft, or is it just the same?
96 minutes, I believe, given our nominal orbital altitude.
NIFI will be slightly different, a few seconds more or less. I guess less to start with, just because we have to start it at a slightly lower orbit so that it decays at the same rate as WFI, which is a lighter spacecraft.
Great. All right. The first two questions have already been answered.
Yeah, so we can retire the Bill Matthews and Don Kalinsky one?
Right,
Yes.
right. Let's see, and then we have, okay, probably a comment from Bernie, and then oh, you have an actual question? Good for you. Bernie Bernie's done this for so long that often, Bernie has insightful comments. So.
Well, I had a question for Craig. What do you do with the thousands of artificial satellites you'll see?
So the question is, what do we do with the thousands of artificial satellites we'll see? The same thing we do with asteroids and everything else. We'll try and remove it with the Starfield or the spike removal algorithm. So.
And we should say, but you still keep that data. It's not removed and just chucked away. You remove it as part of the product, but you still keep that data that's removed, correct?
Absolutely. In fact, it's worth pointing out, Marcus may want to elaborate, but we keep the level 1 data and the level 0 data. So if anybody wants to do something else with them, they can. The level 3 excuse me, are heavily processed. Lots of things are removed from them. But if you want to go back and be crazy and really muck around in the data, you can.
And because our pipeline will be open, all the software will be there. You can just run it, and we'll have a user guide that describes how to modify the pipeline, so you could plug in your own modules to do different processing. So if you want to look for those aurora, or you want to look just at satellites, you can do that.
You have another question? Ada? Oh, okay.
Oh, that's the same.
Oh, that is, okay. I'm sorry. Thor, where's Thor? Over. Oh, there you go. Great. Thor has a question?
Yeah, I was just wondering if the NIFI is locked to a specific WFI in its rotation, or does it have its own independent rotation parameter since they're both rotating?
Yeah, so the rotation is due to the orbit around the Earth. So what we do is the orbital is designed to always keep the radiator looking at deep space and the bottom of the spacecraft looking at the Earth. That way we keep the hot side hot and the cold side cold. And so the rotation is it will be part of this 96-degree orbit, so we'll be out of sync with any of the other instruments, so that's where the SOC comes in to align everything back together.
To add, there's a common theme here, which is we've worked very, very hard to make the photometric measurements independent of the pixel grid. So the detector pixel grid should, if everything goes well, be irrelevant to the photometric data that we're producing.
Great. And then we have one more remaining question up here from Heather.
Yeah, okay, it's on. Like some things are being removed from the prime data set, like the star field and the aurora. Could you guys just put those in separate files and say, this is what we removed from the star for the stars, and this is what we removed for the aurora? Is that easy to do?
So we are keeping the star field as a separate product that you can then use, because that's really interesting for other science. The F corona is also subtracted off and kept in a file so it can be accessed. The Aurora, I don't think we were making a product for, but you can, as we mentioned, recover it in the pipeline.
And I think Punch is required to keep the original data.
Yes, all the original data will be available, level 0, level 1. Look at the level 3 products as well, but all the steps will be documented.
Right, but I think he's saying that there's going to be actually things subtracted out useful of their own. One person's noise is another person's data.
And it sounds like, you know, maybe a small working team to work on the auroral problem could be a nice thing to have, because this is even if it's not detected, you know exactly when you're with Aurora, and so it could be a good product that at least or a tag on the data that could be useful. Let's see. Does the panel have any questions or any additional comments? And also, and then we have Dan Seaton.
Is this on? Can you hear me? Can I just comment on the Aurora thing? I think the way that the pipeline is set up right now, it's really hard to make a product that would track that stuff. It's not configured that way. So Barbara, I think it's a really good suggestion to convene a working group, and we can make the software available, and I think a clever person could customize the way that we're running the pipeline so that the Aurora stuff would be preserved and everything else would be thrown out. But like, I think as things are right now, like the Starfield, the F Corona, those are products we can make. Those are straightforward to make and store. The Aurora stuff is much more complicated to get at that information. It's not in a common projection, and there's a lot of work. But I would love to have people talk to Marcus and me about building some specialized software that would preserve that information if they have a clever idea for how to do it.
That sounds like a great thing to do after we meet our level 2s.
Yeah, well, I mean, I'm happy to share the code now and let people get to work on it. But I think the SOC is pretty flat out. Heather says somebody could do a guest investigator on it. That'd be a great idea.
A quick public engagement question. What are the estimates on the brightness of any one Punch observatory? Would it be visible to the naked eye for every human at every sunrise and every sunset? Or is that just not even a thing because it's so small?
I haven't actually done the calculation, but I suspect you'll be able to see it if you know where to look. It won't be something that's obvious.
And as an amateur astronomer, I've been bugging Craig about that for months now. He's not giving me a solid answer.
And with a constellation, it seems probable that at any given sunrise and sunset, the entire global community could be alerted to that presence, possibly. Something to think about.
Yeah, there's a tracking website called Heavens Above, which has a lot of amateur satellites. I'd love to get it in there if at all possible. Yeah.
All right. Well, Sarah says we're perfectly happy ending a little early. Get to the break. We do have a lot of excellent posters out there, and
we're 1 minute early, just to be clear.
Okay.
So we have until 10:30 the break, and we'll reconvene here.
I want to thank the instrument team leads and
Oh,
the SOC
let's thank
lead.
our speakers. Oh my goodness.
Okay, guys, let's take our seats and get started. So this session will have 4 invited talks, starting with a talk titled Celebrating Punch Outreach by Sherilyn Morrow, who's our education
bouncing around as if I'm fine. Well, thank you. It's a really honor. It's always an honor to embed this little outreach flavor into our scientific research environment of this meeting. So thank you again for including us. Celebrating, because we have much to celebrate, there's much more to come, yet we have also accomplished a lot. So we are both in this mode of celebrating and also looking ahead to what is it we're going to leave behind for the community. You know, Punch, well, it doesn't sound like it's going anytime soon. We're coming up on a launch, right? And so we want to be a part of that in coordination with the Heliophysics Communication Group. As well as leveraging from other partnerships. I'd love to just recognize those in the room currently. We like to come and rub elbows with you. Not our entire team is here, but there are some representatives in the back corner, some who've been with us for a long time. If you could stand up, please. I would love to. They're new and old. John Keller there, and Thor Metzinger, and Brian Meyer. I did it, okay. And Sam, he's a new video editor for us, working with Fisk Planetarium, which is where Thor and John Keller are. And then we have Dr. Sandlin Buxner, who is our evaluator out of the Planetary Science Institute. We have Jason Trump from the Clark Planetarium in Salt Lake City. He is our program manager and a brand new art science consultant who spent time as an artist in residence at the Laboratory for Atmospheric and Space. Excited about her collaboration with us. She's a new SWERI consultant coming on board. This is Alexandra Lockhart. So, yes, collaborators, we're all about, I just met the Globe coordinator here, we're all about thinking about mutual synergy and leverage with other entities. Michael Kirk presented in our annual retreat session. He is the director of the Heliophysics Education Activation Team at Goddard Space Flight Center. I guess everybody knows you, Michael, is that right? All right, well, you can, and we also have Doug Duncan here, who is the PI of he's got many hats, of course, but he's the principal investigator of a NASA-funded project in the science activation called Science Through Shadows. And he and John are leaders of that program, and we expect to be doing a lot of good business with them in regards to the development of planetarium dome films in the coming weeks. So we have a really nice, tight coordination with them, and we're glad that you're here with that hat on as well. All right. So, how many knew that it was solstice time? Good. Please don't make this conflict. Again, I want to be at Chaco Canyon, but I also want to be here with passion, both places. And our whole education and outreach program is about weaving the ancient and modern ways of being present for sun watching. And so, happy solstice. I would otherwise be here. But I just got a phone call saying that the Navajo people, some of them, are blocking the road into Chaco this morning. And so that will be an interesting unfolding as to whether I could have even gotten in if I had gone. This is a great Kiva and Chaco Canyon, astronomical marvel of the world, aligned to modern precision, to the cardinal directions, and also to solar and lunar cycles. That white arrow in the lower left, if you stand there, you can look out at this horizon. This is the photography of Duke Johnson, the director of Clark Planetarium, a consummate photographer who's been gathering our resources in Chaco for our larger film. Notice you need to start defining where the sun rises on your birthday. So this is the beginning of that inquiry. There will be no answers. We have this poster out in the lobby, and I invite all of you to work to determine that. It's not as easy as you may think, we found out at AGU. So the northeast, you see how that door that's circled in red, the rising sunlight comes through that door, and on these days, you know, we have a specific time when solstice occurs, except in the ancient world it was 5 days where the sun rose in about the same spot right? So this whole time period, you can see the sun rising, solstice, sun stands still. As the sun rises, this light square, that doorway, you see that dashed line, whoops, that dashed line there. I guess I could do this. This dashed line, this is that doorway that was circled in red on the previous slide, and a light box comes down into a particular niche. These days, you can go there and observe this yourself. We try to teach young ones and old ones and all ages about why, what's the rationale, why does the sun rise at different times, at different times of the year. These different trajectories, you're all familiar with the amount of daylight hours being less in the winter, and wait, okay, I gotta point more directly, don't I? Woo! The higher trajectory in the summer, which is where we are. Our ancestors used these as horizon calendars to track time. And we can still enjoy this phenomenon today, even with young Girl Scouts there on the lower left. If we really got, okay, where's east, right? East is that way. Go inside, that way. East is that way. So with the girls, we can actually track the sun, low in the winter, high in the summer. And they could get this activity, right? Now, again, where does the sun rise on your birthday? See if you can. At AGU, we found out that 80% of the scientists with whom I engaged could not successfully do this activity at the NASA booth and at our poster. This poster will also be presented to you out there. So I encourage you to engage. This is not only little kid stuff. It turns out that we're not training our leading edge solar physicists in how this works. And it's a worthy thing in the spirit of our ancient and modern sun watching theme for the outreach effort. Our mission scientist is a great ally for this idea and has invited our co-Is and science team to participate in a renaissance among NASA sun watchers like yourselves, reminding us of this lost art and science of tracking and predicting the solar cycle. This connects with the magnetic activity cycle educationally. Our ancestors learned to live well and in harmony with a seasonal cycle. Punch and other NASA heliophysics missions are teaching us to live in harmony with the sun's magnetic activity cycle, right? And so this notion of cycle, educationally and outreach, is very valuable. So I encourage you to find a consistent sun watching place and see how this plays out, and send your images to Dr. Weil. Our outreach theme is designed to make NASA heliophysics more personally and culturally relevant to a broader diversity of people. Heliophysics is a big word, and we found a great connection in the ancient sun watchers and contemporary sun watchers of the southwestern US. We portray NASA missions and NASA exploration of the sun as a natural extension of our age-old, humanity's age-old dedication to observing the rhythms and mysteries of the sun. Our logo is comprised of an ancient petroglyph that may be, and it may be plausibly interpreted as a total solar eclipse in 1097, the ancestral Puebloan rendering of that. These people built the kiva I showed you and carved this petroglyph about 1,000 years ago, and still consider, their descendants still live in the region and consider this a very important place for them. And notice that it's the blend of that petroglyph along with a Druckmiller et al. Kind of rendering, a more contemporary rendering of the corona. So the idea is for us to engage people in personal sun watching, whether more exotic for the eclipses or very simple, like the sun on your skin or the pinhole projections under the tree out here in the courtyard when you eat your lunch. Make those connections between what we do as NASA researchers as well as with the ancestral connections. And so bringing that together with whatever the nature of your solar observation. A big highlight, Craig and I presented in the Cotton Bowl for the total solar eclipse and came up with this Parker Solar Probe. If it's a mission to touch the sun, Punch is a mission about how the sun touches us. not only directly via the solar wind, but also in our hearts. Encourage you strongly to have a look at this 5-minute video, just 5 minutes out of your time. Clearly, Craig liked it with his testimonial there, but we got a lot of other testimonials from cultural partners and so on. This tells you about a site called Rock of the Sun that is the focus, it will be among the focuses of our planetarium film. Sophie Adams, we contracted with her. This is as good as a photograph as I've ever seen in the New York Times about people watching the sun. A young photographer up and coming, and she really did a great job for us. We were in Chaco for the annular eclipse, and here you see some fun times there. Celebrating, look at that annularity there on the left. In the plaza of Pueblo Bonito, a young Anis, the daughter of our evaluator, Sanlin, beautiful image showing off how well this projector works. Please get some. Take as many as you like that could support your outreach efforts out there on the tables all day and this evening especially. Craig asked me to light some kids up. There's one. We got one on film, right? Make an outreach program that lights up some kids. So you see at the top we have our evaluators. Here's where we sent projectors or were ordered from our printer. Look at the bottom with our dissemination partners. Wow, we blasted it out there. It's a huge amplifying effect. And Nikki on national television holding up our projector on several national news programs. This is a game changer product, this one. Nobody will ever make a pinhole projector without 3 different shaped holes. Again, I'm pretty convinced, right? I won't spend too much time here. The yellow highlighted are our major planetarium and science center partners. Their partners become our partners, and that is a very powerful way to go about being a collaborative. We are leveraging the strengths of each of these institutions to make goodies in a stone and soup fashion for all of us. Our native partners are a really important part of this. We collaborate with historically marginalized populations, not to just do things that are good for them, but to collaborate and develop things that are beneficial to everyone. So these dissemination partners are some of the ones in play. I would also list Kate 2024 now as another dissemination partner after Sarah Kovac's connection with us during our annular retreat. You see, annual retreat that we had earlier this week. So there's a picture from that annual retreat. One of our big mottos is that lemons, and they do happen, we know, on any creative effort, get turned to lemonade. That is our way of being. These are some of our other partners: Native American, Spanish-speaking people, blind and low vision learners, and girls in STEM. Thank you to those of you who have chosen to be public role models. It's not for everyone, we accept that, but we do appreciate those of you who are doing that. So 7-year-old Christine is a girl from Pueblo of Acoma who taught us that her mother and father and grandmother also want to fill out their punch team card, right? So we have a template that you can become a member of the punch team. Flashing through some of our Girl Scouts, we just delivered a draft patch for ancient and modern sun watching. Our mission scientist is a co-troop leader. We're showing off our women leaders in science. We are also developing new activities, become a sun watcher with all of your senses. We're also getting some hardware in there, rotating your polarized glasses. I encourage you to go on a scavenger hunt in this building and outside. Start seeing what's polarized. Polarized light is everywhere in your environment, including out there off the screen. And so it's really fun to detect that. We're trying to bring polarization to the astronomy education community in a more a better way. Also, we got to unpack this logo with coronal loops and our petroglyph. Annie Malanashenko, is she in the room? No. Anyway, we are going to have some hands-on tactile activities to activate the coronal loops. Also, Heather Elliott, a dancer, came to a Girl Scout patch earning event prototyping in February of 2024. You see the double CME launch over on the right with the scars. Alexandra Lockhart is over in the corner, and you'll hear more from her this evening. She's going to show her video interpreting heliophysics. Beautiful dancer doing public programs. Strongly encourage you to go to these wet drag and drop fill in the blank activities. We just finished these 3. They're a little more advanced in contact, but you're participating in dragging and dropping vocabulary words and gaming it. I want to call out Don Kolinsky, our web developer especially, who really has debugged this with us incredibly well. We go on to conferences, the American Association of Physics Teachers. Again, we have an indoor demonstration that you'll see this evening for the pinhole projection game changer, not just for eclipses. It's for physics and astronomy education ongoing, and you'll see why. We're publishing, column in the Physics Teacher, conferences. There's Sarah in action right here at the AGU table running our activities. We're learning a ton. These tactiles will be out on the table, and you'll be able to see how we're creating materials not only for blind and low vision learners, but also for sighted people as well. You get to experience that. Okay, I should be about done. Going to conferences. There's a spread of our stuff. You'll see that this evening. Publishing in the Bulletin of the American Astronomical Society about our activities. Trying to get the message out. We have a way, if you want to brand our projector and point back to our resources, we have a way that you can do that. And Shield Drive Center was our first go at that. And kids' creativity. Here are some other 3-hole punch pinhole projectors, right? From a classroom up the road. Lots of creativity, using our mathematical design specifications, putting punch on it, but making it the shape that they like. Okay, so Craig mentioned our newsletter. Thank you very much. I hope you will sign up for that or get involved, get engaged. And those of you who have been involved, we appreciate you, and we will be asking for a little more engagement as we go forward with our planetarium films. Thank you.
The next talk is an online talk given by Mary Hansen, and she's going to talk about the Student Thermal Energetic Activity Module, otherwise known as STEAM. It's Science, Design, and Build. So go ahead, Mary.
Thank you. Hi, everyone. I was supposed to be in person, but I woke up not feeling well, so I am remote today. I'm also going to turn off my video while I'm presenting because during Sherilyn's talk, my internet kept dropping. So I'm going to do that, and I will share my screen. Okay. I will give this a second. Okay. Awesome. I'm Mary Hansen. I'm an engineer at the Southwest Research Institute, and I am the former project manager for STEAM from when I went to CU Boulder. So STEAM is the student instrument for the Punch mission. Specifically, STEAM will be searching for X-rays in solar flares in active regions, and this is a graphic of how the STEAM mission will relate to the overall Punch mission. STEAM science objectives are to explore the enhancement of low first ionization potential elements in the corona, explore how coronal plasmas are heated in flares in quiescent active regions, and to support Punch science in understanding the source regions of solar wind and CMEs. So the main science behind STEAM is that during magnetic reconnection, an explosion of energy is released and releases heat into the corona. And STEAM is specifically looking at low fifth elements, which are elements that will point to the origin of the plasma. These elements are enhanced by a factor of about 4 in the corona over the chromosphere. And by looking at specific elements like iron and silicon and magnesium, we will be able to figure out where these solar flares are originating. If they are enhanced by a factor of about 4 or higher than what we're expecting for chromospheric values, we can say that these X-rays came from the corona as opposed to the chromosphere. So why X-rays? Soft X-ray emissions provide the most direct heat for hot plasmas and are sensitive to temperature fluctuations and can provide a comprehensive comprehensive coverage of the temperature and composition of these thermal plasmas. Currently, STEAM has one soft X-ray spectrometer inside. The hard X-ray spectrometer was damaged during their TVAC testing and was electrically disconnected. So STEAM will not be collecting any hard X-ray spectrometer data. So this is an image on the right of what the spectrometers look like. That box in the kind of back right-hand side of the image is the PCB stack, and it's about the size of a deck of cards. And the detector connected to the ribbon cable is about the size of your thumb. So this is a very small spectrometer that we are using within STEAM. And the table on the left is the expected performance of the functioning detector within STEAM. This is an example of what the STEAM spectrometers do. The red data in this histogram will be individual spectrums that get summed over a period of time and added up to the white line that you see. So every 10 seconds, STEAM is collecting data, and then we can take any amount of those 10-second histograms and sum them up to see the white line here. I will play this again just so you can see it again. And this is what the STEAM data will be doing. Yes. Okay, so for spectrometer calibration, on the left is what the emission lines would look like to calibrate the detectors. This is pre-flight calibration. So this was done prior to delivering STEAM to SWIRI in San Antonio. The science team at CU tested with a multitude of isotopes to find the resolution, spectral response, and energy scale of the detector. And they were able to use their code to create the gain and offset of the spectrometer. This is the current model of STEAM. On the left is the dimensions of STEAM. It's about the size of a small tissue box. And on the right is STEAM as delivered in October with the radiator attached on top. So once again, the hard X-ray spectrometer is still within STEAM, but it has been electrically disconnected. So that's why there are still 2 baffles and 2 PCB stacks in here. Part of STEAM's delivery was undergoing environmental testing. So we did thermal vacuum testing at LASP in Boulder and vibration testing at Element Materials Technology in Longmont. And these are images of STEAM during those testing. This is the calibration curves for the soft X-ray spectrometer pre and post vibe. So as you can see, the top graph shows the pre-vibe testing and the bottom graph shows the post-vibe testing, as well as an additional test of post-delivery. And there is little change between the curves in this pre and post calibration. So we have good confidence that launch will not affect the data collection and that the calibration that was done is accurate. This is what the STEAM data will eventually end up looking like after it goes through the data pipeline. The grayed out box on the right-hand side of this graph is where STEAM is not able to see. But STEAM will be collecting data at each thermal component, and then forward modeling will find the optimal combination of different versions of those models, as you can see in the different dotted lines. And then the red line is the sum that fits the whole spectrum and actually tells us what those different models represent. So for achieving the STEAM science goals, the X-ray photons will be observed, the continuum and spectral line emissions will be fitted with different temperatures, and the forward modeling will use Bremsstrahlung and atomic emission databases to help derive the physical parameters of what STEAM is actually seeing. The tentative data pipeline, there are 4 levels. The first level is downloading the data products right from the spacecraft and converting from binary to a user-friendly format, such as a FITS file. Level 1 data products will be calibrated, count spectra on an energy scale. Level 2 and 3 data products will sort the data into time-averaged bins and calibrated photon data. And level 4 data products will be the level 1 models combined with the physical parameters to produce the final model on the right. So in conclusion, STEAM was delivered with the soft X-ray spectrometer in October 2023. The preliminary data pipeline has been established, and the student work at CU has been paused, but they will continue with data analysis after launch. Are there any questions?
So the questions will be in the panel discussion later on, so Mary, please hang on and don't sign off yet.
Okay.
So the next talk will be West Research Institute, and he'll be telling us how to work with punch data. And
thank you all. Research Institute, there's a long list of authors here, people involved with the SOC, and also why is it Southwest Research. Title of my talk is Working with Punch Data, a How-To Guide. We'll talk a little bit about the data, what to expect with all of this, and I thought about doing a live demo, but what could ever go wrong with a live demo? Okay, so some excellent talks this morning, did a great job of introducing what is punch, so we're gonna skip that. We're gonna ask what is punch data? What should you guys expect as a community to get from the punch SOC downlinked to you all? So you've seen this animation before. This is some model data from Gamera that we have run through a quasi-pipeline to generate the synthetic output data. On the left, we see a rotating trefoil pattern for total brightness, and on the right is polarized brightness. We can see a CME erupting in this data, and also we can see the individual frames of each of the Wi-Fi instruments rotating around, and the inner NIFI field of view. These are the instantaneous trefoil products, so you'll see gaps in the data in the corners here. I'll talk a little bit more about how we sum those up into low noise data products. So how have we designed our data for the pipeline? We had a couple of sort of core data design principles that we wanted to follow. in particular how we deal with data and metadata. In the pipeline, we have really built things around using IndyCube to pass data around our pipeline. IndyCube is a fantastic library. You can create an object that bundles data, the associated uncertainty with that data on a pixel-to-pixel basis, so every data pixel will have a corresponding uncertainty pixel. It also bundles in a world coordinate system, a WCS, that describes where every pixel is actually in physical space in the sky, and also metadata. We want to have really robust and clear-to-read metadata. Again, we wanted to have very transparent and self-describing metadata. We wanted to make sure that that metadata could be converted into FITS 4.0 completely compliant headers. Over here on the right is an unreadable because of the size, but you get an idea of the structure of it overall. What our header will look like in individual FITS files. We've organized it not just to be readable, but to be human enjoyably readable, so that things are broken down into sections, things are well commented, just looks nice, right? You want to paint the back of the fence. Okay, so we're also utilizing, because we have multidimensional data, we want to take advantage of FITS's ability in IndyCube to represent that data three-dimensionally. We're using that to do things like polarization, uncertainty, et cetera. I'll talk about the structure of how we bundle those in a couple slides. For the data pipeline itself, Marcus gave a great talk this morning about how the whole pipeline as a component runs. But again, the ultimate goal of this is to do the very challenging task of combining 4 satellites into one sort of virtual observatory using these modern pipeline tools. Again, Marcus mentioned that we're using tools like Prefect for pipeline orchestration. We're using IndyCube for data handling. So a piece of data as it passes through the pipeline will be stored as a IndyCube object. It can be modified and updated as it passes through. We want the data to be easy to use and extensible to use. So the data pipeline itself, as was alluded earlier, you can create your own pipeline if you want to. Take the modules and create a new version of it. And also robust documentation. We really wanted to make sure that all of our modules are heavily documented, all of our data is heavily documented, so that there's no issues with understanding how a piece of data was processed. The data products themselves, as I mentioned, for this synthetic data set over here on the right, these are some preliminary synthetic punch data passed through a quasi-pipeline called SimPunch that takes in Gamera model data, passes it through forward to generate our polarized total brightness and polarized brightness. And we wanted to simulate real punch level 3 data. Note that this does not include a star field or an F corona because we're at this like level 3 level. I'll talk more about that in a couple slides. The next iteration of this data will also try to include realistic noise so that we can utilize it as a more analog of realistic data. So what will you actually get if you go to download a FITS file from Punch? You get this long file name, but I've broken it down. We start off with Punch, just to indicate what the spacecraft is. We have a data level. There are a couple different levels, but most of the data that you'll end up using is probably level 3 data, well processed. We have a product code. I'll describe what that means in the next slide. A timestamp, and then just in case we have version numbers to mark for reprocessing. So we have to reprocess the data. That will be marked at the end of this, just to indicate that. All of that will also be marked in the metadata inside the FITS files themselves. As I mentioned, level 3 data will be total brightness and polarized brightness. These will be the 4 primary data products that I imagine most people will use. They have been named PAM, PAN, PTM, and PNN. And one day I'll be able to say that quickly. PAM is the polarized low noise mosaic. These are produced every 32 minutes. This is an example up here in the top left. The corresponding trefoil is PTM, the polarized trefoil mosaic. These are every 4 minutes, and that's this product down here. Again, we just build up over one rotation a low noise complete mosaic. From NIFI, we also have products PAN and PNN. PNN is the trefoil equivalent of that, the every 4 minute cadence. And then also every 32 minutes, we'll have a composite low noise NIFI image as well. There's also corresponding clear data, which will be marked as CXX with the same product codes that are also generated in the data pipeline. So when you actually open one of these FITS files, what will you see? Here's an example of, like I said, one of these PAM data products. It's rice compressed, so the first HDU, if you open this, will be empty. It's just storing information about the compression itself. The primary data and the primary header will be stored in the first HDU, or the one index. And then also we have uncertainty, and the uncertainty header will be stored in the HDU2. You can read in this data using all of your standard AstroPi FITS frameworks. So we wanted to make it usable without any sort of bespoke software. We also built the bespoke software to take in that data that can do a bit more with leveraging, bundling the data, the uncertainty, and all of that into an IndyCube object. We also have a sample IDL script for reading in punch data, and that's a development on the Punch Mission GitHub, which you can access as well. So, the live notebook demo, I've converted into a static notebook demo, which is fine. You'll get access to this at the very last slide of this. I wanted to go over real quick how you might quickly in Python read in a punch file and plot it, for instance. So we have just a minimal amount of libraries we have to load: matplotlib for plotting, numpy, AstroPi for dealing with things like FITS and WCS. Always important to use units. We're importing SymPy maps and then also IndyCubes. So here's an example of reading in a file name with the standard AstroPi FITS framework. You can just open it as an HDU list, and again, you can read out from the first HDU, that data, the header, and the uncertainty. If we take a look at this, you'll notice that the data shape and the uncertainty shape, it's multidimensional, right? So these are 2 by 4K by 4K each. So again, we're stacking total brightness and polarized brightness for these data. Earlier data where we have sort of 3 polarized states, those will be 3 by 2K by 2K. We can take a look at the header. Again, here's an example of one of these nice to read header files. We can also then read in that header into an actual WCS object, so we can see what that WCS looks like. Again, we're multidimensional, so the first 2 axes here, and this is backwards from the way NumPy does this, are our helioprojective coordinates. And then we have a third axis, which is our polarization layer for total brightness and polarized brightness. And again, we can see all of our CR picks and our PC matrix and CDelts and N-axis, et cetera. We also include with this too a secondary WCS, which has all of this pointing in celestial coordinates in case you want to utilize that. We can construct this then, bundle this together into a SunPy map object and then plot it using the standard SunPy map framework. We can also bundle it into an IndyCube. So we can again feed the data, the WCS that we read out from the file, and then also the header into an IndyCube object. And again, over here we can see the output from that where we see the bundled dimensions, the axes, any units if those are bundled in, and also the data type. And then finally, we can plot this data just manually using matplotlib if we want to. So we can take advantage of the fact that we can feed in that WCS now into our axes here, show the data. There's a huge range of values in this. We need to scale it with a log norm scale. But again, it's very easy to work with this data, and you can plot it in a number of different ways. So this is my final slide. I talk too fast when I have too much coffee, sorry. Here's a QR code, I'll leave this up for a few minutes, but if you go to this website, you will find the presentation that I gave as a slideshow. We also have the notebook that I was giving excerpts from in this. We also have the sample data that we used to generate that notebook. There's also a link to a full data set. It's a couple gigabytes, but you can download it. And that will give you access to this version 2 of the data, which is updated with the WCS corrected. And yeah, I think that was everything I had. I'll leave this up here, and thank you.
The last talk of the session will be in situ solar magnetic connection.
Team for inviting me here. I'm an astrophysicist at the Center for Astrophysics, and I'm on the Parker Solar Probe team. And I'm going to talk a bit about combining in situ to solar connections with what we can do with Punch. And several of my slides will feature that synthetic data that Chris was just showing. So I really want to say thank you to the SOC team for making that accessible and making the FITS files really easy to use to plot a few things up. So the general concept I'm going to try and tie Punch into here is trying to tie in situ data measurements to source locations back on the sun. And this is a general task that operates in kind of two ways. There are two reasons we want to do this. One is that it allows us to extend the use of our in situ data to conditions and sources and injections of solar wind from the sun to explain why our in situ data is telling us what it shows us. And of course, the in situ data can give us a ton of microphysical insight and a ton of information. And it can also help us basically collaborate with remote observations of the sun to identify locations on the sun where observers with small fields of view might be interested in looking at if they can't see the whole sun at once. And then in the other direction, if you can establish these connections, you can feed back to our models of the corona and the heliosphere. So you can use the in situ data as a test of certain models, and you can try and tease apart, is my model is it consistent with the data that I'm measuring out in space? And this making a connection task here is essentially taking points of measurements out in space, and there's a huge gap of a region of space that we're trying to propagate a connection through, and Punch is exactly observing that whole region between the sun and the in situ measurements. So when I talk about in situ measurements, I'm actually going to here focus on Parker Solar Probe and Solar Orbiter, which, as we'll get to, are both basically their orbits take them off the Earth-Sun line, and they take them much closer to the sun than the Earth. And what that means is that they're directly flying through and interacting with the Punch field of view. And both these spacecraft have instruments that gather the same kind of physical parameters. They're measuring electric and magnetic fields, thermal plasma distributions and moments, and energetic ion distributions. And then Solar Orbiter, in addition, has a heavy ion composition instrument. And these are complementary, as I'll show in a later plot. So Parker Solar Probe has a very close approach to the sun, but it's very close to the solar equatorial plane, while Orbiter doesn't quite span the same radial range, but it can explore latitude in different ways. So when I talk about modeling magnetic connectivity, I'm talking about basically trying to come up with a mapping between a spacecraft position and time corresponding to a measurement, and then a source location back on the sun, so a longitude, latitude, and a time of emission at the sun. And there are generally two parts to this because you're trying to span two different kind of scales. One is the large scale portion of the heliosphere, and then the other is down in the corona where the physical thing is much more complex and anisotropic. So to do the heliospheric part, there are a number of approaches which essentially entail coming up with a streamline that the plasma parcel that's reaching your spacecraft has traveled along. So a simple approximation is to just assume it travels at a constant speed, which is called the ballistic approximation. You can take that further with empirical stream interactions like are implemented in the WSA model, and you can then go beyond simple ballistics and introduce hydrodynamics or magnetohydrodynamics and solve your fluid equations self-consistently. And then this gets you down to the corona with a pretty good guess of what region on the outer corona your parcel came from. But at that point, you can use much more sophisticated models with much finer grid resolution. And what you're seeing on the bottom left movie there is an example of a potential field source surface model, where the field line that you can get, which is the blue line there, is basically a non-trivial field line that you're tracing using a field line tracing method, and that basically takes you the rest of the way from some position on the outer edge of the corona down to a source on the sun. And so there are all these models and ways we can do this, which again basically end up giving you a mapping from your spacecraft position and time to a source location at the sun. But how do we have any idea that what we're finding is real or in any way robust? So there are a number of ways you can start to approach this. The first of which is to assess how good your models are using complementary data, so remote observations. So for example, here are two ways of assessing the global nature of coronal models. The top is showing an example where we're trying to assess how well our EUV observations of coronal holes map where we are modeling coronal holes to be in a given model. The bottom is showing a similar assessment where you're looking to see if the model's neutral line in your corona matches what we can observe, and we've extracted and observed a neutral line using white light data here. So this gives you a sense of if your kernel model is a good representation of the global kernel model at all. And then you can use the in-situ data itself as a constraint. So on the top right there, you're looking at a modeled neutral line in the background. The red and blue patches are showing the kernel magnetic field. And then as our spacecraft fly across the sun over time, they also measure positive or negative magnetic fields, and we can try to see if they match. And then the bottom right is an example where we're using a Parker Solar Probe data encounter where they travel across basically 120 degrees of longitude across the sun. And as they went, they measured stream structure, velocity variation, which we could tie back to specific kernel hole sources. So the fact that you had stream structure matching where your connection was predicting was a good validation that that particular kernel model was doing a good job. And then you can also introduce compositional characteristics, which has the advantage of assessing a consistency at both ends. So you can remotely observe compositional characteristics, or you can observe them in situ, and because they are frozen in once they get a certain distance from the corona, they can basically give you constraints at both ends of your mapping. And Yemi Rivera will talk more about this general topic in this afternoon's session. So going beyond data, we can also just look at the mapping result itself and try to investigate how sensitive it is. So again, there are multiple models you can choose to make these connections, and one test of robustness is just do you get the same answer if you use different model inputs. And similarly, there are multiple portions of your modeling where you have parameters that you can vary. You can vary the boundary condition that you're driving your model with. You can vary the solar wind speed that you're assuming the particle travels out as. And you can basically vary all of these parameters and figure out that if something changes by a small amount, does it change my result a lot or little? And then if if all roads lead to the same result, you end up mapping to the same source, then you have some confidence that this mapping result is robust in itself. Okay, but so then there's a ton of stuff that is being simplified here, and it's a task that we're doing where we don't have a very clear ground truth. And there is a number of ways in which punch data could then come in and help us assess some of these issues. So one example is that we're using a steady mean flow assumption. We don't have any small scale perturbations to our field lines. We're assuming these parcels basically travel along smooth streamlines. There's also an issue in the heliospheric part of these connections where you are assuming your flow basically travels along a line of constant latitude. So there's no assessment of if there are any meridional flows or anything that changes the latitude of your flow parcel. These models are generally time independent, although we're now getting the first time dependent models becoming feasible now. But of course, this means that any of these mapping exercises don't account for transients or variations in the background flow. And so our magnetic connectivity, which is implicitly assuming that your connection stays valid for a certain amount of time, that's something that is not currently tested for in these kind of time static models. And then lastly, the transit time is something that we are, it's a important factor here where we're trying to say that a certain measurement in time was associated with a certain observation back at the sun at a certain time. And that transit time depends on the acceleration in quite a strong way. So when we assume that our particle is traveling at a constant speed to get it back to the sun, we're not accounting for that at all. So bringing punch back into the picture here. So these measurements that we're making, where we're trying to connect back to the sun, are occurring really fully in the field of view of punch. And so if we place them in context, we basically are, we're getting a data set from punch which can feed in that region of space that we're trying to reconstruct by mapping back to the sun. Again, Parker Solar Probe has this strong variation in radial distance, and Solar Orbiter has this strong range in latitude in the latter stages of the mission. So the bottom left here is showing that in a planar sky projection using punch synthetic data. And in the top right, you can see this projected onto the Thomson sphere in 3D. And what this shows you is that the spacecraft in situ data will typically contain 2 crossings of the punch Thomson sphere. And the Parker orbit in particular, because it's got such a high ellipticity, could be tangential to this surface for a long period of time. Additionally, Parker's later orbits will involve 2 radial scans for certain orbits where both of them are over different limbs of the sun. So you can get radial traces across punch data for basically both sides of the sun only a few days apart. So how can this be used then to address these issues with magnetic connectivity? So the punch field of view is then going to give us a bunch of information about flows and density in the path from the sun out to these in situ measurements. It can give us a sense of where and when making steady flow assumptions is valid or not. It can also, because the field of view spans obviously the whole way around the sun, we can look for differences in latitude. Do we see evidence of basically non-radial flows potentially playing a role in the path that parcels would take to get from the sun to our in situ spacecraft? It can provide flow measurements as a function of radial distance, which helps us to tie in an acceleration profile that we can verify empirically, which helps us with the transit timing. And then, because it's a high cadence measurement where you can see transient flows happening all the time, we can also identify where and when transients are interrupting our connection picture. And then I just wanted to close with, so this, where we're using punch here to inform connections where we're trying to make more use of in situ data, we can go in the reverse direction and use in situ data to better interpret punch data. So this is an example where the synthetic data is again being deprojected into 3D onto the Thomson sphere. And so whenever the in situ measurements cross the Thomson sphere, you can basically know a ground truth at that point in space and time. So it can insert microphysical insight into the punch observations of flows and densities. So any in situ quantity that you have in that data set, you can associate with that punch data. But one thing you can go further is to inform 3D modeling. And so thank you to Matt West for helping me with this computation of distance from the Thomson sphere. Essentially, the punch polarization data can be used to infer if a 3D structure is located, how far away from the Thomson sphere would be located. And there are two solutions to this. And so if you invert the image, you can get 2 surfaces where one is towards us and one is far away from us. And again, because our in situ data measurements are flying through both these hypothetical surfaces, then we can have a ground truth which directly can test whether one of these pictures is true or not. And so that's possible not just in the sense of is your density enhancement occurring at the right time and place, but also the further back, the behind the Thomson sphere surface is blown up, it's kind of inflated, and the interior one is shrunk down. So you can test the spatial scales of things. So if you measure a larger scale structure versus a small scale structure, you could potentially tell between these 2 pictures. So just to wrap up, so the punch mission basically offers a continuous field of view of plasma density and flows that fill the interior space that goes from the sun to our in situ measurements. These are continuous remote observations of steady and transient flows, and they can observe it at all different latitudes. And so this is basically going to mean that we can fill in a large portion of that we're making big assumptions about when we do connectivity with physical constraints. Thank you.
speakers please come over to the podium here? And Mary, you're still on there, right?
Mary, are you still on?
Yes, I'm still here.
Raphael, where's Raphael? You have a first question? Or Sherilyn?
Yeah, hi, it's a question to Sherilyn. Hi, it was partially answered by Craig, but so it's about whether we can access the Chaco Canyon, in particular the observatory that you showed. Can that be accessed freely? Do we need permission? And what about accessing it during the night for the purpose of doing astrophotography? So in your presentation, you showed this solar observatory of the Chaco in the Chaco Canyon, right? And I'm interested in someday accessing, going there.
Testing.
Yeah, I'm interested in going there to do some Milky Way astrophotography for outreach purposes. It's a work I'm doing with the NIH actually, but it's a long story. So basically, is it possible to access this observatory alone or with other people at night to do some photography?
Yeah, so we've done a lot of special use permitting. We can help with that. You have to get a special use permit from the Park Service. It's not a trivial process, but it's a doable process if you give it adequate time. Yeah, be happy to help with that, Raphael.
That answers the question, thank you.
Okay, so the next question will also be for Sherilyn while you're still on there, from Michael Kirk. Are you in the room?
Hi, Sherilyn.
Hi.
I was wondering what Punch is doing to talk about heliophysics, the word heliophysics, and describe the relationship between Punch and what heliophysics is, helping people understand that it's a word, maybe contributing to it getting in the dictionary, which it's not. I know that in your talk you mentioned how heliophysics is a big concept and a big word, and I'm wondering what you're doing to help support that.
Yeah, so the idea that heliophysics is about sun and heliosphere watching, and the ancient and modern sun watching theme is trying to sort of broaden what we mean by that to backdoor into using the word heliophysics. Those three, drag and drop, fill in the blanks, those last three, I would love your feedback on, Michael, because they're attempting to do just that, is to introduce the term heliophysics, unpack it with the Greek god Helios, understand what sphere is and why heliosphere is like atmosphere or biosphere, you know, and really unpack it a little bit in a gaming word-like literacy game for heliophysics. And so there's three of them: the solar wind and heliosphere, solar storms and solar cycles, and also one specifically on the Punch mission. So we are going after that. And what we find is that kids love to learn multi-syllabic words. I mean, they know five-syllable dinosaur names. If you make it accessible and take the time to unpack it, people can get it. And this idea that the physics of the sun is physics of the sun, physics that occurs everywhere, magnetic reconnection and so on. And we're trying to express it artistically as well, as you'll see this evening from the demonstration of our dancer. And so just coming at it in a cross-cultural, artistic, arts-integrated, multi-sensory way that also acknowledges the need for the linguistics to tag along.
Thank you. Michael, we should stay with you, and you have a question for Chris.
Okay, so Chris's question. All right. Can you describe what other data formats besides FITS that you might be releasing? Specifically, I was thinking the JPEG 2000 for HelioViewer, NetCDF or ZAR for cloud computing / cube support.
Yeah, that's a great question. So our primary data products are FITS, because that's sort of the standard. If we want to integrate with something like JHelioViewer, I think they use JPEG 2000, which could be an option. We're making, yeah. And then also we are making some quick look products as well, which are standard PNG MP4 files as well. But FITS is the primary sort of science data product just because of the heritage and long history of that.
Staying on the same topic, Raphael, you also have a question for Chris.
Yes, Chris. So where's my question? Okay, it's gone. Yeah, the punch data set can be pretty heavy for a normal computer, a laptop. And so you showed the ND cube and the rise compressed fits. So by experience with SDO, they are not compatible with memory mapping. My question is, have you tried that with the punch fits? Will that support memory mapping when we're directly loading the rise compressed things and ND cubes?
Yeah, that's a good question. These are big data, right? They're 2 by 4K by 4K with an uncertainty layer on top of that. We've made the uncertainty layer 8 bits to try to reduce the impact of that. I did just test, I saw your question, and I just tested it, and it does work with memory mapping.
Sorry, can you repeat that again?
It does work with memory mapping.
Oh,
so
awesome.
I just tested it with some sample data. So, it should work.
I mean, and specifically the memory mapping I'm talking about is the one from the AstroPi fits package. So you're saying this is what it worked with it?
Yeah, so I toggled that to true and it read in just fine.
Okay.
Also, once you read it in as an IndyCube object, say, it supports all slicing and everything as well, so you can slice all the data down if you need sort of a more manageable just chunk of it as well.
Okay, perfect.
Because you can slice it based off the WCS, and everything just scales automatically.
Okay, great. Thank you.
Let's go on to Samaya. Again, this is for Chris, I assume.
For which one?
Synthetic punch data.
Oh, yes, for the punch data. Are there any packages right now that we can use to align synthetic punch data to other instruments?
That's a really good question. I thought about actually for that demo notebook doing exactly that. But because we support things like SymPy map objects, for instance, you can do standard overplotting of images like that with alpha channels and things like that. So it should support all that. And then you could also, you know, roll your own code as well too if you want to do something more custom with that, because it has all the corresponding WCS, so you should be able to overlay, reproject. However you want to overlay data, it should work with it. So. Oh, and just on that note too, if anybody takes a look at that notebook and has any questions, feel free to come track me down and bother me about it during this meeting. I'm happy to answer any questions or get you set up with that too.
Outreach would be very interested in that kind of overlaying and in terms of communicating, yeah.
I want to see some of these synthetic data on a planetarium dome, because I haven't seen it yet.
Okay,
Let's do it, come on over.
Okay, so let's move on to Mary. You still there? Craig.
Hey, Mary. How many students have been involved in STEAM over the years?
I was just checking because I saw your question. I believe over the past 5 years, there have been 40 plus students involved with STEAM.
Staying on the same, you had something. Sarah, you have a question as well.
Yeah, it kind of works as a follow-up to that. So how do you maintain the continuity across the years? You have different students, different mentors too, I think. So how does that work, and any thoughts on that?
Yeah, specifically for the students, when we hired new students, when we knew students were graduating or, you know, got an internship, different internship over the summer, we would make sure to hire new students with enough overlapping time with the previous students so they could learn from the previous students. And specifically because the work is now paused until launch with the data analysis, the previous STEAM students, the most recent group of STEAM students made videos talking about their data pipeline code and what STEAM is, and the mentors will remain the same between now and launch. So there is the previous knowledge from them as well as those videos from the previous STEAM students on, you know, how how their code works and what STEAM is and how to move forward. The STEAM team is also working with professors at CU to be able to have more of a background moving forward with exactly like how to do data analysis, because the mentors at Space Grant have knowledge in that, but they're not. There are scientists at Space Grant, but having the professors who do data analysis for their classes will be helpful moving forward. Does that answer the question?
Thanks. One final question for Mary, and that's from Michael.
Okay, yeah, thank you. I was wondering how STEAM data is going to be complementary or different than the expected cubics data that's going to be hopefully overlapping a little bit?
Yeah, the data will be overlapping a bit. Cubics has 4 of the spectrometers, same kind of spectrometers that STEAM has. However, Cubics has different filters and aperture sizes than STEAM does, so those will target different flux levels. So the data should be very complementary between STEAM and the Cubics SAS instrument. And then Cubics also has 2 other instruments on board that can help with wider picture sort of data.
Thanks. Let's move on to Sam. The questions have been piling up for him. Craig, you want to take the first one?
Sure. I loved your visualizations. They're great. Are you planning to open those tools, or are they one-off analyses?
They're all completely built on open source libraries, and if the punch soc is interested in having like extra notebooks, like I'd be happy to give them.
We're very interested in that. we should talk after this.
Sarah.
Yeah, so question for Sam. Yeah, so you talked about these ways that Punch really can provide information to improve the models, showing where the assumptions that you're making are not as good. Do you have any thoughts about how these might actually lead to iteratively improving the models?
Yeah, so I mean, I guess the answer is data assimilation at some level. I guess all these models are generally driven by a lower boundary condition and not validated any higher than that. So I imagine, and I'm not an expert in doing this at all, but like there are a ton of people who do a lot of data assimilation. So I would say that like inserting ground truth, I guess, at like multiple altitudes would be the way to start.
Okay. Bill, very technical question here. Glenn, Bill is here.
One not so technical. Yeah, Sam, you mentioned something about field line meandering, which I think was not included in most of the mappings that you did. But you described it as a small scale effect, but it's really, I think, not a small scale effect, is it?
I guess the picture in my head was like you have small scale wiggles adding up to like perturb a large scale field line. So
that's not how field line meandering works. I mean, even in Jacobi and Parker 66, it depends on the power at 0 frequency. So, and that's for things that become uncorrelated beyond the correlation scale. If you look at the 1/f signals, they extend all the way back to 1 AU. So I think that the field line meandering is dominated by things that are at the scale of an AU, really. That's my guess, not small scale at all. And so I was going to follow up the question, how accurate do you think these standard methods for tracing field lines back to the surface of the sun are?
So I guess I should be careful to distinguish field line tracing versus like the general process of backmapping of like trying to say where plasma parcels originated from. I would say for field line mapping, it is definitely a large effect, and I think the best estimate of uncertainty is I've seen a couple of papers recently showing the distribution of longitudes where SEPs are measured compared to a certain source active region. and they have this like broad Gaussian distribution of where they're receiving those SEPs. And I guess I'm not sure what that number is, but it's centered at like the ballistic approximation, and then it has some width there. So that's like a good uncertainty, I would say. But I would need to go look at what the number is.
I don't think Rohit's here right now, but he had a paper on that using standard field line random walk calculations. And I think it's like 20 degrees or something on the surface of the sun. And it's going to be worse if you include the 1/f noise. So maybe you can't really do it at all. I think people are guessing.
It'd be interesting to compare these two numbers, right? If modeling gives you a prediction of like a region of the heliosphere where you might expect to end up receiving particles from.
Okay, next question for Sam from Christopher Rura.
Yeah, Sam, great talk. I was wondering if you had any thoughts on like what specific boundary conditions or assumptions you think could be improved using data from Punch.
I guess it's I mean, the boundary conditions we're actually using, right, are magnetograms. So you could, I guess, like choose between magnetograms potentially by like validating against punch data. But like I said to Sarah, I think it's like a new set of boundary conditions that aren't currently incorporated in models at all, where you just have information at different heliocentric distances and different latitudes and longitudes, and it's like directly coming from flows and densities, plasma properties, rather than setting it from magnetic fields to start with.
Okay, so Sam can respond to Bernie Jackson and Dave Webb's question at the same time about Bernie can channel Dave.
Okay, I just wanted to know what your thoughts were about combining punch data with Whisper, Parker. As you know, you were talking about Thomson sphere and such, but you're actually looking at quite a long distance, and you could combine these two analyses or two data sets to better refine structures in time-dependent form.
So adding to that is also Solar Hive a request from Dave Webb. So talking about both the heliospheric imagers.
Yeah, long way out of my wheelhouse. But I at least each of these observatories then has its own Thomson sphere. So it's like well, I guess you're assembling a bunch of like my visualizations of this 3D surface. You have a bunch of those independent planes and different orientations. So I guess there is a lot of routes to like discriminating between 3D localized structures and like cases where like trying to look where your line of sight is getting stuff from a large range of distances. I don't have anything more concrete than to say that they are different planes of skies that are independent cuts at a 3D thing that we're trying to uncover in the first place.
Okay, so next question also for Sam while he's in the hot seat here, but from Elena.
Sam, thank you, great talk. My question is, have you looked at the connectivity with the time-dependent simulations, inner heliosphere simulations? Because in our Gamera time-dependent simulations, we see that magnetic field lines significantly deviate from Parker spiral in the time-dependent simulations.
I haven't personally worked with any time-dependent simulations yet. I think I've seen some initial time-dependent results from PSI, from the mass model, and I think they see similar things of like dynamic changes in the field lines being important. So I personally haven't, but I think yes, absolutely, it's important to.
Yeah.
Next question from Nariaki, also to Sam.
if you look at the in situ data, the quantities are never steady, always changing. They may be affected by some small scale transients, which may be well observed by punch. And how can you incorporate that kind of information in more kind of global MHD simulations to see when the CME arrives at L1 or something? I sometimes look at the NLIL simulations at CCMC or Group C, and arrived, that was something like that. But if you look at the data before the CME arrival, often the solar wind parameters are way off the predictions. And even if the prediction is arrival time is okay, but information before that is completely off. I don't think the model is validated. So the inclusion of these non-steady component of solar wind can be really challenging. So how can you address that question?
In terms of using punch data, I guess you could think about assimilating information about transients like early on in the transient's evolution, and allow your model to propagate it, and then like keep validating it against punch data later and later. I don't know what you would then tweak in the model to kind of like say, okay, this isn't working at all, what do I change to do better? But that would be where I would start, I think.
Okay, so next question also from Nariaki, but this is to Chris, I think. Yep.
Yeah, yes, I think, I just look around and I'm glad that there are several people much older than me, but I'm feeling like a geezer and kind of feel left behind when I heard your presentation, and how much knowledge do we have to have, or how good should I be in software, especially in Python? I attended many Python tutorials, but that knowledge never is in me. And no, because the tutorial is so kind of professionally done. I should say maybe using too technical terms, which is very hard to catch up with. For example, you said ND cube or something, and I just saw some Dan Ryan's paper about that, and it's very hard to understand. So what kind of help are you willing to provide to those people who feel left behind?
That's a really good question. We don't want to make anybody feel left behind with this. We're using Python sort of as the main language for this, but we wanted to make it as accessible for everyone to access. So you could load it as an NDQ if you wanted to, but you could also just load it using standard FITS files that just read out a data array, a header, and you can do everything that way if you want to. So we wanted to make this sort of multimodal in that you can access this data in whatever is most comfortable for the individual user. We also want to have a repository of notebooks, Jupyter notebooks, that are also be accessible as regular Python scripts as well on the website that do simple tasks like, okay, I want to read in a punch file and plot it. How do I do that? Okay, I can download this notebook and use that as a jumping off point to do my own analysis. Or some other sort of small targeted type notebooks. But we want this to be very open and feel very, what's the right word, welcoming to everyone in the community, because we want people to use punch data. We want it to be easy to use punch data and fun to use punch data. So you can always ask us questions because we're happy to help.
Chris, I for one was impressed with over here, Chris. I was impressed with you being able to display and plot data with just loading a few libraries and just a few lines of code and present that real time. I was impressed.
Turns out some computer scientists that know what they're doing have done most of the heavy lifting in terms of building these software libraries. We do also, like I mentioned in this, we're supporting some IDL read scripts as well, so that you can still access the punch data using traditional IDL scripts as well. So again, we want everybody to use this data.
Okay, so let's move back to Sherilyn Samaya up there.
Hi, Sherilyn. I'm just glad to see that, well, you mentioned briefly that we were planning for planetarium shows with as a next step. I was wondering if it was any thought on how to make those planetarium shows accessible to more people in rural areas that don't have planetariums, like for the classroom. I have no idea how planetarium technology works, but I know there's been some improvements in 360 cameras recently, or not recently, but since planetariums were big. So maybe, are there any plans for that kind of thing?
Yeah, thanks for asking that, Samaya. And I have our planetarium gurus right behind you, the director of Fisk Planetarium, John Keller, and Thor Metzinger, and they are pretty tuned in to how to make this happen. And I'm going to defer to John.
Thanks for the question. So I guess two responses. One, we do have a planetarium network of over 750 planetariums in 68 countries and 48 states. So while I totally appreciate those are all, you do have to travel to those locations, but those are, our films will be released free of charge to all of those, to any planetarium that wants to download and show the film. So the first piece would be to encourage communities to talk with their local planetariums to download the content. Second, there are actually VR viewers, right? So a planetarium is a community VR space, but we have had other films at Fisk that we have put into a screen viewer where you can actually navigate around in 3 different directions, in all directions, to see like the front of you're in a virtual planetarium, you can look forward, backwards, sideways, and left or right. It's not as immersive as being inside of a dome, but that is a way to not lose the 3-dimensional 360 perspective of the planetarium film. The third approach is to do cropped views, where you can crop into the sweet spot of the film and make, as you're describing, smaller, short, rectilinear versions. It's not as dynamic as the planetarium space, but all 3 of those are things we will be exploring. And the fourth piece is that NASA comms will be making flat screen types of versions. We have the Rock of the Sun video that just came out. Those are specifically for rectilinear 2D perspectives, and those will also be produced as part of the product.
Did you, maybe I didn't hear it, but did you mention the portable planetarium possibility?
So consistent with the same idea that all of our films are free and available to the world, there are a number of portable planetariums that travel outside of planetary spaces, but again, that you still have to arrange with that to happen. There's a great NASA-science project called NASA Astrocamps that serves over 40 to 50,000 residents of Mississippi and Louisiana, traveling all over that entire area to provide rural schools with access to the dome in a small 30-person setting. So these are all great questions, and something that the planetarium world is continuously trying to figure out is like, how do you deal with getting more broadly content without the dome space?
Oh, yeah.
Just quickly adding on to that, I heard a really nice invitation. Let's go over to Fisk and put some punch data on it and see how that looks. And so it seems, Chris, you were quite enthusiastic about that. So are we.
I'll load it on a thumb drive.
You load it on a thumb drive and make a trip over. So yay, we got a thumbs up from the director. And the other thing is, in these films, we are in a relationship with Parker. Parker has contributed considerably to the making of these films. And so we really, this complementarity, getting that phrasing right, those key messages for how those differing perspectives relate to each other, is something we're very interested in capturing with these films.
Heather, you have?
Yeah, I want to comment on my comment. It would not be a bad idea to, when you make outreach materials and press release materials, putting NASA heliophysics in there, because that's how all the work that we do that's from NASA is funded. And so when people talk to Congress, there'll be a connection there already. Yeah.
Craig, one question for Sherilyn.
All right, this is sort of a softball, but it needs to be sort of aired, which is how should individual scientists engage with the outreach program, either I was thinking, it's sort of easy to get recruited for these large events and so forth. But, someone's got a kid in elementary school or, gets an invite to a high school, how to engage?
Come to punch 56, punchoutreach@gmail.com will always work. We are ready to support any of you. We'll send you a kit of stuff. We are happy to engage when we want to pull on you, and I emphasize that in my talk, but also you can pull on us, right? And if there's something you want to do with your children's classroom or anything else in your community, we are ready to jump to the fore and send you what you want and receive your ideas for what you think we're not yet doing.
Thanks.
Are there any other questions for any other panelists? The room? No? Before we break for lunch, Craig will have the last word as he has a comment to, I think, Sam's.
Just a comment about you guys are in for a lot of fun with the tracing things back to the surface. It's going to be a good time. I want to thank everyone. Just really great presentations today. Specifics on how to engage with the data, with the outreach. Really thought-provoking and intriguing visualizations, and wonderful description of the student activity that went into STEAM. So thanks, everyone.
Good to see you, Mary.
I want to thank definitely all the speakers, all the chairs this morning, and just to let you know, we've got lunch now. Yay, there's a line outside. You can take your food back in here or outside or where you want to do, but at 12:20, Barbara is going to be leading an open TOPS Transform to Open Science 101 discussion. And then from 1 to 2, we have the poster session, so please go see the posters, and we start with the rest of the presentations at 2.
Now is the principle making research products and processes available to all. And while respecting diverse cultures, maintaining security and privacy, and fostering collaborations, reproducibility, and equity. Now, so really, open science is both about looking inward in the way we do our research and also looking outward in terms of the impact that we have. You see that the way that the Punch mission pipeline is being developed, it's being developed with open code, open resources, intentionally, so that this team, which is extremely talented, one of the things that makes them so powerful is that they don't assume that they are in 15 years going to be the best at something. And so they invite the community to, first of all, see exactly how they're implementing everything and contribute. Now, and this is the thing. So my goal is to get everyone who's a core person in Punch to complete open science certification, which means all of our team members, all of our working group leads, and anyone involved in Punch to really understand the practices of open science. And so open science, they transformed open science initiative, which hereafter I'll just call it is TOPS, is part of the open source science initiative, to really capture both the advantages and the opportunities of having a fully open mission conceived and implemented from the start as an open mission. So there are 5 aspects, well, really there are 4 aspects of open science. There are open tools and resources. That is often done through GitHub, but also I have a goal of doing even more than that. Part of openness, and I think Nariaki had a question earlier about this, was what if, okay, great, it's on GitHub, but what if you don't, what if this isn't something that's an easy thing for you to do? Having resources that help people to learn these things without having to become completely proficient at the medium through which these tools are distributed is important too. And so we had a great team meeting on Tuesday, and we talked about creating interactive tools and training materials for people to help them understand how to use and access Punch data. And of course, the big thing is open data. There are different ways that people practice open data. One of the really important things is that people are the more you're starting to see more opportunities come out, if you're used to writing science proposals from, in particular, NSF and NASA, that specifically talk about open data, data management plans, licensing, software license, open access licensing, and things like that. And so doing this training, if you already believe that it's important to practice open science, then this training is nice because it helps you really get the principles very quickly and efficiently. If you do not believe it's useful, well, you're still going to have more and more requirements implemented. NASA is passing policies that do include all 4 of these aspects: open tools and resources, open data, open code, open results. And so inside this training are extremely useful and important things that correspond to what's either been implemented or is coming up in federal government, U.S. federal government research requirements. And so this is a great way to go ahead and just say, hey, I take this training. If those of you have, I've seen, if people are trying to write a data management plan, this part, the part that talks about how to write a data management plan is so clear. And so, Chris, you've seen it? I'm seeing Chris nodding, yeah. It's so clear, and it really is useful. And now I can tell when I see a proposal who has actually seen that, because they put it together exactly the way they recommend it, and it's done really well. So this might take you a little while, but it will save you some time. All right, so my goal in this session is to mainly give you a quick overview This thing is called OpenScience101.org. OpenScience101.org is your pathway to the 5 training modules. And the training modules, the first one is the ethos of open science. That is just in general kind of what I was saying here, but with a little bit more information about what are the aspects of open science, why do we do it, and what aspects of and what do you have coming up in these these upcoming modules. Module 2 is open tools and resources. Module 3 is open data. Module 4 is open code, and Module 5 is open results. And again, I think the 2 that I think will really help you a lot if you're just writing analysis proposals are the open data, because open data, it doesn't just apply to missions. There are people that are also, when they are undertaking analysis, let's say you're writing your punch proposal, you're going to be manipulating and using data, and more journals now are requiring you to, when you publish your results, it has to be validatable and, if possible, reproducible. We can get into the levels of reproducibility that are possible with certain models, but basically this more and more people, when they are writing proposals, it's we're lucky in our community that we haven't been hit as hard, but there are some communities that are hit with many famous papers that are now under question. Because of the way either the data or the analysis or the interpretation. It's interesting too, because a lot of these, some of the ones I've seen, they're very innocent. A lot of people will go ahead and will manipulate data and say, well, this data point looks weird, but when I looked at this data point, I realized it was because it was during, a time when there might have been aurora that was mislabeled. And this other data point, this one's kind of fuzzy, so that might have been during a proton storm. And what happens is people will innocently examine the outliers and remove the outliers from their distribution without applying the same criteria to the ones that land within their expected zone. We do this naturally. It's somewhat a confirmation bias where we go and we examine that. And so this is, so what's happening is that people, a lot of papers, journals are saying, well, even if you innocently chose a subset of your data, I look at Bernie. Bernie's seen this a bunch of times. Even if you innocently chose a subset of your data that you thought was representative, but your selection criteria, you unintentionally excluded a real population of your data, and your results are skewed. Journals are now requiring people to be a lot more specific and have reproducibility. So all of these things here are going to help you become write better proposals, write better papers, have an easier time with your editors, and also, and for me, perhaps the most compelling and exciting thing is that if you figured out how to do something, or more importantly, if someone else figured out how to do something and said, okay, this was really hard, they can share it, make it open, and nobody else has to suffer through that again. And so this is it's a very exciting frontier to be in. So I'm going to go in here. I have, it's kind of fun too. I don't know how much you guys were all in Scouts when you were younger, but it is kind of fun to get I got my badge. It's exciting. You can get your TOPS badge, and you can, so anyways, but I'm going to go back to starting with the ethos of open science. And again, I would like you guys all to consider at least doing the first module. Go through it, see what it involves. A lot of you are going to say, okay, this is all pretty obvious because you've been practicing most of the aspects of open science. But Chris, you saw this. Do you remember like seeing it and being kind of like, that had something that kind of surprised you and you're like, oh, that's kind of neat? Or did you just think this was all blindingly obvious? Okay. Sorry, this is an audience participation.
I remember. Just a comment. I started putting a couple things on Slido so people can do the same thing. So
great. Okay. All right. But
I remember coming across stuff that I remember, oh, this was not obvious. This is new to me, but I've forgotten what it was now. So,
Well, the licensing stuff is really like,
that was super helpful.
yeah, because all of us are kind of like, let's choose, this looks kind of good or something. But we were choosing licenses, a lot of us, based on how we personally thought was the best license for the use of it. But most of the stuff that we're talking about here is stuff that has been funded by either a funding organization, or at least, and as members of your institution. There are licensing aspects to that. This is not just Sarah just being bored and doing this. Sarah is an employee, and so understanding that the aspects of licensing, if you've made some software or a tool or a resource, or if you're publishing a data set, there are policies. If NASA funds you or if NSF funds you, they have different requirements on, okay, you've used taxpayer dollars to do this, to produce this data set. These are the licenses that we require you to use, so that the public we get benefit from it. And there's also organizations that do have different aspects of licensing. So, yeah, Sarah?
So I was going to just suggest there's a few, I've got some, I could ask the Slido questions, and let me ask people in the room if they want to ask the question themselves, to just go to the mic so that I don't have to stop eating. And otherwise, I will read whatever gets put on the Slido. Okay?
Okay. Are there any good ones right now?
I can give you the ones on top, and you can basically call on me for questions when you want, if you want to do it that way. Okay, there's several. Okay, so the first ones I did were, how long do the modules take? And it said something about linking to your ORCID. How does that work?
Yes. Okay. All right. When you log in, you get a dashboard, and whenever you create a dashboard, then you can add your modules to your dashboard. This can be, let's see, I'm trying to remember. I did this over a year ago when I registered. There we go. But you can see my ORCID is here. For those of you who don't know what an ORCID is, it's an open research something ID. And what it is it's a unique identifier number. It's almost like the Social Security number of science, where you get a unique identifier number, and then as you change institutions, you might change your name, all these things. But your ORCID ID stays the same. And so that is a unique identifier that you can get. Everybody should have one if you are participating in anything that might be connected to a scientific organization or scientific activity. If you're on an outreach team, you're going to be doing things at AJU. They're going to be listing your name on abstracts. It's good to have this because you have a unique identifier. So yes, so there's the ORCID. And how long does it take? These can take a while to actually go through this. Let me see if I can, I will show the course outline here for the first one. How well can, not very good, let me make it a little bigger. What is open science? Why is open science important? 6 activities. So these are interactive. What you'll be asked to do sometimes is, like, they will talk about what is open science, and then you might get a set of boxes, and it's like, okay, I made a new PSF corrected data set for Punch. What would I do? What would this correspond to in the open science landscape? Because I use software tools. It's a tool and a resource, but it's also data. And so an example of that might be, okay, you've got a new, how do you, now that as we go through and we explain different aspects of open science, you might be asked to participate in an interactive activity that tests your knowledge and also uses examples. Because, everybody's seen the thing where this makes perfect sense, and then as soon as you get to it, like, you try to apply it into your situation, it's not so clear. We don't fit into compartments so easily. And so here is, they have a lot of activities. Here's just one. Multiple response question. what societal problems can open science help to address? As I said before, people call it the scientific reproducibility crisis. But again, there's a lot of very important results that are difficult to reproduce. And well, I mean, yeah, again, most of the stuff that's been hard to reproduce that I've experienced with, it was poor documentation and innocent, either maybe selection bias or something like that. So I haven't seen, but yeah, but there are actually, people who've done, there's a whole ethics of science anyways, but the scientific reproducibility crisis, if you practice open science extremely well, that means that if your results are validatable and reproducible, you can rely on them more. People can rely on you, and you don't ever have to be, if somebody questions you, you're like, here you go, have fun. This took me forever, you can do it too. You don't have to worry about having to prove that. And again, some journals are now requiring a lot more than just, this is a picture, this is a graph or a plot of the data that I analyzed. They're like, no, I need the data, and I need the tools and the resources that drove that plot before you can publish it. It can help with get rid of the spread of misinformation that is, associated with that. Certainly, I mean, I wish every single one of the papers I've written were 100% correct. I'm excited that Punch will do auroral physics. I did my PhD research in auroral physics, and I published a paper on the model that I did in graduate school, and I found a sign error in my code after the publication of the paper with the model results. Fortunately, the equations were symmetric with plus or minus, and so the fact that my electrons had positive charge in some cases didn't matter so much because of the but it can, it can help remove decrease the spread of information. And these are all, I mean, these are kind of all obviously it can help to address the increase in paper usage due to the printing of scientific journals. And actually, that could be open access journals. Sometimes these questions aren't so clear because open access journals tend to be digital, but yeah. The practice of open science combats misinformation by making results available to the public. And it helps people, let's say that you're a science communicator and not just a person who's writing the journal to a paper or sharing results to communicate to your peers. This is stuff that can help combat misinformation in the public by having it being available to science communicators and people who are working to share these results openly. So yeah, so open science doesn't only involve researchers. Many other stakeholders are affected by the outcomes of open science. I would hope that, in general, our science has effects on everyone, but by practicing open science, we have a more direct connection to the people who to more communities and stakeholders. So anyways, yeah, so it's nice. They give you some thought activities. There's also, a very nice example when not to be open. And that's, let's click on that. Let's unpack this one real quick. It's because I don't quite remember this one, Chris. I don't know if you do. There are barriers. And so in infrastructural barriers and things like that. Let's see, learning objectives, recognizing your own fears. There are when not to be open. There are times when the biggest reason why you wouldn't want to be open is if there are aspects of the data or the methods or the way you're doing the science that programmatically or institutionally require you to not share that. And certainly there are some, results based on classified data, or there are also there are many mistakes. So where if you're working with human subjects or you're working with a community that's impacted, there are aspects you want to protect your partners in that research and the people if you're working with human subjects and things. And so there are aspects of why you wouldn't want to be open then. Certainly if you're trying to improve medical research for people overall, someone's personal medical history shouldn't be open. Either way, so they have your quizzes and things like that. These can take hours. Sorry, it took me so long to answer that question, but I didn't forget it. It took me about 16 hours to finish this. It took me 2 full working days to finish all of these trainings.
Is that one module or the whole certificate?
The whole thing.
Okay.
Beginning to end. Those of you who are more familiar with this, you can go through it and skim it real quick and be like, hey, okay, this is obvious. Okay, blunk, 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 blunk. And then just focus on the bits that you think are important or, or the part that you're not familiar with. I know people who kind of blaze through this in a couple of hours. But again, they're the Marcus Hughes and Chris Loader types who've spent a lot of time already doing this. Me, I really wanted to understand it, and I also, since I was on the Goddard Open Science team, I wanted to serve as to help. I wanted to review all the things in the modules just to make sure that I could, I really saw everything. But yeah, but it's definitely it's worth it. I really recommend you do the first one, Module 1, and then you might choose let's say you're not like a big into code development, but you might want to actually, let's see, modules. Oh, I'm having trouble navigating this thing. Modules. There we go. But everyone is involved in open results, and you might be involved in open data. And if part of your research is creating data products for people, it gives you great guidelines on how to publish and share data, and also make a plan on how to do that. Let's see, are there other questions, Sarah?
Yeah, there's one here from Marcus, who can go to the mic if he wants.
Hey, Barbara. So Chris completed it, I've completed it in the Punch Sock, and we're just wondering, how do we advertise that we're completing this? Should we put it on our GitHub page that like 3 or 4, or how many members of the SOC have completed it? Or like, do we break it down by which module we've completed? Like, what would you suggest?
All right, so Sarah and Craig have tasked me with making an open science page on the Punch website. Again, the fact that we are really being the test case for open missions, and we do have a draft open science page for Punch. I think the place we want to do that is on the Punch website under Open Science, advertising our team members that have completed it. You can also share your badge. I think you can, yeah. If you on GitHub, you can. I haven't done it. I think you can kind of attach the badge to your handle somehow.
It was a little complicated, but I found a way to like make a little picture and then have a link to the certificate.
Excellent, excellent.
And so if someone is interested in that.
Yes, thank you, Marcus. You're the best. Okay, yeah, that would be lovely, because you also want in your online developers presence, it's nice to advertise that you've completed TOPS training. It's still not quite done. One of the things that these modules are very nice for training. They're not very good references. Like, I need something that I can just go and just give me the bit about, there we go. Yeah, 62 results, and I'm like, oh, can you just give me the document that has this stuff without me having to go through all this stuff and find it, and so right now, most of it is really you have to be here, and I'd like to have something that's more portable and shareable. But they're still working on that stuff. But yes, Marcus, that's great. Yeah, if you can help me do that, I would really appreciate it. And then we can put on the Punch website, because it's not on here, I don't think. So.
So if I get 2 days, I really want to spend it writing a paper. Can I take the fast track ones instead? And what's the difference between the fast track
Oh,
and the
you're
OS 101?
correct. Yeah, it's true. There are fast track ones. Let's see if I can find. Unfortunately, like I've already completed them, and so I should. Actually, let's just do this. This is a sneaky thing. I have 2 browsers. There we go. I keep 2 browsers, one where I'm me and one where I'm a rando. And so yeah, so it's here, and then yeah, so this is what you get if you don't have if you haven't registered yet. And then here is yeah, so Craig is right. There are fast track modules that you can go through. You can take if you enroll, what it does is it puts it on your dashboard and it tracks when you're done, and then yeah, and then you can go through the fast track bits. And that's really useful for other people. Yeah, thank you, Craig. I forgot to mention that. Fast track, you can get through that in half an hour. It is really fast, and it doesn't have as much interactive stuff, but it's got the info, and if you're like, you know what, tell me once, I got it, I'm good. You know, you can fast track it. That's fine. I enjoyed the discussions. This was not developed by a single team. NASA had an opportunity, and people proposed to be the people that developed these different modules, and so they had experts in the outside in the general more broad community responsible for these modules. So they did put a lot of work into the interactive stuff to really bring this stuff home. But yeah, so if you want to get through really quick, a couple hours should be fine.
We got a question here from Chris Aurora. Chris, do you want to go to a mic or do you?
Hi, Chris. Mm-hmm. Yeah, that's a very good question. The one thing I can tell you is that it's not just it's proposed, published, perish, right? And if you are proposing, if you have TOPS training and it's very clear that you are and this is the nice thing about the TOPS as well, is that it gives you a way that you can do it end to end. And so it's hard, sometimes it's hard to do it at the end and be like, oh, here I am, now that I'm done, I'm gonna make this open science. Whereas if you started from the beginning with the practices of proper documentation, a clear consideration of how you're going to share and make the data accessible, if you do that from the start, it is a little easier. I'm assuming that's, you probably already knew that, right? I mean, yeah, from the way Chris asked the question, I was like, Chris already knows the answer. But yeah, it does help you. It's a lot easier to do it if you plan it as infrastructurally in the way that you approach your research, even from the point where you start to think of it and propose it. It is hard to kind of do in retrospect. But overall, it will help. And again, like I said, it's going to be harder to win a proposal if you do not, because more and more of the opportunities, if you read them, specifically mention aspects that are clearly outlined in this training, and more journals are starting to require, because of reproducibility and open access, aspects of this. And so in the long run, it will save you time. If you're not required to do it, it's always going to take you more time. But I think it's the more you get, since it's going to be required, this is going to help you.
That's a good point. Thank you.
Okay, we have a comment here from Chris Lauder, and we're coming up against the end of time. So, and then I think Craig had some final words. So maybe we can go to Chris, or no, you don't want to. And then maybe Barbara, you can wrap up, and then Craig wants to say something at the end, I think.
was just that I remembered the one thing that popped out to me was about permissive licenses.
Yes.
That my gut instinct was always like, well, I'll just do like a GNU license or something that prohibits commercial use, because who's going to use the scientific work for commercial use? And I think that was something that the training was like, oh, maybe this is not always the best kind of copy or
Right.
kind of license to use. The more permissible it is, yeah. Anyway,
Yeah, that
that was
surprised me too. Yeah, and it does help. And again, if you're going to propose to an opportunity and you're planning on licensing it, read the license part, because some of these opportunities are like, sorry, it's got to be Apache 2.0 or nothing. And so you can be as creative as you want, but if the AO explicitly says Apache, it's good to know that. Good to look for that. Compliance number one should always be your top priority, right? Okay, so Craig, yes.
All right, let's see, I want, it may be preaching to the choir for the people who are here in the room and care enough to be here. This stuff is really important, and for most of my career, we've kind of had a hodgepodge of ideas about open science and open source, and there've been a few folks like Barbara who've been advocating all that time, but having a standard curriculum is a really big deal. It's important globally, and even though going through an OS 101 might seem like a waste of time, to be blunt, it is not a waste of time, right? Making sure that we're all on the same page about standards and how to share and what it means to do open science is important globally as well as locally. So I'm really pleased that there are fast tracks, and I'm especially pleased that you're willing to evangelize this to us and to the community at large. So thank you for being here.
Thank you.
All right, folks, so we've got an hour now to go look at the posters and hang out, get a little sunshine, and we'll see you back at 2.
Great. And I do have an open missions poster out there, but that's if you have time to only see one, please see Velmir's poster. It's awesome.
Well, it's close enough to 2 o'clock, so I think we can get started on the next section, section 3, which is on cross-scale analysis. And the first talk will be presented by Raphael, and his talk will be on the 3D solar wind mapping for the PUNCH mission.
Okay, hello everyone. I am Raphael Atier. I am co-leading the PUNCH Working Group 1A about the flow tracking of the ambient solar wind. And we'll discuss today the 3D solar wind mapping for the PUNCH mission. And we I guess all know why we're doing that. But I'd like to personally show what are my personal interests in that work. It is mostly to understand the interplay between the corona and planetary environment. And I'm always amazed by the fact that very small changes near the sun's surface can lead to planet-wide space weather effects. We plan to address through this work of flow tracking the critical lack of flow maps in the solar wind with quantifiable uncertainties. So as you have seen before from my work, a lot of the flow tracking has been sort of trained and adapted so far using the Stereo Core 2 deep exposure campaign that has been processed by Craig DeForest. However, these are a work that would be constrained from 5 to 15 solar radii, and we do plan to test further with the other imagery from Stereo before we can finally put that into the pipeline for the SOC. And so I'm going to talk about the current status of that work. So first of all, to maybe make sure that I don't lose anyone, because I got these questions 2 days ago, this flow tracking work is tracking images showing the total brightness for Stereo. So these are a time series of images where the brightness is a scalar field. And the algorithm that's going to be in the SOC and provide flow maps are the correlation-based method that Craig had developed for the paper in 2018. And we're adapting that to go into the SOC. The reason for selecting a correlation-based method over my other method called ball tracking, I'll talk about that one in a few slides, is because we have to satisfy the basic NASA requirements for delivering these flow maps, and we need to deliver dense flow maps. And if you remember from the ball tracking method, ball tracking can only deliver sparse flow maps. So for that reason, we choose a correlation-based method because that's the one that can deliver a data point at each single grid point. However, in addition to the correlation tracking that's going to be in the SOC, we will make available the ball tracking method that's going to provide a higher level of granularity in the flows. So if you're interested in having more accurate but more localized measurements of the solar wind speed, then you will be able to use ball tracking, and a full documentation will be provided in addition to the one for the correlation-based method. So how does that ball tracking work? The ball tracking method is coming from a method that I developed called magnetic ball tracking, originally made for tracking magnetic elements in magnetograms. That method got hit by serendipity because it turned out that it could very well track the little blobs and bloblets, such as the periodic density structures that we see in the Stereo Core 2 imagery. And so I adapted that, and we are able to actually track very accurately wherever we have those plasma blobs moving coherently. The way we assess the accuracy of that tracking method is actually with the data themselves, so that's actually quite interesting to do because we don't need a simulation for that. We do that by by extracting all the different sort of ellipse-shaped blobs, for which we will know for each of them We know the centroid, which corresponds to the local extrema in that density structure. And building this way a training set of sort of ground truth, then we're able to tell how bad or how good we are doing in the tracking, and in doing so, provide error maps for each single measurement. So this is an example of such tracking after some background removal, so that the plasma blobs really stand out from the background. I'm only showing here with those blue labels a subset of what is being tracked, but what is actually being tracked, I mean, there are much more there that I can show, because otherwise these red crosses and labels would be all over the place and we couldn't see anything. All right, so on top of that, the algorithm got struck again, one more time by serendipity, when the CME folks noticed that the ball tracking algorithm was actually also tracking pretty well CME leading and trailing front. So we started to look at these CME events, and I'm showing here an example of the periodic density structures being tracked by ball tracking and giving us a radial velocity. So that's the black line that you see at the top. And overlay on that, you can see let me try to point that. All right. Okay. So you can see here an example of a CME being tracked. And I've overlaid here the specific speed of that CME by selecting with a high level of granularity the variables that were tracking the density structures of that CME, and thus being able to see a clear difference in with respect to the ambient solar wind. So this is a relatively small, relatively slow CME. And we have, of course, other faster CMEs, and I'm still in the process with the help of Heather and other CME experts, still in the process of identifying these different CMEs, because I'm not myself a CME expert, so I'm not able to really pinpoint all of them. And so here specifically, I'm showing the variables that were used to show the velocity and associated with the error bars, which represent more a time variability of the position of the balls within the CME structure. This work is still in prep and will be published by Maher Daye in probably the topical issue for Punch in solar physics. So finally, the end product that we will be delivering through the SOC by the correlation-based method will be in form of a binned profile of the velocity. So this is what such data product will look like. We will have azimuthal profile of the solar wind speed averaged over some radial bins. And the minimum we have to provide is about 4 radial bins over between about 5 and 180 solar radii, but this is just a minimum requirement. We will be able to do much more than that, of course. So, so far, these tests of flow tracking have been done without the information of the polarization. With Punch, of course, we will have the polarized brightness. And we are in the process of coordinating the efforts from people doing tomography to augment both the tomography itself and to augment the flow tracking itself. The end result of that is to basically convert these sort of 2D representation of 2D projections of the velocity into volumetric view of the velocity, with the geometry, the 3D geometry being, of course, constrained by the geometry of the Thomson scattering effects and the Thomson sphere. So this will not be a full big cube full of volumetric data, but it will be geometrically constrained. However, the end goal will be to really go beyond just a simple 2D projection of these velocity flows. So I've been directly interacting with Bernie Jackson And I am welcoming every other people who are doing tomography if they want to, if they see that there is a good use case for their work with the flow tracking. I would be happy to provide the output of my method before the launch of Punch and or after. The next work before the launch of Punch will be to continue performing sanity checks and accuracy estimates by using the gamma simulations of CMEs and large-scale structures propagating in the solar wind, and that stand out over the background solar wind. We will also, we intend to use the forward modeling toward punch-like observations with other kinds of flows, such as MHD jetlets. And finally, and I invite you to see the poster from Valmir Moraes and Vadim Mariski about the flow tracking challenge, where Valmir did an excellent work of reproducing very realistic stereo-like imagery, where the ground truth velocity is known, and we can use that to test the accuracy, not just the precision, but the accuracy of the tracking algorithms, not just the correlation tracking, but also the ball tracking, or any other method that you may think of to track the flow fields. So just to summarize, on the one hand, the SOC will deliver this dense Euler flow field using the correlation-based method, which will provide accurate average speed of the solar wind in the heliosphere over at least 4 different radial bins until 180 solar radii. And over, currently we're targeting about 1440 azimuthal bins, but that may be refined depending on the accuracy estimates we are doing with stereo. And it will provide a really large-scale solar wind acceleration and deceleration with radial distances. If you need more granularity, you will be able to go to the ball tracking, to use the ball tracking method with or without the 3D tomography to get for example, forecast of heliospheric structure arrival, for example, at Earth or wherever you're interested in. And then you will be it will help to provide various heating or momentum parameters over heliospheric distances used in 3D MHD models. Thank you.
The next talk will be given by Rohit, and it is titled The Alphane Transition Zone Observed by Parker in the Young Solar Wind.
Since Raphael finished early, do I get a couple extra minutes? All right, so I will be talking about some results based on in situ data analysis and global modeling that I think provide some interesting context for Punch's science goal to map the Alphane surface and study the processes around the Alphane surface. The Alphane surface, of course, is, I think, a useful answer to the question of what is the boundary between the solar corona and the solar wind. As the flow accelerates away from the sun, it eventually passes, it becomes larger than the speed of a local Alphane wave, and that's the definition of the Alphane surface. And of course, we have a Punch working group, which asks what are the evolving physical processes of the Alphane surface. So I'll have a very quick introduction, and then I'll talk about some results comparing Parker Solar Probe observations with global model, and then hopefully I'll be able to get to some new analysis that looks at some properties of sunward and anti-sunward Alphane modes, which are important for Punch's efforts to basically map the Alphane surface by tracking sunward motions, which you expect below the Alphane surface. So just some quick context. In 1D, the Alphane surface becomes an Alphane radius, RA, and in this model on the right, it's a 1D model, and you can see, do I have a pointer here? This one. Sorry. Can I go back?
The bottom button is back, and then if you hold the top button, it's the laser. It'll just take a second.
Okay.
There you go.
There's a lag. All right, so the 1D model here shows an accelerating solar wind profile, and you have the alphane speed decreasing with distance, and this point of intersection is the alphane radius. This is important for a number of reasons. First, below the alphane surface, you can have propagation of information from the corona towards the sun, because your sunward propagating alphane wave can actually move toward the sun despite being advected away from the sun by the solar wind flow. Right? It's also important for astrophysics in general, because you can have strong transfer of angular momentum from stars to their atmosphere below the alphane surface or radius. And it's also possibly important for onset of in situ dynamics like switchback formation and flocculation, because you can have things like Kelvin-Helmholtz instabilities that are able to get triggered once you're above the alphane surface. So I think everyone's familiar with these types of pictures of the alphane surface, where you get these from 3D global models. The pink curve over here is the alphane surface. It's about 15 to 20 solar radius, solar minimum on the left, solar maximum on the right. So there's some structure over here, large scale structure, but there's recent work which suggests that it might have the alphane surface might have much structure at much finer scales. So these two plots are based on extrapolations of in situ data. On the left, Ulysses data at different heliolatitude, and you extrapolate the data towards the sun, which allows you to infer a location for the alphane radius at each latitude. And you get this kind of highly corrugated irregular structure. A similar plot, this time showing the ecliptic plane. This is the Parker Solar Probe trajectory, and you can again infer this black curve as the location of the alphane surface. So you get this kind of highly corrugated structure. But of course, single spacecraft data are limited in what they can tell you about the broad properties of this region. So this is some work that we did a couple of years back. We took a global solar wind model which had turbulence transport, and if you include the effect of turbulence in your calculation of the alphane speed, then you sort of lose the idea of an alphane surface, and you get this patchy and fragmented alphane zone, where close to the sun you have purely subalphanic flow in beige over here, and then gradually over this extended region, the flow turns from subalphanic to superalphanic until it's eventually purely superalphanic. So we've compared this with some data, and you get reasonable agreement, but let me skip this slide and move on to some new work. So this is just this was just published a couple of weeks back in MNRAS. Here we use a lot more PSP data because PSP is now regularly measuring subalphanic solar wind. And so we used encounters 8 to 14, and we identified subalphanic periods that were at least 10 minutes long. And so this plot on the right shows, it's a visualization of the kind of subalphanic and superalphanic intervals that you see in PSP as a function of distance. So each encounter of PSP, starting from the 8th one, gets two lines over here. The bottom line is the incoming orbit, and the top line is the outgoing orbit. And these blue segments are superalphanic segments, and the red segments are subalphanic segments. So you can see this transition from blue to red as you go close to the sun in later encounters. And in the background, I'm coloring this by the filling fraction of subalphanic points. So you go from almost no subalphanic points out here to almost 70% of the data being subalphanic below 15 solar radii. The plot on the left, I've got a comparison of the model result with this PSP data for the filling fraction. The model result is green, and it agrees pretty well with the brown curve that you get from PSP. So here's some more analysis of the properties of this alphane zone measured by PSP. These are basically joint distributions of the interval duration and the distance at which a subalphanic interval was encountered by PSP in the plot on the left. So the color over here maps to this scale over here, so it's basically giving you a number of intervals within radial bins and bins of interval duration. And you can see that out here, you only see these short duration subalphinic intervals. But as you go to below 20 solar radii, you start seeing some longer, almost a day-long subalphinic intervals at the top over here. But the kind of interesting thing is that you continue to see these short duration intervals even when you're at these short distances close to PSP perihelion. And if I compare, if I make the analogous plot by flying a virtual PSP through my Alphane zone model, then this is the kind of distribution that I get. So there's some similarities in the general pattern, but one interesting difference is that in the model, you only, in this bin between 10 and 15 solar radii, you only see the long duration subalphinic intervals. So this is kind of suggesting that in the model, this whole Alphane zone has kind of shifted a little bit to larger helioradii. So in the model, the virtual PSP has already sort of entered this deep subalphinic region where you only see the long duration subalphinic intervals. So this is also in effect a prediction for later orbits in PSP. You might see in the final orbits just long duration intervals over here. And by the way, this kind of increasing frequency of short duration intervals was a prediction of the Alphane zone picture. So it seems to be consistent with this kind of fragmented and patchy Alphane zone. I wanted to show this plot about bottom right over here about shows what happens to this distribution when you use just your global solar wind model without accounting for the turbulence. And so you get this kind of distribution for the subalphinic intervals when you fly a PSP through it. So clearly the model with turbulence added agrees better with the PSP data compared to the model without turbulence. So it's just interesting how much structure and variability you get when you account for the turbulence and how much closer it is to the observations. Still about more than 5 minutes? Okay. So this plot over here shows the Mach number of these identified subalphinic intervals in PSP on the left and the simulated data from the model on the right. And you see, again, similar patterns, and there's an interesting correlation between long durations and low Alphane Mach number. So the longer duration intervals measured by PSP tend to have lower Mach number, and the same is true for the model over here. So here I've got a bubble plot type of visualization of the Alphane zone measured by PSP. In the left, this is now in the solar, basically the ecliptic plane, the plane sampled by Parker Solar Probe. And each of these bubbles represents one subalphinic interval measured by PSP. The diameter of the bubbles is proportional to the interval of the duration of the interval. And these intervals have been sort of randomized in longitude, heliolongitude, to better visualize them. But you can still see the radial trend, which is authentic. So you see the speckle of short duration intervals out here. You can see them a little bit more clearly when you scale the diameter of the bubbles by the log of the duration. But when you start coming below 20 solar radii, you start to see these really long duration subalphinic intervals. But the short duration patches, they endure even at these short helio distances from the sun. So moving on to the second topic now, which is about sunward propagating Alphanic signals. So as I said, if you're below the Alphane surface, you can actually have propagation of features towards the sun via the Alphane wave. And this has actually been used by DeForest et al. To infer a location from the Alphane surface by analyzing stereo data. And this is the idea, this is one of the ways that we might be able to infer a location for the Alphane surface using punch. But it's important to understand, to basically have a context of what kind of Alphanic motions you're seeing in C2 in this region using PSP. And so the quantity I'm using to study this is the cross helicity. For people that are not familiar with it, it's basically a normalized correlation of velocity and magnetic fluctuations. So we know that Alphane waves have correlated velocity and magnetic fluctuations. So the sign of the cross helicity gives you information about sunward versus anti-sunward propagation. And if you can do this thing called sector rectification, where you process the data so that if the cross helicity is positive, that corresponds to anti-sunward propagation, and if the cross velocity is negative, then you have sunward propagation. And in addition to the direction of the Alfvén waves, the cross velocity also gives you information about the relative strength of the anti-sunward and the sunward mode. As you can see from this definition, where Z plus is the strength of the outward mode and Z minus is the strength of the sunward mode. So this is a plot made by a grad student at UD, Victoria Wang, where she looked at 10 years of ACE data and made a distribution of the average cross velocity for 12-hour intervals, thousands of 12-hour intervals, and made a histogram of this cross velocity. So what you see at 1 AU is an average cross velocity of 0.54, which is moderate cross velocity, not too high. But you can see that the most probable value of the cross velocity is pretty large. So this is telling you that it's dominantly outward propagating waves. But there's this interesting subset of the intervals where you actually see negative values, dominant negative values of the cross velocity. So these are intervals where the dominant Alfvén mode is sunward propagating. So what do you see when you look at PSP data? So this was done by another grad student at UD, Shoham Roy, and he looked at PSP encounters in the distance at around 15 to 30 solar radii, and he separately computed the cross velocities for super-Alfvénic and sub-Alfvénic intervals. And so what you see is that the average cross velocity has increased a little bit in PSP encounters. The subset of intervals with sunward motion, dominant sunward motion, has also decreased. And if you look at the sub-Alfvénic intervals, then you see that the cross velocity is now much larger. It's 0.71, so significantly larger. And the subset of intervals where you have sunward propagation as the dominant propagation is basically disappeared. So this is telling you that there's almost no sub-Alfvénic intervals where you have a dominant Alfvén mode that's propagating toward the sun. However, this is just showing you the trend from 1 AU to 0.1 AU, basically. But these results don't indicate that there's no sunward propagation. It's just subdominant. So you can see this when you actually compare the strengths of the Z plus and the Z minus, which is the anti-sunward and the sunward Alfvén modes. And you see that when you go close to the sun, then the anti-sunward mode is getting increasingly stronger. You see the same thing when you look at spectra in a sub-Alfvénic interval. The anti-sunward mode is the blue curve over here, and the sunward mode is the orange curve over here. So you have an order of magnitude of difference between the strength of the sunward mode and the anti-sunward mode. So that's, I think over the next year, as the working group for the Alfvén surface, we should really try and see what kind of analysis we can do with punch, given these constraints on the sunward motion of Alfvén waves. So let me wrap up by saying that the first section of the talk, I showed that the turbulence implies an extended spatial region where you have the transition from sub-Alfvénic to super-Alfvénic flow. PSP observations are consistent with a patchy and fragmented morphology for the Alfvén zone. And some preliminary analysis that I showed with PSP indicates that the intervals with dominant sunward propagation of Alfvén waves are going to be rare below the Alfvén surface. And this also has implications for nonlinear interactions and turbulence, and it's kind of consistent with a picture in which turbulence becomes more developed above the Alfvén surface, and it's less developed and weaker below the Alfvén surface. Okay, that's it.
The third talk will be given by Yan, and she will be talking about data-enhanced modeling of magnetized turbulence.
Hi, this is Yan. Today I'm going to be presenting some ideas of data-enhanced modeling of turbulence. So we know turbulence is a highly nonlinear phenomenon, and here we just use hydrodynamic turbulence as an example. And the equation that we want to solve in hydrodynamic turbulence is is the Navier-Stokes equation, or we call it momentum equation. If we, you see there is a nonlinear term, v dot grad v, right? If we just ignore the right-hand side terms and just keep the time derivative term and the nonlinear term, and we start with the mode at wave number k, and you can see at the next time step, the 2k wave number mode appears. And you can imagine as the time goes on, they're gonna have more higher wave number mode appear as well. So that is saying, because of the nonlinearity, the turbulence is composed of multiple temporal and spatial scales, and also it also always appears to be chaotic. And if you compute the energy spectrum, the figure on the right is the magnetic energy spectrum in a solar wind from Helios. You can see the spectrum is very broadband, and you can also see over several range of scales, you can find those power laws. For example, over on the right-hand side of the figure, you can see over a range of scales, there is a f to the -5 That's also the indication of turbulence. Here, I just want to show you a simple example. It's a 2D compressible MHD simulation. This simulation is initialized with magnetic and velocity shear over a very thin shear layer. As the time goes on, you can see this animation shows the time evolution of vorticity. So as the time goes on, you can see those roll ups, and you can see finer and finer scale vortex developed. That also saying if you want to look at turbulence, you got to be careful. You need to investigate all the physics at different scales. So turbulence involves a wide range of temporal and spatial scales. That is saying if you want to do turbulence modeling, that could be very challenging. There are different turbulence modeling approaches have been developed over the years. Here, I just roughly decompose them into 3 categories. Here, I still use the hydrodynamic turbulence as an example. The first one is the direct numerical simulation. And the field that we want to get is the velocity field, u, and the equation to be solved is the Navier-Stokes equation or momentum equation. So in the DNS, turbulence is resolved at all scales with a very fine grid, and at very use a very fine grid and very small time steps without any models or approximations. The next one is the large eddy simulation, as you can tell from the name. In LES, turbulence is resolved at large eddies and modeled at small eddies. So the field, the first step in LES is to define a filter scale. Let's say it's L. And we filter the velocity field. So you get U tilde, that's the filtered velocity. That is saying you use the filter, or low pass filter, to eliminate all informations at small scales, just to keep informations at large scales. That's what U tilde tell you. And the equation you're gonna solve is the filtered version of Navier-Stokes equation. So you can see on the right, there is a blue term, that's a new term gonna appear in LES. That term represents the effect of small scales on the large scales. That term is called subscript scale stress. This stress needs to be modeled, otherwise this equation is not closed. And then the next one is the Reynolds average model. In this model, we applied the Reynolds average to the velocity field. So the velocity field can now decompose into the mean flow, that's the U in the bracket, and the U prime is the fluctuation. And the field that we want to get or we want to solve in RANS is the mean flow. And you can also see in the equation there is also a new term, the blue one. So that term represents the Reynolds stress. It represents the effect of the fluctuation on the main flow. So this one is also this stress also need to be modeled. So we have different approaches. Then we also have a lot of diagnostics to assess the performance of those approaches. Here I just show some examples. The first diagnostic I'm going to use is the level of description. We can still look at the energy spectrum. So this is a typical energy spectrum in turbulence, and the scales is roughly decomposed into large scale or energy containing scale and some intermediate scale, we call it inertial range, and very small scale, that's the energy dissipation scale. So we know in DNS, in direct numerical simulation, we resolve all the scales without any models, right? So that is saying the DNS can resolve down to the smallest scale, the energy dissipation scale or Kolmogorov scale. In the LES, we modeled the small scale and resolve the large eddies. So that is saying the LES can resolve down to inertial range or intermediate scale. And the range, we average out all the turbulent fluctuations. So the range can only resolve large scale mean flow. So you can see the different level of description from different approaches. And the second criteria is the completeness. A model is complete only if its equations are flow independent. That is saying in that model, one flow is distinguished from another only by its only by its material properties like viscosity, initial condition, and boundary conditions. So in this sense, DNS is complete because those equation does not include any models, right? The LES and RANS, we need to find some models for the subgrid scale stress, linear stress, and those stress or those models are flow dependent, so they are incomplete. So in this sense, the LES and RANS, they are incomplete models, so their application could be very useful only in very limited class of flows, but it's still very useful. The third criteria is the cost. We know DNS need to resolve down to Kolmogorov scale, so it's very expensive. And if we want to simulate a turbulence with a high Reynolds number, that means the cost is going to be higher. The LES can reduce the cost by skipping the small scale features. But it's still very high if we want to simulate turbulence system with high Reynolds number. And the RANS, we know it's only resolve the large scale mean flow. So it's much more cost effective than the other two approaches. So what kind of method that you're going to use really depends on what questions and what point you really care about. Okay. And here is just an example to give you a rough idea what kind of picture that you can get by using different approaches. The contour on the right showed a velocity distribution for a turbulent jet by using RANS, LES, and DNS. So you can see all the three can provide some useful details of the velocity field. But we also know DNS is more detailed than LES. LES is more detailed than RANS. The figure on the left shows you the time series of velocity by using different approaches. So you can see the results from the RANS is very smooth. So you cannot even get any those fluctuations like DNS, right? So, but the LES is feasible, and it's more feasible than DNS, and still keep some features, the turbulent features. So we might want to do that. In the LES, the critical, the challenge is to find a model for the subgrid scale stress. This stress represents the small scale effect on the large scale. So to derive the model for this stress, the scale invariance property of turbulence has been used a lot. The scale invariance property means certain features of the flow remains the same in different scales of motion. So such a symmetry is, can be interpreted as a very simple relationship between a small scale and large scale. And this, the idea of the scale invariance dates back to Richardson in 1922, and he described the scale invariance in a very qualitative term in this rhyme. Okay, and on the right, I list some LES models like the standard Smart-Grinsky model, similarity model, and dynamic models. There are also several other models. Werman made a comprehensive comparison between different models by using a lot of diagnostics. In this table, minus means bad, 0 means reasonable, and plus means good. So you can see the M1 is the pure Smart-Grinsky model, and M6 is the dynamic model. So you can see M6 really improves than the M1, the pure Smart-Grinsky model. So I'll just show you a very obvious limitation of the Smart-Grinsky model. In the Smart-Grinsky model, the stress is modeled as this one. So it's proportional to mu t and Sij. Sij is the filtered, is the resolved strain rate tensor, and mu is a Smart-Grinsky coefficient. So by using the stress, we can get the energy transfer across the scale. So in a Smart-Grinsky model, the energy transfer rate is always positive. But we also know in any turbulence system, the local energy transfer rate or local SGS dissipation could be negative, as you can see from the figure on the right. It can be negative, and so it's not positive definite. That is saying the Smart-Grinsky model is obviously a flaw in the sense, right? So we need to develop other models. Then we have a lot of approaches, turbulent modeling approaches. We also have a lot of experimental data or observational data. How can we make use of the strengths of the numerical modeling and the experimental data? The data assimilation could be a good idea. So the data assimilation gonna assimilate the experimental or observational data into the model to improve the computational computational model prediction. It has a long history in numerical weather prediction research, but I think in its application in turbulence, it's still at a very early stage. There are a lot of data assimilation methods. Here just to show some examples, like the four-dimensional variational method. This one is based on the optimal control. So U is the model prediction, V is the data, and J is the cost function, like measure the difference between U, the model prediction, and the target data. The idea is to try to assimilate U into the simulation of U to try to minimize the J. And also at the same time, the U need to satisfy certain constraints because we know U is the velocity field in a turbulent system. Then it got to satisfy Navier-Stokes equations, right? So actually, we are solving an optimization program with constraints. The constraint is Navier-Stokes equations. And there are also other methods, like example common filter method, and the simplest one could be direct substitution method. We still use the energy spectrum as an example. So we have the data over at very large scale. Let's say from very small k to km. Then in the data assimilation method, we just replace the data we replace the model data with the real experimental data over very large scales, then try to improve the prediction. Here, just show some examples. And the idea is we can use the data assimilation to improve the prediction of LES. And we can also use the data assimilation to reconstruct the small scales in a turbulent. So this is summary. We know resolving all the scales is challenging, but LES could be useful. The data assimilation can be used to predict to improve the prediction and reconstruct the small scales. And we know punch can give us information within the upper end of the inertial range. So that is saying punch can give us some data at large scales, and we can make use of punch data at large scales, and also try to assimilate the punch data into those turbulence modeling approaches to try to improve the prediction of those numerical models. That's it. Thank you.
So the last talk of the session will be given by Rahul, exploring the relation between transverse energy injection scales and plasma properties in the corona.
Hi everyone, I am Rahul Sharma, and this is the project, something what I was being involved with Nikita and Richard Morton. Yes. So in this particular project, what we are doing is basically talking about like how the plasma and the magnetic field conditions in the solar corona affect the wave energy injection scales. So wave energy injection scales, or what we primarily known as the perpendicular correlational length scales, are kind of like very much important when it comes down to the turbulence theories and like how the waves are going to provide the energy for the heating purpose and stuff. So here on the left, we do have the movie which is showing from the comp instrument. So so it is the line of sight Doppler velocity movie. So just by a visual inspection, you can see waves are kind of everywhere. So they are being observed into the open field line structures, in the active regions, in the closed field topologies. And the general idea is that these waves are being originated in the lower solar atmosphere, where the photospheric motions shake up the magnetic field lines. These waves do propagate along the magnetic field, and while doing so, these waves are going to interact with the inhomogeneous solar atmosphere. So the inhomogeneities in terms of the magnetic field and the density, they do kind of result into the partial reflections. And these partial reflections generate the counter-propagating waves, and when these waves are going to interact with each other, there will be turbulence. And this idea is at the center of the Alphen wave-driven turbulence models, and these models were kind of like fairly in business about explaining how the solar corona is being heated up, and also what drives the solar wind, how the acceleration of the solar wind happens. So general idea about, here is an expression about the volumetric heating. Can we actually just click on here, maybe, which is going to expand it? Yeah, that's it, thank you. So here is an expression for the volumetric heating rate in these turbulence model, where CD is a constant, Z plus Z minus are the Alsacer variables that account for the fluctuations in the magnetic field as well as the velocity. And this parameter, L perpendicular, is what we call the correlational length scale. So correlational length scale is basically going to tell us about what are the biggest scale of the eddies that will be present due to the waves. So if we look at one of the kind of these very generic the kind of these plots about this turbulence model, we have the energy containing regions where these large scale eddies are eventually going to break down to small scale eddies until they arrive at the dissipation scale, and where the actual heating or the solar wind energization is going to happen. So this large scale is basically what we call the perpendicular correlation length scales. And these scales were being studied very fairly in the solar wind community. So what they're going to tell us, this particular scale, is how much magnitude of energy is available for the heating or the solar wind acceleration, and where could be this energy is available, at what location it will be available. It does not tell about how that dissipation is going to happen or what amount of energy is going to end up into the dissipation process. So generally, in the numerical models, these are being chosen as ad hoc from the photosphere or over the transition region, and they can go from 0.1 megameter up until 10 or 35 megameters. So here is just a small cartoon about like how exactly these eddies should look like, because I will be showing these from observations. So if we are looking in terms of these hydrodynamic eddies, they're very simple. They don't have a particular shape. However, in the presence of the magnetic field are going to stretch these eddies, and it will have a preferential direction. So the direction which is along the magnetic field will be called the L parallel, which is parallel to the magnetic field, and the perpendicular component is what I refer to as the perpendicular correlation length scales. And as what we can expect, the perpendicular correlation length scales would be way smaller in magnitude as compared to the parallel. So here are the kind of the observations what I have been using so far. So these comes from the COMP and the UCOMP instrument, which is located in Mauna Loa in Hawaii. It's a coronagraph with a spectrometer and the polarimetric capabilities. And here are basically the cadence and the spatial sampling, as well as the upgraded instrument, which is slightly better in terms of the spectral resolution and also the field of view that is going to cover. So in my study, what I generally used is the Doppler velocities, and for this particular project, we have compared the outcomes with the background conditions, which is coming from the numerical models. So in the numerical models, we have used the STSW model, which is a part of the CORHEL, and the photospheric conditions, boundary conditions, are taken from HMI, and then all these outcomes were being forward modeled to match the observations that we got from the COMP instrument. So here is a basic overview how we estimated these correlation length scales. So we do have the Doppler velocity data from the COMP and the UCOMP instruments. We do know that the waves are basically following the magnetic fields. So for any given pixel, for the time series, we can take their Doppler measurements. And for the neighboring pixels in the Fourier domain, we can estimate the mean square coherence, and we can repeat these to the surrounding field of view. So the idea is to that scale where these waves are coherent is going to provide the largest scales for which the waves can have the energy that is going to get dissipated. So when we create some sort of a map, it looks something like this one. Here's the map, which is the coherence. We are taking 0.5 over the coherence over 0.5 as the kind of the threshold that we want to estimate the correlation length scales. So as expected, along the magnetic field, the correlation length scales, the parallel correlation scales are way higher as compared to those what we are getting in the perpendicular direction. So again, these elongated islands, we fit it with a 2D Gaussian function. Then from the 2D Gaussian, we got the sigma in parallel and the perpendicular direction. That is basically what we are now referring to, the correlation length scales. We can repeat this for the entire sun, and here we can get the global map for the co-coherence as estimates. So here, the perpendicular coherence is obviously having quite lower magnitudes as what we compare with the parallel co-coherence. Again, we had these kind of analysis done at the different times into the solar cycle, and again, using the data from the COMP as well as the UCOMP instrument, just in order to check that if the resolution of the data might have any effect on the estimation of the correlation length scales. So here we do have the outcome and the perpendicular coherence, and these are the probability density plots. And you can see that despite like taking at a different from 213 or 2015, 16 or 22, or even with a different instrument, we have all these plots which were being kind of like the peak was falling somewhere between 5 and the 10 megameter. So these are still the sigma values that we converted into the length scale using the 1/e folding, and what we got for most of these is got somewhere between 7.6 to 9.3 megameter, which is basically the scale for which for the supergranulation scales. So somehow the waves are getting reorganized themselves on the supergranulation scale in the corona. Now, moving ahead, the comparison, as I mentioned before, these estimates were routinely being done by the solar wind community, but they were very far away from the location where the wave energy is injected into the solar wind. So here we do have these cross which are coming from near the Earth, from the instruments on board the ACE and the wind spacecraft. These are the plus signs which are coming from the instruments that flown quite near to the sun, the Parker Solar Probe and the Helios. And the plus sign here is an exception because this data came from the radio measurements. So the Faraday rotation measurement, and the idea was to estimate how smooth is the coronal magnetic field, and that is the smoothness that they have actually found, and we have included it. So apart from it, this diamond is basically the only estimate that we have actually got for the correlational length scales near this whole solar atmosphere. There are two lines which represents two different models. So the dashed line is coming from the model from 1986 from Holweg, where they predicted that the correlational length scales should be proportional to the expansion of the magnetic field only. The solid line, on the other hand, comes from Steve's 2012 paper, where they have kind of extended the earlier model. So they do have the expansion of the magnetic field, but they also have the nonlinear coupling between the flows and the alpha wave fluctuations. However, both of these models were being designed for the homogeneous conditions into the solar atmosphere. Let's say the corona holds. However, the solar atmosphere is highly inhomogeneous, and if there is inhomogeneity present, then it can lead to the resonant absorption that can lead again to the concentration of the wave energy to the scales, which may be comparable to the length scales of the inhomogeneity. So to examine this, what we have done is basically taking one of the examples that we have got. Here we have got the perpendicular correlational length scales, the lines over it plot, what kind of the magnetic field topology was in there. So we have selected 3 magnetic topologies: the active region, because the magnetic fields are highly complicated, intertwined and stuff; the coronal hole, where the field lines kind of like being open and less complicated; and this is the loop structure at the base of a pseudostreamer, where the waves can be launched on the either foot point. So that could have a different mechanism of the counter-propagating waves. The second patch shows the expansion factor, which is estimated from the PFSS model. And here we can see that in the active region, the magnetic fields are very, very less expanded. In the coronal hole itself, we can see that there is a structuring in the magnetic field itself. And again, here in the loop structure, there are regions where there's very strong concentration of the magnetic field. On the top layer, these are the estimates which are coming from the observations. The first panel is the plane of sky component of the magnetic field that we estimated using the magnetoseismology technique. The second one is the density, the coronal density that we got from the line ratios from the comp instrument. The third one is the temperature, which is an average temperature for the observation duration, which is again coming from the DEM estimates from the AIA. The bottom panel is, however, coming from the model. Again, there's very similar parameters: the plane of sky component of the magnetic field, the density, and the temperature. However, you may notice that in the observations, we do have very fine scale structuring, but in the model, we don't have any. It is giving the background static conditions. So the idea is to then compare the observed correlational length scales of these parameters, just to identify what could be the leading parameter that is dominating the observed. As you have already noticed in here, that from these two models, which have already got the expansion as well as the fluctuation, our estimates are way higher. And this is something what we have not anticipated, so there is something more physical mechanisms that might have contributed that were never being accounted in these models. So having the absolute magnitudes, we also have the gradients in the radial directions. There's a radial gradient that we got on all the observations. So in the plane of sky magnetic field, the density as well as the temperature, and also on the models. And from the observations, you can see there are huge gradients, huge fine scale structuring that will be contributing to what we see into the observations of the correlational length scales that might be affected. I haven't got the gradients on the expansion factor because that itself is a change into the magnetic field condition. Here is a very simple, very back of the envelope analysis what we got. So it's just a first order approximation. So we have done a multiple linear regression model, And here we have on the left the perpendicular correlational length scale. On the right, we have got all the factors: expansion, plane of sky, density, temperature, and where C is the constant. And here, for 3 different regions that we have got the models and the observation model, the gradient, and the gradient in the model as well. In most of the cases, more of the dominating parameter, which showed most of the changes as compared to the actual correlational length scale, comes out the density. However, this is a very simple model which is very linear. However, in reality, it should be very different from expected. There could be a higher order terms. There could be a combination of these parameters that we have not taken into account. But a very simple approximation tells us that density inhomogeneities do have a very big role, primarily because they do kind of contribute to the reflection of the waves. More reflection waves, there will be more cascading, higher correlational length scales. Here is something that may be related in future to the Punch mission. So I'm taking this from the Craig's 2018 paper, and what they have found in the stereo observations from the 6 to the 12 solar radii is about these fine scale structuring, the density structuring. And these density structuring will have the dimension which is around 20 megameters. If you scale it down to the corona, they will be highly comparable to what we have got with the correlation length scales from the observations. So maybe in future, Punch can actually find these density inhomogeneities, and that may be explained that why the kind of the correlation length scales we got are way higher than what we expect. Here are the main conclusions, and thank you.
All right, so are we doing Slido now? Yeah, okay. You're not dismissed. You have to go sit. Can we have all the speakers back up here? So now we do the thing where we have the open conversation and we do the Slido thing. And Kurt's gonna run the microphone. And panelists, you have to press the button when you respond. And hold it, yes. Okay. All right, so let's see. Sam Badman, do you want to ask your question for Rohit?
Yeah, thanks, Rohit. Nice talk. The question, and I think Amy asked basically the same thing, is what part of the solar cycle is your model run from? Because the open flux can vary in the solar cycle, and that can basically shift the average alphane, the alphane speed curve, essentially. So is your model dependent on a certain magnetogram, for example, and have you looked at how that might vary through the solar cycle?
Yeah, very interesting question. I think right now the results that I showed you were from a solar minimum magnetogram, which we were using to compare with early PSP encounters. So it's like a very crude first comparison where we're using the same boundary condition magnetogram for 10 different orbits. So it's just to get an overall sense of what kind of patterns you get. The effect of solar activity on the alphane surface, we have looked at that in the model, and you can do it in 2 ways, right? One is if you use a tilted dipole type of a situation, and then you tilt it to 60 degrees or something like that to represent solar maximum. And what happens is that in these dipole type models, during solar minimum, these alphane surface dips closer to the sun at the heliospheric current sheet. And when you tilt the dipole, then you basically see more of the high latitude type of alphane surface, which is at slightly larger distance from the sun. So effectively, what happens in a tilted dipole model is that the alphane surface seems to be pushed out a little bit more, which also makes sense from the perspective of fast wind, sampling more fast wind in the ecliptic, because in the fast wind, the alphane speeds are larger, right? I mean, the speeds are also larger, but the alphane speeds are also larger. If I use magnetograms, in general, the effect of using a magnetogram is to pull the alphane surface a little bit closer to the sun, even solar minimum. And we think that's probably because the magnetograms have higher order multipole moments, which decay faster compared to the dipole. So you basically have a loss of magnetic flux sooner moving out. So yeah, but we would like to do more systematic comparisons of solar max magnetograms with PSP results from that time.
You can also look at in situ measurements of the magnetic flux. You can also see that varying the solar cycle, and it goes along with the magnetogram open flux too.
And then Yami, yours is related. Did you have a follow-on?
Yes, so yeah, it was pretty much related, but one of the things that I was kind of hinting at is coronal mass ejections, right? So I think the way in which the Alphen surface is thought of is independent of these very kind of these big perturbations, which are coronal mass ejections. So I was just wondering how you'd expect in terms of its coherence to remain, and then, you know, are you expecting kind of the frequency of these CMEs that increases to shift it out and kind of have this more breathing pattern?
That's also a very interesting question, and I think our model is pretty much restricted to steady state, non-transient type of solar wind. I think some of the long subalphinic intervals that PSP has seen, people have associated those with CMEs. So one effect that they seem to have is to create longer duration subalphinic intervals at larger distances. So it does seem to be pushing out I think Sam's done some work on that, and maybe Vamsi at APL has done some work on that. In our model context, we haven't been able to look at that so far, but definitely something interesting to look for in these orbits of PSP.
All right, next let's go to a question for Jan from Sarah.
Thank you. Yeah, and you mentioned a little bit about this right at the end, but I'm basically wondering, pulling it into Punch, what you were telling us about the scales of turbulence, you know, the ones that Punch is particularly looking at, and what's the new thing, or what do you think we're going to learn from it?
Yes, the Punch, according to the recent paper that we just submitted, I think the Punch data can observe informations down to very close to inertial range, but still not deep into the inertial range. So it's close to the large scale. So in this sense, I think we can talk about possible application of Punch data in models. For example, in RANS model, I know currently all the global modeling is like a RANS model. So in that model, we know it's a RANS model. So that is saying the Punch data have higher resolution than the RANS model, right? So that is saying we might be able to use Punch data to refine the models in RANS, in global modeling, because we know in the RANS model there is a RANS stress that we need to model, and in that model there are several coefficients or parameters. So the Punch data can help to tune those parameters or coefficient. In another sense, as far as I know, there is no LES model for like LES global model, because it's kind of more expensive than the RANS. But one thing that we can do for RANS, I think it's really needed to do, is RANS can resolve down to finer scales. So, but in LES, we need to find the best model to describe to simulate the system. So in the Punch, we have the data down to the upper end of the inertial range. So that is saying we have some data at large scales for LES model. I mean, in the LES model, we the first thing we need to do is to try to find the best model in the LES. So the Punch data can be used to try to, as I mentioned at the end of my talk, you can use the data you can use the data assimilation to try to find out which LES model is the best for the system. So the Punch data, I think, in this sense, can be used to do the Punch model, so the LES model as well. But I know, as far as I know, there is no such work in space plasmas.
All right, and Lika has a question. Off Slido. Wait, we'll authorize it.
Thank you. First of all excellent talks, and this question or comment is precipitated by Rohit's talk. I think whatever we call it, alphenicity, alphen boundary, alphen zone, you know, that's a very important boundary. We understand that, and also the fast and solar wind that we have plotted forever since Ulysses days. So now that we have had Parker Solar Probe since 2018, and we have gathered data between Venus and progressively closer, and of course we are going to get to perihelion, what would it take, and it's not just for Rohit, for anyone who would want to attempt to do this, what would it take to actually utilize the Parker data and create a plot similar to Ulysses, which should be much more accurate and representative because it's not so far away, right, 2 to 4 AU, and it's not actually single point. There's just a lot of density of points. So I think it would be really awesome to look at that, what we get in terms of solar wind plot. Thank you.
Yeah, I agree. I think people have already started making these types of plots from individual PSP orbits. I think I showed an example from Sam's paper where the type of extrapolation from PSP towards or away from the sun gives you an inferred location for the Alphane surface. But as we saw, that has like big perturbations because you can have things like a CME which just blows out the. So eventually, I think maybe it'll be interesting to collect all the several PSP encounters and get a sort of average range of distances for the Alphane surface or Alphane zone. Definitely something interesting to look at, like an average solar minimum, solar maximum separately type of thing. I don't know. Yeah, I don't know if anybody else has thoughts on that.
Other thoughts on that one? All right. Let's do Michael, since you're standing right there. Michael, you had a question for Raphael.
Yeah, Raphael, I was curious to know about the robustness of your flow tracking, or both of the flow tracking techniques to data dropouts. For example, right at the edge, there are little gaps for the high time resolution data versus the more unified data products, and how your flow tracking algorithm will be applied to those data products.
Yes, so regarding the correlation-based method, the correlation can be lost after some data dropouts. When you're trying to correlate the displacements of these plasma blobs, if they have moved by more than their own size, then it can be tricky to find a reliable correlation. However, with ball tracking, I expect more robustness toward data dropouts. I faced this problem before with MDI high res. By simply giving the ball intrinsically, they have inertia, they have momentum. So they can tolerate a lot more data dropouts than correlation tracking. So if you have many frames missing, there's the assumption that you're still propagating radially. The balls can be given the constant momentum until the data are available again. That can work until, of course, a certain limit, but that limit will be much farther than the limit for the correlation-based method. I think we can, in the preparation work, can include that sort of robustness test and see, at least with Core 2 or HI data from stereo, how far that limit can go with ball tracking and correlation tracking. Regarding the edge for the trefoil, not talking about data dropout, but edge cases. I'm not sure, again, what the data will look like with the fully reconstructed trefoil image. So I'm not sure. We need to work with simulated punch-like observations.
All right, and then let's see, Raul, we've got a question to you from Rohit. Do you want to answer? Do you want to ask and answer that one?
Yeah, I think I had this thought even when I saw your poster and the paper when it came out, that your inferred correlation scales, I guess at the base of the corona, right? That's where you are.
Yep.
They seem to me to be a little bit on the smaller end of the range of scales I thought were associated with supergranulation.
Yeah. So I mean, you're right, actually. So what we have got in the paper and also in the presentation, so I'm talking about the sigma values which are being converted into the length scale by 1/e folding, which is just √2. So these are like the full width half max. So to get the full width of the distribution, that will be twice of these values. So if you are getting something between 7.6 to 9.3, if you take twice of that, that will go into the range of the supergranulation scales. So yeah, you're right.
And then while we're on that, Sarah, did you want to ask your question about also to Raul about the supergranules?
Yeah, I guess I was just wondering, I mean, that was intriguing. You were talking about the supergranules, the waves being reorganized on supergranule scales. And I was wondering if you could expand a little bit about why reorganize? Are you certain that they're not just transmitted to some extent? Or where are you coming from with that?
So these are the scales. So when I say supergranulation scale, so what I mean there is that the waves are coherent on that scales. So it's not like the one single wave which is kind of like being expanded into the magnetic field or getting to that particular scale. So most of the waves which are being launched from the photosphere, they are being traveling up through this inhomogeneous corona, and when they do, the scale what we have been getting there is comparable to the supergranulation. Now the interesting part was coming from the papers on the switchback as well, because the switchback scales were also comparable to the supergranulation scale. So why the corona does that, I'm not sure, but what they kind of on the comparison what we have got is like if it is a reconnection driven event or a wave driven, they are basically having the scales which are kind of comparable. So that could be an interesting thing to investigate, why the sun is doing it.
All right, let's do, Bill has a question for Rohit.
Trying to trick you, Rohit, no. Which one did I ask?
You said, Rohit, do you find the apparent vanishing of the inward fluctuations in subalfanic region?
Yeah, so you were
could just read it.
focusing on the reversal of the sign of the rectified cross-helicity. But if there's no inward traveling fluctuations, that would mean that there's no reflection. And personally, I find that to be counterintuitive. I'm just saying, do you find that to be counterintuitive? And wouldn't there also be a signature in the Alfvén ratios or energy difference?
But I think after I showed that vanishing of the negative cross-helicity intervals, I said that that doesn't mean that you don't have the invert mode. It's just, it's almost never the dominant one, but it is like an order of magnitude weaker than the outward mode. So you still can have weak nonlinear interactions, like we saw the cross-helicity was like 0.7 on average, right? So that's not like vanishing. But all I was saying was that there's no parcels of solar wind where that seems to be the dominant wave motion, sunward.
Could that be a scale-dependent issue as well?
Absolutely, yeah. We've seen that if you make a spectrum of the cross-helicity, then it changes by scale, right? So what I'm looking at is sort of the largest interval length average cross-helicity.
A long time ago, I think Michael Bird and people like that looking at scintillations found evidence of blobs moving inward in the middle corona. Something's happening moving inward.
Yeah, Craig, you had a question about that, but it got deleted. Did you want to ask it real quick?
I was just intrigued by that high imbalance that gets worse in the subalfanic regions. Do you think that might be why we didn't see so many inbound features, or do you think we need to, you think that maybe we won't be seeing a lot of inbound features?
I think that's something that the working group 1C should try and answer in the coming year. Because I'm not going to try to venture to answer that because I have very limited knowledge about image processing, but I think that's something we should talk about, like trying to just put some constraints on what Punch might be able to see based on these in situ observations.
All right, and let's go to Bernie for Raphael. Oh, Kurt's got it for you.
Yeah, I just wondered what radial differentiation you could get with the, you figure with your ball tracking technique in different heights of the sun.
Yeah, I'm not sure what you meant by differentiation, but do you mean how far it can provide velocity tracking?
In a unique sort of
okay.
Value.
Yeah, so, well, I can't give you a number because for the first time you're going to observe very far, so we don't have really a baseline for how far we can go, but it will depend on, so for the correlation-based tracking, it will depend on how much the periodic density structure really last and how far they are still visible above the background. The plan is, of course, to go up to 180 solar radii, but I can't guarantee that we'll be able to see yeah, that far.
How many, you think?
How fine of scale can you do it? Can you do it 5, 6, 7, 8, 9, or do you have to go to 10 solar radii and then all the way to 30 to get the next measurement?
Oh, you're talking about the resolution then?
Yes.
Okay, sorry. Yeah. All right. Well.
Acceleration and deceleration.
Okay. So yeah, originally okay. So I see what you mean. What you saw actually was when I measured the CME speed, for example. The integration time was a little bit was about 6 hours, and the differentiation especially was along just a couple of pixels. So originally, I think you can. I'm pretty confident we can have the resolution of the instrument itself, especially. So it's a trade-off always. If you care about a higher time resolution, then we may have to integrate over more pixels originally to differentiate over more pixels. So for the correlation tracking, I think that can be very accurately done over just a few pixels of in the original resolution. For ball tracking, I think it will need a bit more pixels. So I would say maybe at least twice more or 3 times more what correlation tracking will be doing for the spatial, radially.
All right, let's see. Let's go to Craig, who also has a question for Raphael about the tracking.
So is the ball tracking sufficiently robust that you can do Lagrangian frame measurements of the diffusion constant?
I think on its own, I don't think it will be robust. I think we would need to have the reconstruction, some 3D reconstruction offered by tomography. You could still get a measurement, you could still have a number from the different, but you would need to give it as much reliability as the velocities themselves. It will still be contingent to those assumptions of what is my 2D velocity representing in that whatever frame, whatever Lagrange frame we have, and understanding that there is still this 3D uncertainty that if you just keep the data product offered by the correlation-based method or the ball tracking method, you still don't really know where you are in that line of sight and what is the distribution of that blob along the line of sight. So this is why I believe you still need tomography to help there.
Yep.
But yeah, be my guest if you want to take the flow fields and measure a diffusion coefficient, just like we do on the photosphere with those plane of sky.
Well, as a quick follow-up, I was really thinking primarily about confusion between features, right? If the balls jump between features when they cross each other, then maybe that's a source of enough confusion that you can't.
So yeah, there is a lot of work that I did to avoid jumping across feeders. So I have methods in place to avoid that, and also further disambiguation can be done once you analyze the trajectories. Based on the trajectories, even if you have data dropouts, you can disambiguate a lot of the, even not using tomography, you can actually infer a relative position along the line of sight by simply analyzing trajectories of the balls.
All right, let's go to Lika. Had her hand raised actually, so go to Lika.
Yeah, I'm raising this and just to sort of put this in your consciousness. And I don't know if Robert is here, Robert Jaralim. Last year, the Frontier Development Lab, or last year or year before, undertook a problem looking at stereo EUV data, creating something called Solar NORF, Neural Radiance Inference, something like that, and creating a 3D version of EUV. And I'm wondering whether we can actually start taking some of the images from stereo and begin to apply that concept. So I'm kind of putting this into the system just to figure out what's possible in terms of looking at flow tracking or even creating the tomographical kind of maps utilizing now imaging data as opposed to EUV. Like Robert is here at HAO.
All right, do we have thoughts, or we'll wait and hear what Robert has to say tomorrow?
Yes.
Okay, yeah, let's go to Joan and then Samaya.
Hey, Raul, thank you. So have you thought about using other observations like the upcoming Aditya or Alaska or K-Core to connect those density fluctuations from UComp out to Punch and then using Punch the rest of the way?
So, the comp is a very good instrument, comp and UComp, in the way that it kind of like samples the entire FOV at one time, and that makes it kind of like more interesting to connect the waves and the inhomogeneities that we've got. And the second instrument I can look for is another chronograph, like METIS observations that can also have the density estimates in one way or the other. I'm not sure about the Aditya in that way, because it might be having the slit kind of the observations. So if it's a slit and stare, then it may kind of like it will be very hard to identify where I'm been looking at the waves or being flows, and so there might be an overlap with these two, and that makes these correlations kind of very difficult to make.
All right, Samaya.
Yes, nice talk, Raul. I was wondering, you showed 3 different scenarios in the comp data. Is a closed field, open field, and an active region field, to kind of describe how the magnetic field, the strength, and if it's closed, and then that helps you determine the alphane surface. But the field is like constantly changing, like interchange connection near active regions, and I was wondering if these compounding effects, if they matter in this case, or have you thought about it and what impact that will have?
Yes, of course they will. So in our case, we have taken an average for the better estimation of the correlational length scales. So if you look at the different, so if we can get the data which is like long enough and we can take some shorter durations, we can just evaluate how the change into the topology is going to affect the evolution of the waves and the correlational length scales and stuff like that. So the waves are definitely going to behave in a different way when they are being subject to different topologies, and this is why we can see kind of like different magnitudes in the different the kind of the magnetic field configurations. So again, like having the real-time comparison between the change into the topology and the correlational length scales will be a bit difficult, because we need some sort of an averaging of the data, and that kind of like creases out the small-scale dynamics that might be happening in that way.
All right, actually, let's do Rohit. Can you ask Jan your question?
When you were showing I guess the images from the 3 different simulations, DNS, LES, and RANS, then you correctly said that the RANS doesn't show any turbulent features, basically, right? But I think a lot of RANS models have a sort of equation, dynamical equation for the average properties of the turbulence, like most generally the turbulent energy. So that is, RANS models do give you some information about the unresolved turbulence. They don't explicitly resolve it, but there is some statistical knowledge about the unresolved turbulence. That's how I got my alphane fragmented alphane zone in the global model. So just thought that it's important to mention that RANS isn't completely discarding all the turbulence information.
Yeah, that means you need to include the additional turbulent effect in the RANS model. It's not the pure RANS model, right? And the other thing is like, yeah, I think I asked the same question to Bill. Like in your code, right, in your simulation, you included the turbulent effect, and the question is, what kind of scales that you can resolve in your code? Like it's still in large scale. I think it's still in large scale, right? It's not down to inertial range. It's not down to
It's barely
scale.
even the correlation scale. So
Yeah.
it's like 1 to 5 correlation lengths is the grid resolution of the code. So it's pretty much RANS. It's
Yeah,
not,
it's still like
yeah.
it's better than purely RANS, but it's still not better than the LES if you have
Sure.
that model.
Yeah, but I would also say that I think a majority of global solar wind models just completely, they're not even RANs, they're just like, they don't have any accounting for the turbulence at all.
Yeah,
Just
yeah.
doing the full MHD, assuming that there's nothing
Sure.
happening below the resolution scale.
That's why your code is better than others.
That's what I wanted you to say ultimately.
That was all a setup. Okay, we have time for one last question, so let's let Bill have the last question. And Bill, you can pick between your two questions, whichever you'd like.
Okay, I can ask Jan and Rohit that question offline, but I want to ask Raul just noting that at 1AU, Helios, Ulysses, magnetic correlation lengths almost always are very well described by a log normal distribution. Have you looked at that in your models, in your measurements of correlation scales?
To be honest, not yet. But like, so these are the correlation length scales which are being very highly dependent upon the observations we are having. So the resolution and all these sort of things will matter. So depending upon that, the kind of the outcome we got is kind of like they having this Gaussian kind of a distribution. But
what kind of distribution?
So Gaussian, like we do have like from the very small values to even going to the higher values, and because we are being taken the entire corona at one time. So again, depending upon the resolution itself, we can have like not one correlation length scales, but many correlation length scales.
Sure.
And that may actually contribute to the log normal distribution.
I actually think that the answer to this question, if you look into it carefully, might help answer the earlier question that you had as to why the typical values are somewhat different than the supergranulation scales, because the log normal with a wide variance can cover a lot of territory.
Okay, that's an interesting solution. Thank you.
All right, let's thank all of our speakers. And then we have posters and coffee for the next half hour until 4.
easier for that, probably.
Hello, everyone. So we are starting our next session, the cross-scale analysis part 2. And the first speaker is Yemi Rivera. She will give an invited talk connecting solar heliosphere structures across the punch field of view, heavy ion diagnostics.
Yes, thank you for the invitation to talk about heavy ions, my favorite topic. So yes, this is work that was actually part of initially all of these ideas kind of came from conversations, as I've noted down there, from my advisors, past advisors, and people at conferences. And so these ideas actually developed into a white paper that was submitted to the decadal survey. So there's a bunch of people on there, all of their ideas just collected in terms of some of the heavy ion composition diagnostics that we can do. And then it ended up being a published paper in Frontiers. So all of these things that I'm going to say, all of the ideas are in that paper if you want to go and take a look. But yes, I found this, putting this talk together, especially for Punch, to be a little challenging because Punch isn't looking at composition, but I figure what I could do, and what I did at the winter meeting was to talk about it in the context of what are the diagnostic potentials and how can we use it to unify the corona, the heliosphere, and also between structures that are observed by Punch further at large heliocentric distances. So first I wanted to talk about the general properties of heavy ions, just to get everybody on the same page. Oftentimes you think of ion and elemental composition as interchangeable, and they can be, but they give you actually different diagnostics, which is really interesting. So the compositional makeup of solar wind that we measure both at the sun and the heliosphere, they can tell you, well, the measurements in the heliosphere can tell you where that solar wind came from, what part of the sun it came from. And if you do have remote and in situ observations, that's great because that's even more powerful. You can link them up that way. Also, how it evolved from the low middle corona, so initial evolution of the solar wind out from the sun as it escapes the corona. In terms of Punch, the way that I had envisioned heavy ions being important is these heavy ions, after a certain distance from the sun, preserve information about where they came from, right? These coronal properties, and they can tell you a lot. They're very, they're heavy in information about the corona. And so a spacecraft that intercepts, right, measurements in the Punch field of view can be very useful for linking some of the properties that we make in situ to processes back at the sun, right? But also from the remote sensing side, from Punch, right? Linking those measurements to in situ observations, and then also used, as I mentioned, to map structures from one place to another, especially with, like Sam was mentioning this morning, Parker Solar Probe and Solar Orbiter, which will be in the field of view of Punch, which is very exciting. So in terms of ion composition, one of the reasons why there's such powerful diagnostics of this outflow from the corona is because they undergo what's called this freeze-in process, like Sam was mentioning. So you can imagine as you're flowing away from the sun, the density decreases very quickly because you're expanding. Collisions in general decrease. And so you get to a point where your ions, whatever they might be, iron, magnesium, all of the ions, reach a place where they freeze in. They're no longer evolving, meaning ionization and recombination no longer taking place. And so this is an image taken during an eclipse, looking at the visible two iron lines. So on the left is iron 10 plus, iron 11, if you're talking about spectra, the spectral line, and then iron 13 on the other side. So this is in the visible and near infrared lines. After you get to a certain distance away from the sun, collisions become less frequent. So radiative scattering actually dominates farther away from the sun. And so this relationship is what was used here to determine the freeze-in distances here. So on the left is iron 10 plus, and you can see even between them, right, iron 10 plus and 13 plus, they can be slightly different depending on what structure you're looking at, fast versus slow, locations of solar wind, right, corona holes versus closed field structures. And then these ions are then directly related to the measurements you make in the heliosphere. So you've probably heard of ACE-SWIX. There's a SWIX instrument also in Ulysses, and also Solar Orbiter has the heavy ion sensor in the inner heliosphere, so you can then map, right, these particular ions to measurements made in the heliosphere. So these are just iron 10 plus and iron 13 plus that you would measure with these instruments, which is really interesting, and means of really connecting these two. So above the freeze-in height, then you have the static values of the charge states, and then the last point there is the measurements that we make in the heliosphere there are imprinted with non-equilibrium ionization effects, and also potentially can be influenced by non-thermal electrons, which are driving the ionization recombination. So here is an example of that. So we notice that both in our modeling of CMEs and the solar wind, non-equilibrium ionization seems to be important in both cases. Also, we notice that the freeze-in distance to these ions are very important to what we end up in the heliosphere. So this is just an example from a paper we had published last year. This is for a CME. So you'll notice the different the properties of the plasma below and the charge states up top and below, how they're changing as a function of distance. In this case, for a CME that's really prominence material that's really dense, you get out really far, and so you actually have the opportunity to recombine and not just ionize as you're flowing out. And then on the left is just a plot, since we often use C60, C65, these ion ratios to characterize where the solar wind is coming from. I just wanted to show this plot showing the sensitivity across these different ions and across temperature, right? So they could be different depending on what structures you're looking at as they flow out. And of course, elemental composition, right? So ion composition, or 10 plus population, the elemental composition is all of those iron elements or iron ions added together, and that's your elemental composition. Just for clarification. And so here what we find is that as most of us probably already know, the chemical composition of the sun changes between the photosphere and the corona. Closed field structures versus open field structures change. And then, so I've just showed here on the right the difference, right? The just general, very simplistic way in which we think about it, which is open field structures are in the purple there, very similar to the photosphere, while the closed field structures tend to be more of a spectrum of values. And we think that this is because you have these different processes that are driving the chemical compositional changes that we see at the sun. So one of them, which you've probably heard of, is the FIP effect. I think we talked about it earlier. That is something that has been observed both at the sun and in the heliosphere. Another process which often we don't think of is gravitational settling. Gravitational settling, FIP effect, is the organization of ions, or elements rather, from their first ionization potential. Gravitational settling, as you can imagine, is then the stratification, mass stratification of these ions. So heaviest being iron, and helium being the lightest. And so you have the stratification that could happen. Another aspect that we haven't been able to observe is Coulomb drag, potentially being important in the fractionation processes as we move out into the heliosphere. And so the point that I'm trying to make here is that the elemental composition can be used to link between the sun and the heliosphere, but they can also, when you have a lot of elements that you measure together, they could be diagnostics of closed field corona. So oftentimes, the leading model, I guess, to describe the FIP effect is the Pondamora force. This is related to the magnetic field structure, alpha waves in the corona, right? Magnetic field strength, thermal structure of where the solar wind came from. And so very quickly, I just want to say these can be used, both the remote sensing that we make for these ions and elements can be used with the composition that we measure in the heliosphere with the implementation of a model, the non-equilibrium ionization model. So you can actually go either way. You can take the emission, right? So you take the emission that you measure in the in the corona to derive properties of temperature, density, and velocity of your outflowing material. You can then use that to run through a non-equilibrium ionization code that can then tell you how good you're doing, right? So you can compare to ion composition in the heliosphere, and then you can do the other way around, which is this series of papers. This is exactly what we did in my PhD. These two papers here, we started with the ion composition of a coronal mass ejection. We derived the thermodynamics from that, and we actually generated emission from that. And one of the values of that is that ion composition, right, it doesn't assume ionization equilibrium. Oftentimes when we look at emission at the corona, we have to assume ionization equilibrium. And so if you go the other way around, you can actually show, in this case, what the emission would look like, right? So you have the ion abundance, elemental abundance, temperature, density, and outflow speed, and you can actually generate emission that you would normally, that you could compare to emission that you see of the sun if you had spectra to do so. But in this case, I just wanted to point out, and non-equilibrium conditions were incredibly important, and if you would assume ionization equilibrium, it would be very different. And so how I envision this being important for punch is, of course, being able to link these structures, right? Characteristics of the corona to the inner heliosphere measured by Parker Solar Probe and Solar Orbiter. Heavy ions, again, ideal for mapping throughout this sun heliospheric system since they become static, right, at a particular distance from the sun, which is something that we can model as well. And so you can link then coronal structures to the heliosphere, but also heliosphere to heliosphere structures, right, within the field of view of punch. So for instance, I had just taken this image from the punch website and put Parker Solar Probe and Solar Orbiter here. But if you have this structure of solar wind or CME that you measure at Parker and Solar Orbiter, you can then use composition to map the structures between them. Composition is incredibly, it could be a way of distinguishing between different structures, right, as you move from one to another. And so punch would be this critical observation between them because we really don't have observations that we can map, for instance, looking at the speed structure of the structure from one place to another. So this is where punch, I think, is going to be incredibly valuable. So the in situ observations then providing coronal context to what punch observes, and then really punch being this observation that can enhance conjunction studies between measurements taken in the inner heliosphere in connection to then science objectives that I've written down there. And I think so. I'm about 3 minutes or so. Okay. Yes. So this is an example that I wanted to give in terms of some of the connection that we've done with composition. What I see is punch being incredibly useful for connecting these particle observations and the remote sensing counterparts, really unifying the way that we think about some of these observations, but also the solar wind as it flows out. Elemental composition, again, being providing information about the closed field dynamics from its chemical makeup, and then the ions being providing the thermal structure, right, the thermodynamic evolution from the charged states. And so on the right is just a plot. Up top is the proton temperature as a function of distance. And then the bottom is the proton velocity, or the bulk speed of the solar wind as a function of distance. In this case, we had this really fortuitous conjunction between Parker Solar Probe and Solar Orbiter, where we were able to then constrain the temperature profile and velocity profile between them. And so one of the ways in which we use composition, obviously the study itself was meant to look at the acceleration and heating in the fast solar wind, but we used helium composition that's measured in both cases. So you can, if you do a little work, you can actually get helium composition from Parker and Solar Orbiter. We use that to differentiate between structures and that we've mapped back to the sun. And then we've used also the ion composition that we measured with solar orbiters. This is coming from the heavy ion sensor. We've derived an electron temperature that would be associated with the corona that we can then compare to remote sensing observations. In this case, they were not contemporaneous observations, but we have an example for the slow wind in which we do have contemporaneous observations from ice and also composition measurements from SPICE that I'm not showing here. I'm not sure why I didn't include that here. But you can then you can compare all of these and link your solar wind from one place to another, and looking at the conditions of the plasma and how they evolve in order to constrain models about solar wind acceleration and heating. And so how I see this being important in terms of punches, all of this is happening. So I don't know if you can see it, but I've put there a little box showing the punch field of view. So all of this is kind of blind to us. If we had punch, then we would be able to see the structure from one place to another in the heliosphere, which currently we're blind to. But I think all of these elements together is going to be really important to really understanding this full spatial temporal evolution of the plasma, right from the corona through its formation and expansion into the heliosphere. And then the last slide is just kind of a summary of all the things that we talked about. I made this for a talk last year for Shine, and I thought it was really handy. It kind of summarizes everything, how you can use heavy ion composition for these different science questions, these open science questions that I think are very related to punch. And so I will say I've kind of focused on the first two columns, but also the kinetic properties of heavy ions are really important in terms of some of the properties of wave particle interactions and things like that. That might be handy. And that's it for me. Thanks.
Thank you, Yemia. And the next speaker is Kurt de Koning. It is an invited talk. The title is Probing CIRs with Thomson Scattered White Light.
All right, so yes, I will be talking about CIRs, particularly what we have learned about CIRs in the past from Thomson Scattered White Light and how we will be able to use punch in the future to probe CIRs with Thomson Scattered White Light. So stereo was launched back in 2006, late 2006, 2007 is when observations started. So stereo made most of its observations of CIRs during a time of solar minimum, low solar activity. Punch, on the other hand, will be launched in the coming year near solar max and making most of its observations at solar max. How will this different structure of the heliosphere impact our observations of a CIR? Now, ideally, a CIR is this nice, simple structure, very smooth, maybe a single structure in your entire field of view. And so when you're looking at this, it's very easy to imagine that stereo might have seen these simple structures and have had a good view of CIRs. On the other hand, as solar activity progresses, we're going to see more and more, potentially at any rate, a breakup of the CIRs into these kind of more large-scale blobby structures, or possibly even into this highly fragmented look, this highly fragmented heliosphere, in which case our view, a line of sight from punch through this material, will be encountering multiple blobs of material, and the question is then, what exactly are we looking at? So just stepping back a little bit, what is a CIR? For those who don't know, we have fast solar wind and slow solar wind originating at different regions in the different times in the corona. Because they are originating at different regions, different times in the corona, but flowing along the same radial line in the end, the magnetic fields can't interpenetrate. Because the magnetic fields can't interpenetrate, the streams don't interpenetrate. And so what you end up having is the fast solar wind catches up and piles up into the slow solar wind, causing this stream interface that you see as the dotted blue line here, and you have compressed fast solar wind behind the interface and compressed slow solar wind in front of the interface. So that's basically the idea of what a CIR is. It's simply a pileup of material. as far as the global structure of a CIR goes, a CIR is, at the end of the day, nothing more than an outflow of solar wind from a co-rotating sun, and therefore the CIR, like the solar wind itself, has this Archimedean spiral structure. Looking at the local structure, as with any large-scale structure, as we learn in differential geometry, you can approximate the local structure or the local region of any surface, assuming that it's sufficiently smooth and nice and everything, by its tangent plane, and that's exactly what we have also with the CIR. Is it can be approximated by a tilted plane at any local region. So now turning to stereo itself and the stereo observations that have come out in the past 18 years since stereo was launched. The first and perhaps most important thing that stereo did is stereo actually saw a CIR in white light. So here we have one of the, from the Rolliard et al. Paper from 2008, first observation of a CIR, and you can see the CIR as this structure here, and this is in the high 1 field of view. You can see it as this structure here that's slowly propagating outward, and then later on it appears in the high 2 field of view and continues to propagate outward. So that was an important accomplishment. So that's one of the major areas of science that stereo high has accomplished. Another area of accomplishment of stereo high was shown by Brian Wood in this paper from 2010, in which he took stereo observations, stereo high observations from stereo A and stereo B, and he was able to use some simple model that some simple phenomenological model that he put together in order to reconstruct what a CIR looks like. So here you have the real data, here you have his simulated data looking through his data structure, his CIR data structure, and this is what his understanding, the model's understanding of what a CIR looks like, which Craig likes to call a snail shell model. So that's what, and that's of course one of the big things that we're looking for within Punch is, one of the big questions is, what is the global structure of a CIR? Is it this snail shell model? Is it something different? And that's what we're hoping to find out. So that is the reconstruction. Another big part of CIR high science is from this paper in Sheely et al. 2008 is one of the first to mention it, but there is multiple papers that have come out in the years following this paper, and that is that CIRs are not this, of course, like most things in the solar wind, they are not smooth, simple structures, but they are, in this case, they were called blobby structures. And you can see the blobbiness of the structure by looking at this track over here, and then these other tracks that follow behind, all of which seem to converge along one single track. And what's assumed is happening over here is that you have intermittent release of material, of blobs, from a single co-rotating source, and then these blobs will eventually catch up again to the slow solar wind, and they will all pile up together to form a blobby CIR. It's shown a little more clearly in this image from Politnikov et al. 2016, in which again you see the raw image over here. This is the outer part of the envelope, and then you can see over here how they've drawn all these different other intermittent releases of material that are all converging onto this onto this main structure. So CIRs are blobby. Another important point I think about CIR science is that there have been multiple observations of them over the last 18 years, and they have been cataloged. The original catalog was hosted by the RAL team on their website. It can be found at this link over here, or this website over here. A more up-to-date, and the original catalog goes out through 2012. And it's a good point to remember about this original event list is that it contains both CMEs and CIRs. So there's an intermingling of events from that High has seen. The Hellcats catalog that Politnikov describes events from in his 2016 paper, describes the properties of 190 CIRs that are in this HELCATS catalog. That is a catalog that extends from 2007, excuse me, out through about 2015, late 2014. Again, it can be found at this location. So CIRs have been regularly seen over the years. These are not, they may be difficult to see, but they're definitely observable. Then we come to the question of, can you forecast a CIR? Williams et al. In a 2011 paper looking at 24 different events said that comparing two different methods of forecasting CIRs, said that the stereo high method using stereo high to forecast did not do very well. Davis et al. In 2012, looking at a larger number of events, thought that their technique could provide a timely prediction of the arrival of CIRs at least one day ahead of their arrival at Earth. So can we forecast them is still a bit of an open question. And finally, just to avoid the wrath of Bernie and Dave and James Tappan, SME has also seen CIRs. SME was launched on the Coriolis spacecraft in 2003 and observed through 2006, is that correct? And according to a review from Tim Howard, I believe he said that it only saw 2 CIRs. So, but here's where the CIR is in the SME field of view, this white line right here. Yes, Bernie. All right. So there you have it, from somebody who knows better than I do. So now looking ahead to the future of CIR science, I want to concentrate on the punch, or the P from punch, which I think is the most, which in my opinion is the most important letter in the acronym, referring to the polarimetry, the using polarization not only in the inner helio, not only in the NIFI, but also in the WIFI field of view, and that will allow us to do then localization. That's what the P is all about, really, is localization, and be able to do that localization through a wide field of view. So just to remember what we see in terms of brightness, total brightness, or polarized brightness is simply a line of sight integral through a certain structure along and then weighted by some sort of a function, a different function for the total polarization and the polarized, for the total brightness, excuse me, and the polarized brightness. But we're really just looking, we're integrating through a density structure. Now, if we assume that this density structure is a direct delta function, then we can concentrate all the density in one location, the density information can drop out, and then we can use the polarization ratio, B pole over B total, to provide an information, approximate information on the scattering location. So when we're looking through the heliosphere for a CIR, of course, what we want to do in order to see the CIR as a bright feature, we need to look through the largest amount of material, largest amount of mass, and that tends to occur at a line of sight that is approximately tangent to the stream interface. And it will occur, of course, on the compressed slow solar wind, which is denser, and so that's where our line of sight is going to be looking through, is through this compressed slow solar wind that is approximately tangent to the stream interface. Now, one thing to notice here, here's our observer, here's our line of sight in blue, and this lighter gray line over here, or circle over here, is the Thomson sphere. It looks like from this, this very simple picture that the CIR is going to be appearing, the line of the point of tangency is going to be appearing well behind the Thomson sphere. Sheely and Rolliard drew a similar picture, looking at all the possible lines of sight for a particular set of structure, Archimedean spirals, and came up with this locus, this bean-shaped locus of where you might see the CIR, the brightest points of the CIR. So now doing a simple, what we're going to do now is just a few quick simple calculations. Looking from the observer along a line of sight, and looking how density structures relative to the Thomson sphere, what is it that we might see? Now, in the images that I'm going to show, I'm going to assume that anything, or I'm going to normalize the distance the line of sight distance for a fixed, I'm going to always be doing it at a fixed elongation angle. I'm going to normalize the line of sight distance so that the Thomson sphere is always at zeta equals 1. And then, so anything less than zeta, anything less than 1, a position less than 1 is inside the Thomson sphere. Outside the Thomson sphere will be points greater than 1. So here we have what really might be considered an ideal situation. We have a very narrow density structure centered right on the Thomson sphere. And as we look through the brightness, calculate the brightness using those formulas that I showed earlier, you can see there is actually 2 curves in here. This lighter curve is the polarized brightness. Hiding underneath it is the total brightness. And because the total brightness and the polarized brightness are very, very similar, what we find is, of course, that the polarization ratio at this dotted blue line at the top is very close to 1. We can use this shape over here to backtrack, knowing what the polarization ratio is. What does this tell us? What the scattering location is, and what we can see is that the scattering location occurs basically where we would expect to find it, right here on the Thomson sphere. Now, looking at a slightly wider density structure, still centered on the Thomson sphere, we can see in this case that the polarized brightness and the total brightness can be separated into two different structures, resulting in a lower polarization ratio and resulting in a much more well-differentiated location, either in front of the Thomson sphere or inside the Thomson sphere or outside the Thomson sphere, with the interesting point that even though the density structure is located right here on the Thomson sphere, this approximation technique based on the polarization ratio places the location well removed from the Thomson sphere, and in fact introduces about a 20% error. But again, given the information we have here, we couldn't tell if it's inside or outside the Thomson sphere. However, as Sarah pointed out in the meeting on Tuesday, the pre-meeting, if the material is hiding either inside the Thomson sphere or behind the Thomson sphere, we have a slightly better situation. So here we have a narrow density structure located well behind the Thomson sphere where we might expect to observe CIRs. Here is again in the purple, we have the total brightness, the pink, the lighter color is the polarized brightness, and we can then find out where use this localization technique based on polarization ratio. We can actually fairly easily or precisely find out where the scattering location is, a single scattering location, which in this case comes very close to the center of mass location of the material is at 2. The scattering location is estimated to be at 1.99. So that's a very low percent error. If we make a broader density structure, we can go through the exact same procedure, and we see that in this case, the estimated location based on polarization ratio is closer to the Thomson sphere than the real point, and we have about a 10% error. So in fact, assuming that most of the material is hiding behind the Thomson sphere, either inside or outside, this estimation technique does quite a good job in finding out where the center of mass material is. This, of course, is an ideal calculation where we have a perfect background subtraction and no noise in the material and no noise in this simple calculation. If we add noise and background material, then there's going to be an increase in error. And of course, the real question, coming back to the very beginning, is if we have a fragmented heliosphere like this, and we are looking through possible multiple structures, how well will this localization technique actually work? Thank you.
Thank you, Kurt. And our next speaker is Gabriel Muro. And Gabriel will give an invited talk, The Evolution of SCP Events Through the Inner Heliosphere.
Oh gosh. Can you guys just go back to the beginning?
All right, hi. My name is Gabriel, and I am going to just give you guys a bit of a synopsis on how I characterize an SEP event through the inner heliosphere, and basically mention opportunities where Punch would have been really helpful if it had launched, a year ago as opposed to a year from now. So, this particular event that I was looking at had a really nice spacecraft, multi-spacecraft configuration, which is becoming easier and easier as we launch more and more spacecraft, with redundant tools. But this one in particular was really well aligned along what we would call Parker spiral lines, or nominal magnetic fields, which are the solar wind pathways between Parker Solar Probe, Stereo, and ACE. And Stereo just happened to be pretty close to the Earth around that same point in time. I messed up this graphic here, and I've actually just shown you the configuration of the spacecraft at the same time, but trust me, the post-storm connection is still very, very, very similar. And this animation here is essentially what we think, a cartoon version of what we think an SEP event looks like. So we have the CME, which is that U-shaped thing moving off to the bottom right. But we also have these particles, these SEP, very fast particles moving ahead of the CME, and they generally will follow Parker spiral lines. At least that's the idea. PFSS modeling showed that this particular active region, which I believe produced this event, was very well connected to Parker Solar Probe as well as Stereo and ACE again. The big, I don't know how to actually point with this thing, but the big black arrow there is where Parker was on this particular date. Which button is it? It's this one? Okay. Hold it down. Okay, that's not where I expected it to be. All right, this big black arrow right here is the location of Parker during the actual event period. On this particular day, at the very end of July 17th, 2023, we saw 2 solar flares measured in X-rays using GOES X-ray, a sort of M5 one that cools down pretty quickly, and then a very large, and you'll see it's just actually quite wide, M5.7 flare. And this one had a very extended duration period with regards to cooling down. So the area that we're looking at is down here on the bottom right, and this is the suite of GOES SUVI observations that were available. And you can see that this is a pretty large and wide and long-lasting region for this M-class solar flare, which produced the largest SEP event of orbit 16, and it's comparable to orbit 17 as well. So what was interesting about this is if you look down here on the bottom right portion, just before the event occurs, you see sort of a two-phased thing occurring. You see plasma being lifted above the surface and then being ejected. So I'll let it play one more time. So that would be flare 1 and flare 2, which created sort of a temporary prominence, I suppose. And then the second flare ejected that outwards. Now, I was wondering, is this the SEP? And so I was trying to figure out if some signatures might at least in the in situ data that we received later, might actually tell us a bit about that. So what I did was I examined using AIA differential emission measure temperature mapping, which combines these 6 cameras here, and essentially decides what is the most likely temperature of a given range. So I've created a small little square down here on the bottom right, where I'm measuring up here in the upper right the most likely temperature occurring during the period of the flare and subsequent CME and everything that occurs afterwards, the solar storm essentially. Now peak ion temperatures reach at least 9 million Kelvin, at least. Not quite sure how hot it is in total, and that's basically because the DEM is only useful up to close to 10 to the 7th power. Beyond that, it's pretty iffy to make any estimate about this, and this is where I believe STEAM is actually a very useful tool for understanding the ionization that's occurring, because flares should be very, very efficient at ionizing particles and ionizing a prominence essentially very close to the surface there. So when we look at the CME propagation, here we go. Stereo, which is one of the instruments that was measuring it, we see a pretty large event occurring on the bottom right portion. Now, there we go. Pretty large event expanding outwards to the southeast. And additionally, there we go. We have whisper data. Now, if you guys can't see it on the screen, that's fine. It's extremely difficult to actually capture this CME propagating from the left towards the right there. And this is one of the things where Punch will be extremely helpful with the round-the-clock coronagraph. Because Whisper, which is a wonderful device, only is operational during encounter periods for Parker when we enter a certain distance. This particular event, Parker was at 0.65 AU. So it was, I was lucky that it was on at all. But interestingly, we are able to see little spatterings, I suppose, of CMEs and things like that crossing even at this great distance there. And I believe Punch probably is able to do a better job. So go forward. Okay, so now on to the actual measurements that we got on Parker Solar Probe. So this whole slew of events starts with a type 2 and type 3 radio burst flurry, essentially. We have many type 2s and type 3s occurring in conjunction here. If anyone's interested, later on I can expand this out and you'll see that there are just too many to count. And a few moments later, about 30 minutes or so later, we get our first protons arriving at Parker Solar Probe. These are the protons in our epi-high HET, which is our high energy telescope, and this measures from somewhere around 10 to 100 MeV. Then we have LET, which is the device that I'll be comparing against stereo, mainly because stereo and LET capture very similar ranges. They're pretty similar devices. And epi-low, which goes all the way down below the MeV down to the around, I believe it's 100 keV. And so we can see the first particles to arrive are, of course, these most energetic protons here. Magnetic field-wise, nothing's really happening when we get these protons. It's quite a while later when the CME shock occurs and we see this huge magnetic shock, and then we have a magnetic cloud and a strange little, I guess, magnetic hole that occurs a bit later there. But those first particles arrive without any effect on the local magnetic field for Parker Solar Probe. And so that means these are moving far ahead of any CME shock or anything like that. And they're moving at such a speed that I'm not even sure if Punch, with its pretty high cadence, could capture this since, if I go backwards here, since the time frame, oh, here we go, since the time frame with protons moving at an estimated 30,000 kilometers per second would probably move it out of the field of view in less than a minute there. So I'm not sure if Punch is capable of going faster than 4 minutes, but if it can get down to 20 seconds, that would be great. We might actually image a SCP event. And so this is what I call what we call a velocity dispersion estimate, analysis estimate. Essentially, we assume our fastest protons, which would be these guys, it's flipped for some reason, arrive first, assuming that all of these particles started at the same position and traveled the same distance. And this distance in this case would be the SCP path length, which is longer than just the radial distance because it's following along those Parker spirals there. So what we captured here were a whole bunch of different ions, which Yemi introduced earlier. We've got protons, which PSP and stereo were able to measure. You can see the event looks somewhat similar. You have to kind of blur your eyes a little bit, just squint your eyes, and they look pretty similar. Helium and helium was measured in all three of these spacecraft. Protons are not measured in ACE, and oxygen and iron. So iron can be a little iffy. It looks like the statistics are a little bit low there, but oxygen, I feel like we've got pretty good statistics at all three spacecrafts here, which is where sort of the interesting part of this SCP event occurs a bit later. So before we get to that, additionally, we have to remember that our spacecraft is able to measure in both directions. So HET, the high energy telescope, and the low energy telescopes are able to measure in the A direction, which is roughly sunward-ish facing, along with the B direction, which is facing opposite of the sun. And so these energized particles are moving in a sort of cyclotronic motion along these magnetic field lines very, very quickly, and some of them are moving in the opposite direction, at least with respect to Parker. So what we see is that at the beginning of these events, there's a whole lot of ion anisotropy. The measurements are quite different. They are essentially front-loaded towards the sun. But as we move further, what is that? All right, well, big SCP event coming. Okay. Oh. I'm not sure what I should do. Okay, sure. Oh. now minute 45 of my talk. All right, should I just continue? Okay, yeah, it's fine. This is all screwy anyways. Okay, so I backtracked just a little bit just to remind us. We are talking about solar energetic particles that are moving very, very quickly at around, let's say, 10% the speed of light. Around 10% the speed of light, down a Parker spiral pathway. We were able to measure many different ions, protons, helium, oxygen, and iron here. ACE just simply doesn't measure protons there. Roughly speaking, if you guys don't look at these all the time, these energy spectra basically look pretty similar to me. They're just kind of spread out because stereo is, of course, further down the line. It's around 0.3 AU further down the pathway of these SEP events. So it should appear a bit more hazy, larger in size as it radially spreads. So we also have anisotropies. So looking specifically at LET, which is just 1 to 20 MeVs, which is the same, very, very similar devices on stereo. We have protons facing the sun. These are all the A devices here. So helium A, iron A, oxygen A. They're facing in the sunward direction. And then we've got B, which is the anti-sunward direction, 180 degrees in the other direction. Now, we see that these particles are heavily weighted towards the sun as the event begins for at least the first, I don't know, ballparking it, something like 12 or 15 hours or so. Afterwards, so if you were to kind of just focus on everything to the, from the right to the middle there, it's pretty isotropic. They look very similar in both directions there, and that's basically because as the event kind of relaxes, there's much more cyclotron motion of these particles up and down the pathways, which makes them appear similar in both directions, although at the very beginning, it's really just front-loaded because those particles are moving very quickly in one particular direction. Now, one of the ways that I analyze an SEP event is to take what we call fluent spectra. Oh, sure, okay, I don't know how many minutes I have left. 2 minutes. So, fluent spectra, which is taking all of the energy measurements for different, oops. Oh God, what's happening again? Yeah. Fluent spectra, which take all of the energies for various nucleons going from like 1 MeV up to like, 80 MeV there. For all three spacecraft here. Parker is the squares and circles, stereo is the downward facing triangles, and ACE is the upward facing triangles. And you can see there's a lot of overlap between ACE and stereo, which we would expect because they're well calibrated and pretty close together. Now, what was interesting is when I radially adjusted the fluent spectra. To do this with the lighter ions like protons and helium, I simply reduced it by a factor of 1 over r to the 4th, and they all overlap here. So these are the protons, and these are the helium in all spacecraft. Energy spectra-wise, they look the same. The shape of the SEP event is similar in both of them. But when it came to the heavy ions, I had to go a full order of magnitude more, 1 over r to the 5th, to get them to sync up. And once again, they look pretty similar with their spectral shape. And so this is a really curious and sort of unknown, at the moment, reason why this has occurred. So what I was trying to think of was a reason why this would occur. And this could possibly be due to the mass to charge ratio. Essentially, how much charge a given particle has versus its overall mass. So with respect to protons, you ionize it one time, take away 1 electron, and it's fully ionized. But when it comes to things like oxygen and iron, you take away one electron, and it's not very ionized. I'll wrap it up. And so we're attempting to do a statistical method to get the average ionic charge state for each of these ions here. Okay, animation didn't play. I'll just move forward there. The reason for that is that if there is more mass compared against charge, those atoms moving around, those ions moving around, are able to escape their given Parker spiral field line and perhaps move to another Parker spiral field line, which is why stereo wouldn't be measuring them. And it all depends on how ionized those particles were down near the surface where the whole solar event began. Essentially, steam giving us some idea about the flare ionization efficiency would be great for this event. Additionally, all of those anisotropies could be well sorted out if we had smaller scale chronograph data to work with. So that's essentially it. I have no idea. I think I'm at like 45 minutes of my talk now, with a bit of a break in the middle. But yeah, that's all. So thanks. Sorry for the alarm as well.
Thank you, and thank you for a very long talk. And so this is the last talk of the session, and since after this there is only the reception, we decided that we will continue the session as planned, and we just have a reception a little bit later. So the last talk of the session is by Mihir Desai, and forecasting shock-associated energetic particle intensities in the inner heliosphere, a proof of concept for the Punch mission.
Okay, so due to the unfortunate circumstance, I'm standing between you and wine and beer and food, so sorry about that. Just to give you an example of what I'm going to talk about, CME shocks and energetic particles. These are solar energetic particles, the type of particle events that Gabriel just described. What I'm showing here is I'm not showing anything here. This has really gone too far now. Oh, okay. Okay, so as the CME plows out through the inner corona and the inner heliosphere, it drives a shock wave. If it's fast enough, these shock waves can accelerate SEPs, solar energetic particles. Close to the sun, when the acceleration happens close to the sun and you see SEPs out in a distant spacecraft, they're called SEPs. When the shock goes over the spacecraft, actually this is not the slide I was talking about. I don't know what's back and forth. How do I do this? Odd, I've completely botched this up. Okay. All right. So when the shock is accelerating particles close to the sun, they're called SEPs, and when the shock goes over the spacecraft at 1 AU, they're called ESP events. This is that portion here, and you see particles are being accelerated all the way up to roughly around above 100 MeV up to 500 MeV. So we want to be able to understand both of these events, both of these type of particle measurements. First observations of ESPs were found in the 1960s. They were associated with what's known as Forbus decreases, which were associated with, now we know it's with a magnetic cloud or a CME. And because these were also associated with geomagnetic storm, they were defined as energetic storm particles. They have spectra, which Gabriel showed, which are softer. Softer means they're steeper than the SEP event that they accompany. There were a bunch of theories going around, but now it's generally accepted that they're accelerated via what's known as diffusive shock acceleration, in which there are two primary mechanisms depending on whether the shock is propagating along the upstream magnetic field direction, which is a quasi-parallel shock, or the shock is propagating normal to the upstream magnetic field direction, which would be a quasi-perpendicular shock. Depending on that, you could get acceleration mechanisms which are dominant in one. In this case, it's the first order Fermi acceleration. They bounce back and forth between the magnetic mirrors, as it were, either side of the shock to get an energy gain, and the particles get accelerated. In this mechanism here, the V cross B electric field along the shock lets the particles to drift along and accelerates them quite to high energies. Now, of course, if we know all this so well, what are we doing and why are we doing anything? Here's an example of the ESP time profiles that you see, and they're not always like the classic example I showed earlier. In fact, about they come in 6 different categories with more or less equal numbers of in the distributions. Typical events are only about 10-20%. There are these type of spiky events. There are typical plus spike, all kinds of weird stuff going on. And there's this step-like, and then there's this irregular stuff. Now, I will come back to this very briefly at the end of the talk as to why we want to be able to address some of these weird-looking time profiles here. So why study them? Of course, they provide important information on particle acceleration in shocks. They also help us understand how shocks can accelerate particles close to the sun and produce the SEPs. Some of these enhancements are so extreme that they actually saturate the very instruments that are designed to measure them. Here's an example of that. And forecasting is thus important. Although I'm only talking about lower energy particles, but as you see, they extend all the way up to 500 MeV, and the radiation hazard is caused by 100 to 200 to 300 MeV particles. And that was that double whammy. You had a huge increase, 4 orders of magnitude increase, and on top of that, there's another one. So it's a double whammy that you get when you get a big ESP event. There have been attempts to see what kind of parameters, what kind of properties can be used. This is mostly about not forecasting ESPs. This is exclusively about using ESPs associated with these shocks, properties of their shocks, to predict the arrival of these shocks. So all these studies, for instance, Posner looked at particle anisotropies, the spectral behavior, and he could predict the arrival of an interplanetary shock, a geo-effective interplanetary shock, up to 24 hours ahead of time. And there were other studies using other properties, but nobody actually tried to predict the properties of ESPs themselves. Despite that, the success rate was about 50 to 70%, which is not great. Is not really, you wouldn't really call any of your customers that there's something going to happen with a 50% probability. So we want to improve that. So Maher, what he did was he went through a bunch of parameters that he could find ranging from the ESP properties themselves, ion to oxygen ratios, etc., along with the properties of the shock and the ICME to find some kind of a heat map where there's a correlation that would allow us to predict ESP properties. There's a bunch of events here there. So the rest of the talk, I'll talk about this work that he is in preparation for the Punch special issue, I think. You already heard about the fast and slow solar wind causing CIRs. What you didn't hear about is that they also drive shock waves, forward and reverse shocks, beyond 1 AU and beyond mostly. And these guys also tend to accelerate particles that you can measure back at 1 AU and across throughout the heliosphere as well. You've already heard about the CME shock. Now you see that this is a nice smooth shock, but try to relate that smoothness with those time profiles that you see, and you'll fall flat very quickly. So here's the list and the analysis that Maher did. He started out with the Helsinki fast forward shock database, which uses wind ACE and stereo A. He estimated the energetic storm particle peak flux within a 12-hour window, and he computed the shock properties for these types of events. Same thing for CIR, rinse and repeat. Just use the right energies to make sure that you have measurements that you can correlate with that. Remember, these are all restricted to below 1 MeV for now, but at some point he will extend it to higher energies to look at other stronger events. The best correlation he seemed to have found for these types of events is for both of these types of events. I'll show you an example. Before I do that, like this is the delta V, which is the velocity jump. You can also use the magnetic compression ratio, the density jump, etc., etc. Theta BN is not being used here, but that could also be an important parameter, as I mentioned earlier. So this is he used the peak, for the ESP events, he used the peak velocity with the peak flux. This is the peak plasma velocity. And he also used the delta V. And in both cases, it appears that the delta V is a better a parameter that correlates better with both types of events, ESP events and CIR shock events. And this has been kind of known, but not done in a systematic fashion with a bunch of parameters and using correlation heat maps and things like that. So it's a nice study to be able to point to. So as I said, the peak flux is most best seems to be best correlated with the delta V, which is the jump in the velocity across the shock itself. Let's see. So Raphael gave a very nice presentation of what he is trying to do and how he's helping this work and how punch plays a role in what we want to do going forward. He's tracking blobs and CMEs, and he can estimate CME speeds with this. So what we want to be able to do is to measure the CME speed, measure properties of the CME shock close to the sun using punch, run some SEP acceleration model, and predict SEPs at various locations in a heliosphere, including Parker, Solar Orbiter, and all 1AU spacecraft, to be able to see whether our acceleration models are correct and how punch can make our life easier when it comes to forecasting these types of events. Here's an architecture of a potential forecasting algorithm, which is iterative, so it's an evolving forecast he's thinking about in the long run. But this is not the only parameter that can come into play. The set of parameters or the set of conditions that could allow us to finally come up with an algorithm, empirical but data-based and physics-based, especially if we use the SEP acceleration models that are well known. So to summarize, Maher was talking about a problem, which is how to predict ESP properties, or properties of energetic particles associated with shocks, and how difficult they are to predict, and they're important for space weather, as I mentioned. One solution is when punch launches, we will be able to estimate a certain number of shock quantities, specifically delta V, the compression ratio. We don't even need the shock, for say, it's just a compression region that we need. So we don't need punch to identify the shock itself, just compression ratios across that region where particles are supposedly being accelerated. The caveat here is that shock is not smooth and round, and I saw some excellent simulations from Elena. And what we would like to do at some point with this working group to see, I think, is to combine punch data with the Gamera model and SEP acceleration models to be able to start predicting, taking account of the small scale shock structure and how you connect to different parts of the shock can create different types of time profiles to see whether you can address some of that variability that we've been seeing in the data. I really think that this is now, we're going to enter into golden age of space weather advances with a lot of the spacecraft that we have. That I'll stop, and we can sit here or go outside.
Let's try sitting here and see if we can make it to the end of that session without more fire alarms. So I'm asking all speakers to come over to the podium, and let's take questions. Okay, and I'm told that in order to answer, you have to hold a button. Okay, so the first question in Slido is by Heather, and yeah.
Okay, it's for Kurt. Can you use the speed gradients to help identify the CIRs? Because whenever you see like if I'm taking in situ observations and I have the solar wind sweep across me, I'll see the speed rise as a function of time, but that's essentially a spatial gradient. I was wondering if that could help with identifying the CIRs or criteria that could maybe help you figure out some of the issues with that where you were getting. I wonder if that's useful.
So are you talking about using in situ data along with
No. If you can identify a speed gradient in the
images.
Yeah.
I guess I'm not sure about the answer to that question. I know Craig and I are going to sit down at some point in time to look at what CIRs look like in the high field of view, and that may help us to answer that question as we get better, as I get better in identifying them.
Okay, the next question is by Craig, and it's also for Kurt.
Just call it a follow-up. So very elegant to note that just from the geometry of how CIRs are formed, they're always behind the Thomson sphere. That's cool. Is there any circumstance where it might be in front? For example, if it's fragmented or bent?
Well, if that simulation that Dushan published for the Parker Solar Probe paper is anything to go by, it certainly looks like there could be CIR fragments inside. But again, that's simply a model, and I don't know how good the models are. I think Bill said something this morning that suggested a lot of the models probably have a lot more ambiguity in them, a lot more uncertainty in them than we like to think. And certainly the models are very dependent on what the driving conditions are. And in most cases, I don't think we really know what the driving conditions are. We're estimating them from very limited data sources.
Actually, don't sit down just yet, because the next question is also from you, and it's for Yemi.
All right, so Yemi, how do you imagine making the best use of punch data together with compositional data? Are we talking about tracking individual features or doing some sort of ensemble measurement? What's your vision?
So I think the way that I was thinking about it is that it provides this kind of global scale of what's happening. And so in the example that I was giving in the second to last slide, we use composition to distinguish between different types of solar wind when we did the back mapping to the sun. So we compared the measurements taken in the heliosphere and then also back mapped it to a coronal hole, compare the composition from a measured in situ measurement to the coronal hole. And so you have this connection that you can make. And so the way that I kind of envision punch working in collaboratively with the composition data is that you have all of this, the density and velocity structure that you don't see, that punch completely observes between one spacecraft and another. And so all of that can be then linked to these global scales, and then composition can be an element to connecting back at the corona.
Then the next two questions are from Nikki, and the first question for Kurt.
Yeah, Kurt, in that super complex image you showed of the CIRs that were extremely complex, was the complexity due to the solar wind itself being formed in little polar or equatorial coronal holes and stuff, or is it because of CMEs blasting through the existing structure in the heliosphere and warping it?
That example that I took was from a paper written by Dushan, I think from 2020, in preparation for the Parker Solar Probe, what it might see. And if I understand correctly, what Dushan did is he updated the boundary conditions on an hourly basis. And so what we're seeing there would be complexity in the solar wind itself rather than CMEs interrupting the flow.
That's really cool.
Mm-hmm. Go ahead.
Oh, and next one? You want me to? Okay, so the next one was from here. Obviously, the whole reason we're going to have punch is it's going to capture these velocity gradients and these shock structures even better than we could have with stereo. But could we do something simple to test out this idea with stereo with like a really big CME or one of the big shocks?
Yes, so we can try. The one thing that I sort of swept under the carpet here, or the rug, or whatever you want to call it, is how not just because there's a great correlation doesn't mean that delta V is going to be a great predictor, right? If you look at a single delta V, a narrow delta V, and the range of the peak fluxes that the variation was there, it was nearly 2 orders of magnitude. So in the past, when we've done CME speed with peak proton fluxes, it used to be 4 or 5. Delta V is a better predictor, and there's there's more constraint on how much the peak flux varies. But as I mentioned, there are other quantities that are also equally important, like the connection to the shock itself, and what the angle, shock normal angle would be, and all those things will have to interplay with SCP acceleration models and the shock structure that was very impressive Gamera simulation. So all those will have to make it better and get that. You will never find a single parameter that can be used to predict ESPs or SCPs because there's too many variables, as you saw from that heat map.
Mm-hmm. Let's take the next question from Michael Kirk.
Sure. Gabriel, do SCPs interact meaningfully with any sort of other solar wind structures? I'm thinking you have tremendously energetic material. There might be something that happens. Is that visible, detectable?
As for visible and detectable, I'm not so sure. But we do suspect that the SCPs have their own sort of independent thermodynamics as they travel down the pathways. And you've got particles that are traveling so quickly that they're able to occasionally escape their nominal magnetic field path that they would be in. So if you had things like, I've heard of these, I haven't actually seen these necessarily, but empty flux tubes and things like that, they may actually be getting filled up during these high energy particle transport periods. Additionally, I suppose there's also reconnection that can occur down the pathways, basically like very violent CIRs as in some way to think about it. As for how observable these things are, probably very difficult. The only place to see these would be very low, close to the sun, because the density of SCPs are quite low, few orders of magnitude below the particles that we get from, let's say, coronal mass ejection fronts. So I'm not sure if Punch would have the capability to actually see that.
The next question is from Thor Menzinger, and
so you'll have to forgive my ignorance. I'm a total novice. So I was just wondering, I've heard the term blob all day, and I'm wondering, as these blobs travel through the media, based on their composition, do they actually have turbulence signatures that you can kind of infer what that blob is made out of just by the wake that it leaves?
Nikki might be the best person to answer that question.
Yes, Working Group 1B is going to answer exactly that. Two things. One, yes, I think compositionally, I think you're asking to Yami, do they have heavy ion composition signatures that are different? So the composition, because it's frozen in low down, as Jamie was describing, captures actually any pre-turbulent stuff. That's what's so cool about it. But what we're going to be able to do with Punch is literally watch the blob as it interacts with the surrounding medium and see how much the blob itself gets distorted and how much it generates new turbulence. And that's Punch, we designed it specifically to go after the size scales to be able to answer that question.
Okay. The next question is from Narieke, just behind you.
Listening to Mihir's presentation, he often talked about predicting ESPs and characterizing shocks close to the sun using Punch. But what does Punch do to characterize shocks close to the sun? Because in SCP community, people now use a GCS model, ellipsoid fitting, and in combination with MHD steady state model, you can get some shock parameters close to the sun. But maybe the main advantage is to characterize shocks in structure of the shocks, or how can I understand what Punch will do?
So to answer the question, how close to the sun can we resolve a shock and shock properties? I think Craig might be the person to answer that, because I'm expecting 10 solar radii and above, at least, if we go down, right? Roughly. So we won't be able to do the SCP portion of this, right? Maybe 5? Okay, we're getting closer. A lot of the action is happening, between 1 to 5 solar radii. The highest energy GLE type of events are happening 5 to, less than 5 solar radii. But the hundreds of MeV, 200 MeV for space weather kind of purposes, that's happening beyond 5 solar radii and 20 solar radii and continuing all the way to 1 AU. So we should be able to do better than what we've been able to do before. The second part was the consensus of whether a compression region can accelerate particles,
That's
I
right,
guess. Yes. So a compression region, a shock is just a very sharp boundary compression region, right? As long as the particles have a gyro radius that can see the difference between upstream and downstream in the strength, delta V or delta B or delta rho in density, they will get accelerated. They may not be as efficient accelerators as a shock, but they should get accelerated. There are papers by Giacalone and Jacobi that talk about acceleration at compression regions as long as the ion gyro radii is bigger and can experience the compression or the changes in the compression across the shock, which is another reason why diffusive shock acceleration finds it difficult to accelerate electrons. It's a theoretical problem that they cannot solve. But observationally, we see electrons all the time.
Nariaki, wait for the microphone, please.
I can't hear. I didn't hear.
What about other parameters of shock, like shock Mach number?
Yeah. All those are important. And they're related in some sense, right? The compression ratio, Mach number, theta Bn is probably an important parameter that we'll have to get out using SEP acceleration models and the Gamera models and things like that. But certainly the shock structure and the information about hopefully some of the upstream magnetic field with inner heliospheric spacecraft may be able to allow us to constrain the problem a bit better.
Okay, the next question is by Michael Kirk.
Yemi, a question for you. This is me trying to wrap my head around Punch and your presentation and stick them together into something in my head. So it's a little bit word soupy, but we'll get there. I'm curious about how Alfvén or Faust mode waves would affect the structure of the topology of the heavy ions as they're before or as they're frozen in, and would Punch and the polarization of Punch help create some sort of two-dimensional map or expose sort of the origin or some formation mechanisms or how they were affected on the sun? So it's not entirely a well-formed question, but if you have comments.
Yeah, that's really interesting. So in terms of the interaction between ions and waves, right, if you do have a mass per charge dependence, for instance, and you have some resonance, then you'll have some, right, translation of kinetic energy to those ions, and that would be expressed in a way where if it is mass per charge dependent, then that would be, as you have different ions that have different mass per charge, that would be expressed in that way. So one of the things that we often find in the heliosphere are called these dropouts that are mass per charge dependent. And it's very strange, mass per charge, a helium 2 plus 2, 4? 2, I'm blanking now. Yes, no. So mass per charge, 2, right? I get confused. Anyway, so the idea is that you have these dropouts, these very anomalous dropouts in mass per charge 2 ions, specifically at that mass per charge. And these are, I guess it's worth differentiating between energetic particles, which is what Gabriel was talking about, versus the thermal population of the solar wind, which is different. They can be different in many ways. In that case, what we were finding, we went through this modeling process back at the sun. This is a paper that John Raymond published last year, where it was found that we found that there was a resonance with helium 2 plus that absorbed the energy and didn't allow that energy to be translated to the other ions. And so you have this depletion modulated by what was happening back in the corona. So in that way, I think it could be really interesting, and that would go into the kinetics of the heavy ions. Unfortunately, heavy ions are a minor component of the solar wind, so oftentimes we have super low resolution compared to the resolution that we have of protons and even helium, which is 8.5% by number density. And so the minor ions are 10 to the -4, 10 to the -5. And so they're still, it's really hard to get them at higher resolution that you would need to say something very concrete about the wave-particle interactions. But I think as you get into, you start making instruments that can have with a bigger effective area, for instance, you can capture more details of the heavy ions. The heavy ion sensor on Solar Orbiter does have, in theory, could have 3D information of heavy ions. And that's something that's really interesting because we've never been able to do that before. And so you have now potentially a way of teasing out some of the wave-particle interactions that's happening locally, at least. And then, of course, with UVCS, we've seen, right, the outflow of heavy ions being preferentially accelerated in polar corona holes and also preferentially heated, right? So if you look at the temperature and isotropy of heavy ions versus something like protons, that's very distinct, even low down. So you have this, very low down, you're already out of thermodynamic equilibrium among these ions and these populations. So there's a lot that you can do. The problem then becomes we don't have measurements like UVCS right now, and the heavy ion sensor on Solar Orbiter is turned off. So there's an issue of observations of heavy ions in general that I think they're such a powerful diagnostic of a lot of things, but we don't have measurements that we have or can connect to each other. So that's my spiel.
The next question is from Craig to Gabriel.
Oh, thanks. So at what altitude range do you want tens of seconds observation? Is it even in our field of view?
It should be. I believe most of the SCP event, or at least SCPs that I've mentioned today, as well as other ones that I've looked at, they seem to be flare associated. So that would suggest that, and also, you need quite a lot of energy, and the flare is basically the best location for this. So you would expect this to be occurring pretty low. Additionally, I'm not so sure it's well sorted exactly if they go from 0 to 30% speed of light immediately, or how quickly acceleration occurs. Through the collisional region, they are obviously not moving as quickly as once they hit the what do we call it? Freeze-in distance. Freeze-in distance, which is collisionless. That's probably where their speed gets locked in, at least if they started below that. So it's possible to view there. Additionally, I suspect we might be able to see a shockwave traveling through F corona. So I'm not so sure how well Punch is going to be able to characterize polarization in the F corona, but I would think we should be able to see an SCP shockwave moving through on the scale of something like 20. Well, for my event that I showed you here, that was a particularly fast event, but there are others that can go as slow as a minute or so across the field of view, which I think is hopefully doable.
Okay, so particularly with NASA in the room, I have to remind everybody that we are not running campaigns in the primary mission. That said, let's talk and see if something's feasible after the primary mission.
Great, love to.
Then the next comment is from Bernie.
I have kind of two comments, but Kurt, Dave Webb and I wrote up the map CIRs in the brightness data from Helios long before SME or stereo were flown, and we showed the segmentation of these structures as they rotated around. And that was kind of that's an interesting thing. I wrote it up too further in another paper that I had, but, and then me here. I've, by the way, I have to leave pretty soon because I'm on an airplane to San Diego. But anyway, have you seen the recent high resolution 3D reconstruction of the Halloween storm shock that I have been showing around for about a year? It's on a website that
I should look at that.
It's really interesting.
Yeah. I should send me a link if I don't have a link.
lws.ucsd.edu.
Okay, I'll remember all that.
Okay, the next question from Craig to me here.
Thanks. So those flux versus delta V scatter plots are pretty great because they show that there is an effect, but they also show that it's a small effect. So what hypotheses are being batted around for what the rest of the effect is?
Well, it could be seed population differences, it could be, you know, connectivity, as I said, it could be theta B, and all those factors could end up playing small roles that cumulatively try to eventually explain the final result. But as I said, previous studies like Kaler did this long time ago, SEP peak fluxes versus just the CME speed from LASCO or some coronagraph. Now that showed the same speed had 4 orders of magnitude variation for the peak fluxes. Now it's 2 orders, so we're going down the right path, I guess. But you know, I think in order to get it accurate, we have a lot. Hopefully, you know, that keeps us in business as well, right? Speaking of, just a comment on Yemi's lack of heavy ion measurements, we will have a previous composition instruments, not sure as good as his. I don't know what the 10 minutes, that's because they're closer in and fluxes are higher. So this one is 1 AU, so, but we'll get it probably about 20 minutes to half an hour.
Okay, do we have any questions that are not from Slido? Lika?
Oh, Lika, can you hang on just a second? Announcement, you said. No, I was going to do announcements.
Okay, so let's thank the speakers again.
All right, so, oh, go ahead, Lika.
I didn't hear what you said. So this is kind of important for this panel. That's why I'm making the announcement. First of all, thanks to all of you for this half a day of presentation. They were excellent. And what I wanted to tell you is that you might not be aware, but about over a year ago at NASA headquarters, Heliophysics Division, we created sort of 4 different domains. Inner heliospheric domain, magnetospheric, ITM, no surprise, and outer heliosphere. And I'm leading the inner heliospheric domain. Any domain that kind of presupposes that there is a boundary is always a tricky one. So I have assumed my domain to include, you know, all the way to L1 and beyond the sun's interaction, including the terrestrial planets. So what I saw here today, it is like amazing, bringing together stereo, SDO, SUVI, Parker Solar Probe, all these variety of you know, observatory that we have presently, and what you have showed collectively touches on so many important questions. I am also leading an effort in artificial intelligence, and I'm really interested in sort of pulling some of you together. So the reason I'm making the announcement is that I might reach out to some of you to form a group to kind of orchestrate how we bring this together. And I will look at it in the beginning with the lens of kind of bringing the tools of artificial intelligence to what you are doing already, right? All these models. So just wanted to make that announcement. Don't be surprised if I reach out to you. All the posters and the talks have been just excellent. Thank you very much to the organizers and the speakers.
Thank you, Lika. That's great. And let's do a round of applause for everybody who spoke and did a poster today, because it's been amazing. So. Okay, so I know what you all are waiting for, and sure enough, on the other side of those doors is our reception. I just wanted to let you know one thing. Let's see how late we are. Okay. The picture outside was the backup picture, because we're planning a picture where everybody's going to be wearing their punch Polaroid sunglasses. Carrie Don's going to take it. So at 6:30, we're going to, so you have time for drinks, get some food, hang out, whatever, and then we're going to call you together so we can take this Polaroid picture, which means if you haven't got a pair of Polaroid sunglasses yet, make sure to get one. They're at the front. Second, I'm really happy to say that we've got our outreach colleagues here, and they're going to have a table, I believe, outside by the drinks, showing you some very cool displays that you can check out, both before and after, because this will go on till 8 o'clock, I believe. Yeah. And then at 6:30 when we do the picture, we also going to have, there's another outreachy thing right here. So there's going to be lots of fun stuff to do and food and drinks. So thank you very much.